just adding another slide.
Do you need me to just kind of buy some time here?
No. I hope there's not too much drama with connecting this. There has been, though, right? It's just a little student stuff.
Test. All right. Hi, everybody. Welcome to day 2 of VeloxCon. We have yet another packed day of sessions, so I will not go through a ton of details, but for folks who may not have been here yesterday, just a few housekeeping items. As a reminder, we are live streaming and recording everything, so you will have access to that after the show. We do also still have the conference room available called Chips and Salsa for ad hoc conversations, meetings. If you needed some more privacy, you can head into there. One note, we will have lunch and snacks and coffee this morning, but everything will end at 1 p.m. sharp today. So make sure you get lunch and everything before they clear up. And then, of course, we can use the micro kitchen next door after that. Finally, when you leave today, make sure if you are not a Meta employee to find a Meta employee. They'll be hanging out in the back out there in the hall to escort you out. And then we're going to try to take a conference photo before lunch, so please stick around so we can get a big group right before that. Okay, I am talking slowly as Greg is making final changes to his slides. But if Greg is ready, we will introduce him. All right.
I think we're ready.
Great. So I'm happy to welcome Greg and his colleagues from NVIDIA, who will be talking more about the work they're doing with Velox and GPU.
That's great. Thank you so much, Ali. And thank you guys so much for your time and attention today. So I'm here with Karthikeyan and Shruti on my team. We've been doing great work in Velox-cuDF, and we're just so happy to be part of this community. And we've made a lot of progress since last year. Really excited to talk about where we've come and where we're going next. So today, I know there's a lot of Spark content today and a lot of Presto content yesterday, but most of our integration efforts so far have started with Presto Velox. But of course, everything we're building in Velox-cuDF applies equally well to Gluten, and we have a lot of internal results about that. But today, the focus we want to emphasize is the Presto execution on GPUs using Velox and NVIDIA CUDF. So if you're not sure, if you haven't heard about this integration, or you want to learn a little bit more about how it works, the right way to think about it, that's where I want to get started and introduce CUDF a little bit for folks who haven't worked with it before. And then I want to go into Presto GPU performance. We've been looking at TPC benchmarks and scaling out on some GPU clusters as well to get up to 30K. We recently did in the last few weeks. And then I'm going to hand it over to Karthikeyan to talk about our development roadmap in Velox-cuDF. You've seen a lot of his work and the team's work in open source, and that's only gaining momentum. and then I'll hand it over to Shruti to update on where we are with TPC-DS expansion, which has been our main focus this quarter. So yeah, we love Velox. Velox is great. This has been such a great partnership. Really kicked off in a strong way last year after VeloxCon last year. And Velox is great. And the open source community is a huge draw for us. CUDF is open source as well. And we use open source building blocks for GPU execution. And all C++ execution, CUDF's main APIs are C++ as well, so it's very easy to map these together. And the pluggability and extensibility of Velox is really part of what makes this possible. Like, you couldn't plug in a new executor if that wasn't a core part of what Velox wanted to do from the beginning. And then, that's the engine itself, but also in the way you deploy it and use it. Velox has broad goals for batch, ETL, interactive, the AI training, offline and online pre-processing use cases. So Velox has invested a lot in the compatibility layers out to different front ends. And that's just a super valuable thing about the ecosystem and one of the best parts about the community. The deployments via Spark, Gluten, and Presto C++ have made huge progress. The migration updates we got yesterday from Meta and Uber, these are huge milestones. I mean, the pathway between 90 and 100% was awesome to learn about in detail. And these deployments are just make it such an attractive community, and we're delighted to be a part of it. Okay, so but what about CUDF, and how does CUDF fit into the story? So CUDF is an open source CUDA C++ library for GPU data processing with C++, Python, and Java bindings that you can use to access the algorithms in CUDF. And Velox-cuDF is it's in the experimental namespace in Velox. And we've got a driver adapter that lets you replace all the GPU operators, or all the CPU operators with GPU operators. And this is kind of an example here in the diagram. You'll get plans. The Velox worker will get plans in from the Presto coordinator or through Gluten. That's an executable pipeline in Velox, and we use the driver adapter to convert it into a GPU pipeline. And now we've got these CUDF vectors that can point to data that remains on device, and we can do end-to-end GPU execution using this replacement model. And now, when you run Velox-cuDF, we run it a little differently than Velox is used to running. So it's pretty impressive that Velox is still able to execute well when we're running single driver or two drivers, where Velox is used to running with a driver per core, and bigger batch sizes as well. We don't want to process kilobytes of data per task. We want to process hundreds of megabytes or gigabytes per task. So, but Velox is flexible enough that this hasn't really been an issue yet. It hasn't required any special tuning really either. Velox-cuDF also extends the connectors because, as we know, like getting I/O right is critical, and we're able to keep some of the metadata processing for Iceberg, for instance, in the main Velox implementation, and just take the heavy compute parts like deletion vector processing and move that to GPU. So Velox has made a great framework to build in a GPU integration, really at the ground floor of the engine. All right, so. I want to talk a little bit about the CUDF ecosystem and why Velox is so important for it. So, if you look at the stack to like reach a runtime like Presto or Spark, and you want to try to accelerate that, you need some sort of compatibility layer to map down to a different way of running it that isn't the way it normally runs. You need an execution engine that's going to be in charge of using the resources to compute the plans, and you need operators to do each step of that, and those operators need to call algorithms. So, go back 2 years ago, and Spark Rapids was the main way that distributed ETL could access GPU acceleration and CUDF. And Spark Rapids, it's open source, and all that code, they had to write their own operators, they had to write their own execution engine, they had to do all the Spark compatibility, and that kind of fits in this big Spark Rapids bubble here. And then we've done the similar work with Polars and DuckDB as well to like build up all the interface that you need for Polars, a Polars user to get access to CUDF for data framework, or a DuckDB user to get access to CUDF. But we haven't found a way to really reuse code that well between these stacks. But Velox has really changed that for us, because Velox gives us an execution engine that we can really separate the execution needs from the compatibility needs and reach Spark and Presto with the same operator. We write the operator once in Velox-cuDF, It ties into the algorithms that we've been developing over years in the CUDF library, and then we can tie it into any Velox app from there. So Velox has been a really, really great tool, and we're really pivoting our efforts in CUDF to focus on that part of the ecosystem. And we've come a long way. So last year we talked about, we had just scrambled to get together a TPCH run through Velox as a pure Velox run at scale factor 100 last year. And since then, the first thing we were trying to do is, okay, well, running via Velox is great, but we need to really run through Presto or another distributed runtime. We targeted Presto first. And we got to start upping the scale factor. So by Tech Exchange last year, IBM Tech Exchange in October, we got the 1K run to go on a single GPU, and then a Presto worker doing the job, getting plans from the Presto coordinator, setting it up the right way. And then the big breakthrough happened this year with UCX Exchange to let us do multiple GPU workers communicating smoothly. And Marios is going to talk more about that later this morning. So it's a crucial feature here because you need to have a fast shuffle tool to make these workers go smoothly together. If you take GPU workers and they have to use HTTP exchange, you can't get, they end up idle is what happens. So you need a fast shuffle to make this work. And yeah, so for GTC, we got a 3K run up on multi GPU with 3, 4, 5, 6, 8 GPUs. And then recently we've been scaling out on a cluster where we can go and do 10K and 30K. And I'm going to share more about that in the performance section. Plus, TPCH is great, but we need to get DS, and then we really need to get the next round of operators that are crucial for customer workloads. So that, I view these as early milestones in the real work in customer-facing workloads with their data types and data sources and UDFs and all of it. That's really the focus moving forward from here. But we have made great progress in this quarter on TPC-DS that we'll get to a bit later. Okay, so on the performance side, one way to zoom out on the ecosystem is to look at how Presto Java, Presto C++, and then the Presto GPU runners, the data that we're collecting regularly on these different modes of running Presto. So Presto Java to Presto C++, this gives, when we do this test in the cloud on small clusters at a TPCH 1K, we see the 5x speed up that folks at Meta and Uber have also kind of presented the same order of magnitude from their migrations. And this is great. And Presto Java has started its open source journey in the early 2010s and attracted a big community and has been really, really successful, and I think the whole Presto ecosystem is doing a great job pivoting over to native execution and getting big benefits from that. One of the things that's great about Presto C++ is it makes it much easier to tie in GPUs than it would be straight into Presto Java. That'd be a much harder thing to do. But with Velox, there's a good way to do it. So these numbers, we're showing more speedups going to GPU with A100s and B200s. Now I appreciate we moved from cloud to on-prem, and we need to be like, we need to talk about our data sources carefully here, but if you can get a hot cache run, the GPUs can really scream through, and there's more speedups to come. So to give a little bit more detail about the TPCH 1K and 3K picture, I have some CPU runs here with 8 nodes running versus a Lustre data source, and we're running it as hot as we can with the async data cache and soft affinity and discarding the first run and all that. And then I'm comparing it to a few different GPU counts running the same workload, because we can run 1K on a DGX. A DGX has 8 GPUs on it, but you don't have to assign all of them to the job. So you can have 1 or 4 or 8 working on 1K together. And at 3K, we can have 3 GPUs or 6 or 8 GPUs on this DGX working together to complete the queries. And these speedups are in the 3 to 10x range, and yeah, we're kind of focused on running as hot as we can in both cases here. So there's our internal resources are focused on on-prem testing, but we're really interested in extending this to the cloud as well, working on the P4 and P5 instances, and also the G7, G7E instances will be our main targets. Before our on-prem resources, we can also reach higher scale factors with a system that we're building out that we hope can be kind of a standard in what speed of light GPU data processing looks like. So NVL 72 GB 200 with IBM storage scale system. This is an on-prem system in our lab that we've built out, and it kind of eliminates the major bottlenecks that GPU data processing has with I/O and shuffle. We want to make sure that this runs at speed of light and runs as well as it can. You could imagine having the system servicing millions of queries, and just load balancing across the 72 GPUs on it. So you should think about this system not as like, instead of having a cluster of CPU, you'd have this like tightly integrated GPU cluster with really good, really high capacity storage that's super fast, and super fast connectivity between the GPUs, and tons of compute available for data processing. So a few of these NVL72 pods could service a huge query load is the kind of the idea that we're working towards. So we're bringing this up. We brought up the system just in the last 2 months, and this is the first results to come off of it at 10K and 30K. So we're running in 2 to 3 minutes at 10K depending on the GPU count, and about 5 minutes at 30K for 24, 28, 32 GPUs. And then there's some overlap with at 10K we can run it either on the DGX, which is like a single node. It's kind of like a P5 instance that you can get on AWS. You can run up to 10K on the single node, and you can also run that on 8 GPUs on the cluster as well. So it's taken a lot of work to stand up the storage scale system and have it work smoothly with Velox. But basically everything you need to run this comes in the open source now with UCX Exchange, and to get the storage to run well, you need a GPU direct storage, so you can directly send data RDMA into the GPU memory from the storage cluster. And we have a blog post coming out about the storage and I/O side, that the setup that works really well, and what we encourage folks to use. And if you're interested in doing testing on the system, we want to publish a reference architecture about this NVL72 and storage scale system. So the email here, dalinfo@NVIDIA, we're looking for, we have a few partner slots available to do development and workloads on the system and make sure it works as we're designing it to. So yeah, this is part of where we're going with Presto GPU is on the performance front. And from here, I want to really, this is VeloxCon. We need to go back to Velox for a bit and talk about what's been happening on mainline, what we have in open PRs, and what's coming next. So I'm going to hand it to Karthikeyan.
Thank you, Greg. So yeah, let's transition to discuss about the Velox-cuDF project update and our roadmap. So over the past year, we have transformed this from an experimental module to complete true powerhouse. And I'm excited to share the progress with you. Yeah, so first and foremost, I want to emphasize that NVIDIA is fully committed on the open source development, right in the Velox's main branch. So everything we do is built in the open. cuDF library is built in the open, and Velox-cuDF is also built in the open. To give you an idea of our momentum, so last year at VeloxCon 2025, the Velox-cuDF amounted for less than 1% of the pull requests. Fast forward to today, more than 10% of the pull requests, monthly pull requests, are coming from Velox-cuDF. And that's an incredible momentum due to the open source community. And we have made big improvements in functionality in Velox-cuDF. We have made huge improvements in Velox's CA infrastructure. So we're enabling dedicated GPU builds and GPU unit tests, and first tests are coming. So we have to give big thanks to our partners at Meta and IBM, who made the continuous integration possible. So their help in setting up continuous integration in Velox-cuDF helped any contributor to develop and test their code before committing to the Velox. And next, because of this, we have had a lot of contributions from the community. And IBM research has actually already merged the UCX exchange, which allows shuffle between the GPUs using NVIDIA and NVLink. Okay. Let's look at the code architecture here. So we have Velox, massive Velox code base with more than 640,000 lines of code, which has connectors, CPU operators, and then expressions. On the right, we have CUDF with GPU data structures, algorithms, and GPU readers and writers, amounting to more than 190,000 lines of code. So in between sits the lean critical bridge, Velox-cuDF, with only 18,000 lines of code. This bridges the gap between these two massive code bases and brings GPU acceleration natively to Velox. Let's see what we have achieved with this architecture. So today, we have successfully GPU accelerated 34% of the GPU operators, of the Velox core operators, and 37% of the data types. We heavily focused on fixed width data types, string data types, and we are currently near completion for full decimal support, which is critical for financial workloads. And we also support list and struct data types. So for the expression, we have added a lot of functionality to the expression evaluation. So currently, for Presto and scalar functions, we support 19 scalar functions and 6 aggregate functions. And Windows aggregation is currently actively worked on with the open PR right now in the Velox. And we have made massive changes to expression evaluator. And we made it this made it easy to add any new functions to expression evaluator, which sparked a lot of amazing community contributions. And none of this is not possible without the amazing community. So we have merged over the past year more than 250 PRs and with 60 issues. This incredible momentum was possible with more than 20 contributors from like NVIDIA, Meta, and IBM. And to all those super cool developers in the audience and watching video today, thank you. You are the reason for this incredible momentum. And let's go and look at the next Velox-cuDF roadmap. So going forward, stability is our #1 priority. So now we have the Velox's CA for GPU, which runs dedicated GPU builds and unit tests. Every commit to the Velox-cuDF module is actually verified before it gets committed. And we have new features coming up for operators, aggregations, and expressions. For operators, we will be adding more and more features for the joins, and we will be adding support for the window operator. And for aggregations, we are improving the streaming aggregation so that it can handle even more higher memory workload. And for the expression engine, we'll be expanding our coverage from like 19 functions, 19 plus 6 functions to more than 100 functions soon. And Velox has this massive fuzzers, incredible fuzzing infrastructure that tests different parts of the Velox modules. So we'll be expanding that to Velox-cuDF also, starting with joins. And right now, our partners, anybody who wants to start with Velox-cuDF has to build CUDF from source, and that takes significant amount of runtime. So we will be releasing a CUDF tarball with full support from NVA Enterprise, so that it can be built from the binary. So stay tuned for that. Now, to go into detail about expression evaluator, so Velox-cuDF has 3 evaluators. One is AST, abstract syntax tree, then JIT, just-in-time compilation, and function evaluator. Function evaluator runs everything on each and every expression in an individual kernel. Now, CUDF has this fused kernel called abstract syntax tree, which can support simple expressions in a single fused kernel. Whatever the expression that is not supported, we can do some pre-compute on the function evaluator and pass the overall results back to the AST evaluator, and AST evaluator can do a full expression tree on the GPU in a single fused kernel. The same, whatever we can execute in the AST in a fused kernel, we can do it with JIT, just-in-time compilation also. And we'll be expanding more on JIT function coverage. Next, for the Flux testing, to make sure that we have a reliable and then a robust Velox-cuDF, we want to expand whatever the Velox already has on fuzzers. So they have join fuzzers expression aggregation. So we want to, we already have an open PR for adding join fuzzer, and we will be adding more fuzzers on expressions, then aggregations, then windows, then once we have GPU memory management and then spilling enabled, we'll have memory and spill fuzzers also. Now coming to the I/O part, we have an incredible announcement here for the I/O side. We will be adding Iceberg support to Velox-cuDF. So we are adding cuDF Iceberg connector and a data source, which will enable Iceberg v3 support. And this cuDF Iceberg connector offloads all the heavy lifting to the GPU side, like reading Parquet files, reading and applying deletion vectors into the cuDF algorithms in the GPU, and also schema evaluation. The core the metadata processing is still handled by the Velox core code base. So this will enable overall like Iceberg support in Velox-cuDF module. Yeah, that's all for the Velox-cuDF roadmap. Thank you for keeping up the incredible momentum. If you want to contribute, open up a PR with that cuDF in the title, and if you find a feature is missing for you to test or Velox-cuDF, just open up an issue. Our amazing contributors will take care of it. Thank you so much for your attention. I'll hand over to Shruti to talk about the incredible TPC-DS progress.
Thanks, Karthikeyan. I'm going to be talking about our journey into TPC-DS support, the features that we've added so that we can GPU accelerate this benchmark, and I will show us our performance story so far. TPC-DS is another popular benchmark for measuring performance of query processing engines. Compared to TPC-H, TPC-DS has more complex queries because it has a dimension modeling approach where queries rely on information from fact tables and dimension tables, and therefore it results in more complex query plans. It also has more input tables. TPC-H has 8, while TPC-DS has 24 tables and has more queries as well. To GPU accelerate TPC-DS, we have introduced new operators, window, nested loop join, hash join operators, and this progress has been incredible, and we thank our contributors at IBM to help us make this progress. Another advantage of ensuring that we are entirely GPU accelerating this benchmark is that we can now ensure that there is very little data transfer between host and device, and we don't have to rely on CPU fallback for operators. Even lightweight operators like, say, group ID, which since we have now accelerated on GPU, ensures that we don't have to do this back and forth between host and device. The pie chart on the right shows some of the new operators that we've added and the amount of runtime it takes for TPC-DS SF100. If you look at one of these, that is cuDF filter project, it is quite significant because for TPC-DS, it requires decimal support, that is operands that operate on decimal type inputs. Velox-cuDF now has comprehensive coverage for decimal inputs. We have decimal 64 and decimal 128 support, and which for arithmetic operators, comparison operators, and aggregators. The operands, if they are of different scales, we have support for automatic scaling alignment. And we also have custom GPU kernels for decimal division, since we need to match Velox semantics of half-up rounding. We similarly have expanded support for inequality comparisons with decimal input signatures. For decimal aggregations, we again have custom kernels for the sum and sum and average aggregations over group by and global inputs by ensuring that we are storing our intermediate partial states, aggregation states, in a serialized format. The kernels are able to serialize and deserialize from the state to the serialized format. Now, all of this progress has helped us run TPC-DS for SF100 and SF1K. So this bar plot here shows the query runtime for these benchmarks on two different test environments. Presto CPU, where we ran a single worker, and this is on a single node, on a machine with 2 terabyte system memory with 220 cores. Our Presto GPU run is, again, with a single worker on a B200 GPU. For both of these runs, we are using local repartitioned Parquet files as data sources. And what we see is that for SF100, when we compare Presto CPU to GPU, we get about 5x speedup over all 90, and this is across all 99 queries put together. Moving to SF1K, we again see a similar 5x speedup with Presto GPU running in around 350 seconds for 98 out of the 99 queries. The one missing query is, maybe I can talk about that a little. It's query 23. And one of the reasons that it's failing is because there is an exploding join. And this is an issue that we are likely to face as we move to higher scale factors, is how are we going to tackle memory management on device efficiently? With these results have been possible because of all of the ongoing work in terms of open PRs in Velox. We have support for all the operators that I mentioned earlier, support for ensuring correctness for TPC-DS, and various optimizations that we needed to ensure that we are using device memory efficiently. The runs here have been with a staging branch that simply aggregates a lot of the open work that contributors have taken the time to put in. With this, I would love to welcome developers to contribute to Velox-cuDF. Please do check out our issues on GitHub. They are tagged under cuDF. Also do reach out to us on the Meta Slack, say hi. We'd love to learn more about your workloads and what features you're interested in being accelerated on GPU. As Greg mentioned earlier, we are also interested in partnering on the NVL72 machine, so please do reach out on dialinfo, the email ID dialinfo. We have a deployment repo that is Velox testing, where that will help you deploy single worker and multi-worker Presto CPU and GPU. And do try it out with Velox and Presto with GPU acceleration. The link to the repo is on the slide here. We didn't get a chance to talk a lot about Spark Gluten integrations, but that's something that we are very interested in, and that is also under active development. With that, we come to the end, and we're happy to take questions.
And And I'll just remind folks, if you do have questions, presenters will be available out in the hallways during breaks. Okay. We are ready for our next one? Yeah. Okay. I'm really excited to introduce Ori from Meta. Ori is one of the co-creators of Velox and is going to be talking about TorchWave today. So Ori, I will hand you the mic.
Yeah, hi everybody. So I'm Ori from Meta, from Velox, and we'll be talking about how Velox is going towards new frontiers. Everybody's going to AI, and AI is the place to be, universally agreed, so that's where we too are headed, especially in light of the fact that AI is by now indisputably the main consumer of data. So we'll be covering a whole range of topics here, starting from the business case of why we do actually experience an organic need to move compute over to GPU. Then we'll be talking about this preproc pipeline and what it is and what are the opportunities and why PyTorch in its present form is not doing that very well on GPU and how we can improve that situation. Then we'll be talking a little bit of tech about how GPUs work and how you can get value from that type of platform, as it's by now like the main compute platform, so we should understand it better. And then we take some examples of kernel fusion, some examples of the actual workload, and then we'll have some thoughts concerning the difference between the AI world and the data management world. After all, you know, they're both talking about arrays, but there's all kinds of subtle differences of semantics. And if we have this mission of unifying compute across all the branches that matter, then our understanding of these spaces and how to unify them is of course crucial to our mission. So like said, AI is the main consumer of data, and Velox has had this objective of unifying compute, being like Dave Cohen said at the very beginning, that Velox should become the ABI for compute. And we are seeing this vision being realized now most recently through the integration with libcudf, where Velox in fact is the ABI for heterogeneous compute. And we'll be extending the same notion to new frontiers, also including then the training preproc and things like that, AI adjacent. The message also already from last year is that the gains from brute force optimization of, let's say, vectorization on CPU or straightforward offload to GPU have been achieved. There's very little like low-hanging fruit to pick there. That lunch has been eaten. So now to go further in our mission, we have to understand the application. We have to understand what we are doing, why we're doing. We have to have the big picture. The first instance of this is the introduction of query optimization last year at the same conference. Now, as you heard yesterday, query optimization is well underway. So we are taking charge of the front end, so we know what is the plan to execute and why we're executing it and what are the underlying possibilities in optimizing that. Similarly, this year we're introducing the full program optimization for pre-processing data flows for training, which is not exactly query optimization, but it is also a language technology about compilation, about understanding the underlying performance potential of the whole application. So now if we look at the data center situation, our biggest application in machine learning is arguably ads. And ads has this odd compute shape where you have a bunch of small servers running DPP that Elodie was describing yesterday. And this DPP runs on these small servers, and then there's bigger servers, typically with 8 GPUs. And then there's always the eternal question of what's the proper mixing ratio? How many front end, how many GPUs? So it used to be 4 T1s for one A100, and it would be 11 of them for a B200. And of course, how many you need on either side will depend on the application, and its mixing ratio is never right. You're always underutilizing one side or the other. So making resources fungible is a big thing, especially now that we're seeing public clouds building things for LLM use cases, which are predominantly GPU. We are building data centers for LLMs, and they are predominantly GPU. And this 40-60 mix of CPU and GPU in terms of power consumption is a bespoke mix that's nobody's building. So if we want to be fungible in where we're running, we need to be consolidating compute on GPU. So this is like the first business case that's really driving demand for compute migration to GPU outside of the core areas of training that have like always been on GPU. So then, let's see. Okay, now are we like wasting these valuable GPU resources by running preproc? We are not, because the utilization when we're running training is actually not that high. It's not like half the cycles are taken or something like that. And also there's natural breaks because there are patterns of all reduce and all broadcast, and there's other communication patterns that create like time windows where the cores are sitting idle and the network is busy. So we can interleave pre-processing and training. Now, for the product evolution, last year I was talking about VeloxWave, which is our go at doing kernel fusion and compilation for addressing SQL on GPUs. So we did do table scan with filter push down, and we did group by and hash join and the basic operations like that. But we did not have an immediate road to market for that, because after all, for us to deploy a system for generic data management, we would have to have a GPU data center for that. And the GPU data centers that we do have are geared towards training, and the economics of running data management on that kind of scarce resource just don't work out. So what does work out, however, this year is moving the preproc there, because we already have the GPUs. We take the immediately GPU adjacent part of this value chain of training data, which is the PyTorch preproc. And then if we can make that essentially for free by merging it in the idle spaces of training, then we already have the platform. We have a huge win, because Python preproc or PyTorch preproc represents about half the CPU consumption of DPP. Then we would, if we are successful with this, we would be at a ratio of 20 CPU to 80 GPU, which is getting closer, but it's not quite there yet. So, okay, so the preproc pipeline in general, it begins with SQL data frames. So like Elodie was explaining yesterday, so this is table scan, reading, filtering, data selection, data cooking for a particular model. So why is there a SQL thing to begin with? It's there because if we did have a materialized input for every model we're training, we would be running out of space. So we need to have like one master table of training data, and depending on what model we're training, we'll be picking different parts of that, different features, different rows. So we'll be selecting from that table, and therefore we'll be running on-the-go transformation first in SQL, and then because training wants to have even-sized batches, we have to rebatch them. So we make random-sized batches because of filtering, and then we make even-sized batches by consolidating them. Then we do tensor filtering, clamping things to a value range, and so forth. But the typical input size is, if the whole input batch is 1 gig, the individual arrays on which we operate are maybe 1,000 to 10,000 to maybe 100,000 elements. And if your GPU kernel is running on 100,000 elements, it's not running efficiently. For a single kernel launch, you need to process a pretty massive amount of data, much in excess of that. But however, if we have 100 independent operations, each with 100,000 inputs, then the situation is already much better, and we can create what we call a full wave. That's a GPU term for a single request that will saturate the device. Okay, so the way TorchWave works is plugging into the PyTorch execution framework, where PyTorch first runs everything in Python interpreted mode, and then it produces a trace, which is called an FX graph. And this graph is like a trace of the compute that took place. And then any kind of compilation engine will then have this graph and a sample input as its input, and then it will compile it to whatever target. So Torch Inductor compiles to Triton, TorchWave compiles to CUDA kernels with a runtime compilation, and there's other runtimes that do other things. But there is a generic means of plugging in these things. So in specific, what TorchWave does when it sees a graph, it will do some simple transformations, eliminate no-ops from there. But the interesting part begins with like detecting multiply used computations. So if something is used many times, it should be completed before its first user begins. So then we cut the graph into layers. So suppose we have 500 independent operations. So then we look at all of these and see what are the inputs that are accessed by more than one. And then we put all these inputs that are multiply used in a separate layer. And then we look at that layer, are there multiply used things, and then we put them in another layer. And so then we execute these layers in sequence. But once we have layered these things, we have these layers that have hundreds of expressions each, and these expressions are guaranteed within each layer to be mutually independent, so you can execute them in parallel all at the same time or in any order. And then, having done this, we can look at this compute and then figure out how to make CUDA kernels from these by fusing them. And CUDA kernels GPU is an interesting platform because for any one algorithm that you want to execute on there, you have like a ton of different implementations, which will be, you will have to pick between these implementations based on your input size and based on other environment criteria. So it's a particular kind of puzzle. But the bottom line is that what is logically serially expressed but logically independent becomes explicitly parallel. So when programming GPUs, the basic unit of programming is a thread block. So that's a bunch of threads, like the name indicates, that are running the same program. So typically 2, 5, 6 threads per block. And then a grid is when you have many blocks. And a kernel launch is something that starts a grid on the GPU. And this starting a grid on the GPU does not come for free. It has, even if it doesn't do anything, it takes about 10 plus microseconds to start it and then see that it has finished. And then each of the blocks in the grid, setting up a new block is not for free. It's a microsecond or two. And therefore, these blocks should run for some double-digit number of microseconds at least. And the grid is not very efficient if it's running for less than 100 or 200 microseconds. Milliseconds are better. So then, given these constraints, there's a few types of things that are done on GPU. So element-wise is simplest. It looks just like a loop over an array. So you combine the first element with the first element of one, with the first element of the other, and you produce a result. And that's very straightforward. You can run that as wide as you want. And of course, as long as every block has enough work, it's a good fit for the platform. So matrix multiplication is not exactly element-wise, but it too is something that can be scheduled into pretty much infinitely many independent operations, and all you need at the end is one barrier to see that everybody's finished before you access the result. So then the other kind of operation that we run on GPUs is reduction of different sorts. So anything that is adding up elements of an array or filtering sets or doing prefix sums or anything like that is a reduction. And these can be implemented based on input size in a few different ways. So if you have a single block, then it's pretty simple. You just add up 2, 5, 6 elements in a highly parallel fashion, and you can, and then you remember the sum, and then you do the 2, 5, 6 next, and you remember the sum, and you do 2, 5, 6 next, and so on, which is very efficient, but it's not very scalable because you're hitting a tiny fraction of the device throughput. However, if you can do this algorithm on 100 or 200 inputs at the same time that are independent, it works very well. But if you have few big inputs, then what you got to do is do this in multiple stages. So you split the array into independent parts, you add them up, add up the sum on first and second and next, and then you add up these sums in a separate kernel launch because you have the first sums have to be computed before you can start with the second one. And then finally you end up with 3 kernel launches. And then you can hit more throughput, but the efficiency is something like 4 times worse. So then there's an intermediate form to just, you still need barriers, but you can have, normally you have a barrier between kernel launches. So you launch a kernel on one stream, it finishes before the next kernel that you launch on that stream begins. So that's a barrier. You can also do a barrier while staying on device called cooperative grids that has less latency, but it can tie up resources if the utilization is not even across all these blocks. So there's many different ways of orchestrating this compute. Now we look at the use case here, keeping this in mind because we'll be deciding what to do based on input sizes, and all of these implementations of one algorithm have their place here in this architecture. So here is an example. So what it does, this expression, what it does is not on the face of it readily obvious, but we can look at its components, and we see one reduction, which is a cumulative sum, a prefix sum. So every array element is a sum of all the elements before that. And then we have a bunch of element-wise operations like subtraction and clamp to, clamp a value to between bounds. And then we have a bunch of views, like that's extract without copying slices of tensors. And concatenation is also a view operation because then the inputs can fill in different slices of one big tensor without intermediate materialization. Okay, so then expressions like that in this one graph, we have a few hundred of them. So you can imagine like figuring out with the graph by looking at it is not readily obvious. But when we analyze it, we see that it falls into 13 layers. And many of these layers are some of them are compact, but many of them are tens of operations wide or hundreds of operations wide, which means that there's latent parallelism to do what normally would go sequentially about 100 operations at a time. And so this is the core knowledge, the core insight that we start from. So now, knowing that we have so much independent work to schedule, we have to translate this into kernel launches. And what the default operation does is doing them one kernel at a time, which hits this 100 or 10 microsecond latency several thousand times, so all you get is latency. But if you merge these operations together and put them side by side in one kernel launch, then your situation is radically better. So what can you fuse? What is fusion, first of all, if you have A plus B, and that's one kernel launch, and then plus C is a different kernel launch. That's not fusion. Fusion would be A plus B plus C in one kernel, and then it means that you have to generate the code of the kernel and compile it on the go to have it ready to execute. And this is the kind of fusion that Torch Inductor does. We do a bit more fusion because we can combine this with any kind of reduction. Again, if we're running a single block wide per expression, it's very easy because we can just put async threads between the input and the next stage and the next stage, and it's easy to synchronize that all the input has finished before you start the processing. You can do that at almost no cost if it's a single block wide. If it's a few blocks or tens of blocks wide, you can do a cooperative grid, and you can still stay on the device, and you can keep putting more and more operations in one kernel launch while running wide and staying on device. So the only thing that is not conveniently fusible is a situation where you first compute the size and you don't know the maximum for the size, and then you have to go back to the host and allocate the memory on device, and then you have to then pick up the computation. But that happens only 3 times in this whole graph. So typically we know the maximum size of the result even because we have reductions, but we don't really have like explosion of cardinality. So this is how we orchestrate that. Of course, Fusion has some limitations as well, because GPU likes simplicity. So there's a thing called register pressure. If your program is complicated, it may require many registers to run, and the more registers it requires, the fewer instances of that program fit concurrently in a GPU core called a streaming multiprocessor. So then this is why actually this vectorized interpretation that Velox is doing does not very well fit on a GPU, because if you have a big kernel that has every operation you could conceivably do rolled into it, some of these operations are complex and they take many registers, and then everybody's occupancy suffers. Occupancy means how many of any one particular thing fit at the same time on the device. So then it's kind of smart to put all the simple things together and all the complex things together. And this type of information can guide the Fusion decisions. Okay, so TorchWave capability, it being a native executor, it does not have to fuse absolutely everything. So the adjacent and consecutive parts that are all understood and supported can be fused pretty much without restriction. But then you can have some things that you leave unfused if they're big enough standalone by themselves. So adopting a thing like that does not require that you have custom implementation for everything, because you have a GPU fallback. And if the GPU fallback is efficient, meaning that it's doing enough work with few enough kernel launches, then you can leave it to be as it is. So there's to give an idea of the amount of parallelism, the grid, we have typical thread blocks of 256. You can fit a few hundred of them on an A100, on a B200. You can fit some 50% more of them. It's a reasonable thing to say that to make a full wave, you should have like 600 to 800 blocks of these things. And of course, if you have an integer multiple of that, it's even better, because then you keep the device busier. And oversubscribing on CPU is not always good, but oversubscribing on GPU is most of the time. I mean, I cannot think of an example where it would be harmful. So having a lot of work in flight is the thing. So this GPU programming, you can liken it to the game of Tetris, this first video game of all, where your win is when you get the whole width of the box full of these squares, and then you got these squares of these rectangles of different shapes that are falling from the top of the screen, and you have to rotate them so as to make solid lines that are fully occupied, and that's the analogy of your full wave on the GPU. So GPU, everything is kind of a square, and the GPU is a bigger square, and then you put these small squares packed as best you can within this bigger square. So that's the mental model that I find helpful to describing this. Okay, so then of course you have, when playing Tetris, you have to have good reaction time, because you have only so much time to decide which way you're going to rotate the block that's falling. So this is a scheduling overhead. So in some cases we find that when we can execute in 20 microseconds, it takes us 200 microseconds to decide exactly which should execute how wide. The trick here is, of course, we have many operations going in one kernel, and these each operate on different input sizes. And then depending on the input size, we might decide to do it a single block wide or multiple blocks wide. these operations also have a cost. So if you know that your operation is expensive, you will give it relatively more blocks than a cheap operation, because your other objective is that every block in the launch finishes around the same time. So there's all kinds of scheduling magic that we have to do, but we have to be deciding very fast. Now the good news here is that in these training workloads, all these data sizes are within 20% in one batch to the next batch. So typically you can cache these decisions. Okay, so here is a micro benchmark. So we have a tiny little thing, a PyTorch expression that adds up 2 tensors, and then it picks 9 out of 10 elements of the result based on a modulo of the size. And then we're running this with different input sizes and different numbers of these going concurrently, and we're comparing the 3-kernel thing, where you first do intermediate sums, and then you add up the intermediate sums, and then you finally move the data to their destination, either in 3 steps for a big input or in 1 step for a small input. And what we're seeing is, as long as we have enough small inputs, then the single block tends to win. And then we can see, based on the strictly sequential execution on GPU, we can see crazy multipliers depending on your input shape, like 60x or something like that. So mileage will, of course, depend on the actual application, but the fact of the value of launching a lot of work at the same time is foundational, and that's not in doubt. Okay, so now some thoughts about the kind of, if we come back to our mission, which is to unify compute across these value chains, and ultimately to create a better user experience, because this right now making these AI applications, recommender systems in this case, involves first this managing the data and putting together these training tables, typically big Spark ETL jobs. And then there is this other stage of pre-training, data reading, and data massaging in SQL on one side and PyTorch on the other side, and then there's the model architecture in the training proper. And so if we would have to have, and it's not exclusively Velox's task, but it should be an objective of our organization to have like an end-to-end understanding of this and to see what is a good way of talking about these compute flows. So now we have gotten a bit further into understanding this stuff because we have hands-on experience in both data and now also on tensors. And we have a few observations on what are the differences. Because if you squint, they're kind of both arrays. So, but there's some fundamental assumptions are somewhat different. In SQL, we're streaming through a bunch of rows, and typically we're talking about operations on scalars, and then these operations become operations on vectors by vectorization. But when we're talking PyTorch, we're also always talking about having a full data set materialized and materializing full intermediates, and always doing an operation on whole arrays, whereas SQL has a more like streaming mindset where you batch things that happen to be consecutive, whereas in PyTorch this batch boundary is very explicit and there's really no idea of streaming. There is quite a bit of functionality for multidimensional arrays in PyTorch, whereas we have a lot less of that in the data management side. There is a notion of zero-copy view on both sides, a dictionary encoding on one side or a slice of a vector, and then we have a pretty rich view semantics with all kinds of strides and zero-copy reshapes of tensors in PyTorch. So then this PyTorch model of doing an array operation at a time is really good on GPU because it's already like vectorized, so to say. But if your arrays are too small, it's no good because you need to have, I would say, tens of millions of inputs worth for a single kernel at a time approach to be effective. So this is the gap that TorchWave is filling, that is taking everything that's small and independent and making it into larger waves. Okay, so there's an A11 library that is the other interesting difference, or let's say user experience for these training workflows, is that you have kind of batch semantics on the SQL side, and you have full data set at a time semantics on the PyTorch side. And then when you go from one to the other, you lose some context. So you don't necessarily know, for example, what is the batch dimension. Even though one of these dimensions of these tensors represents the position in the batch, you don't know what dimension it is. So A11 is an addition to the tensor format that seeks to preserve this data and to create more transparency about the semantics. So the semantics carry better from one side of the fence to the other. Okay, so going forward, the basic arithmetic I'd like to leave you with is we have, on a modern GPU, we have host-to-device bandwidth of maybe 50 gigabytes per second, but the device internal bandwidth is over 100 times greater. So if we take the assumption that to pre-process one item of data, you need about 10 memory accesses, we should be done with a pre-proc if we're running at full device utilization in a tenth of the time it takes us to copy the data into the device to begin with. So this is the contention why we say that pre-proc could be for free. Now, of course, if this is all realized and we will be running our first end-to-end pipeline because we have enough feature coverage now, in the next couple of weeks, we will see how that goes. And ultimately, we'll tweak it until we have full device utilization and this bet is realized. Of course, this, when fully successful, is going to give us a mixing ratio of 20/80 between CPU and GPU, and that's not quite where we want to be because our destination would be more like 595, which then creates this organic need to also move the data frame, the SQL data frame and the table decoding and all the SQL gear into the GPU as well. And that is something that for which there will be a use case later. And this would be basically the first meta use case where we have a clear business case where it is obviously beneficial and needful to move traditional data management compute into a GPU, and then we shall see about all the libcudf and VeloxWave and all these different things that could be tried in that space. So that is exciting because our vision of this end-to-end GPU first data center is actually being realized even ahead of our expectations. Okay, so thank you.
Okay, I think we are in a break now, and we will reconvene in about a half an hour. Thank you. Hello, hello. All right, we're going to get started so that we can stay on time today. So I'll ask folks to wrap up conversations and grab seats. If anybody's listening. I don't know if anybody's listening to me. Sounds like no. Okay. All right, we are doing our best to stay on time today. So I am thrilled to introduce Marios from IBM, who's going to be talking more about the GPU work we are doing. Velox.
Thanks a lot. I'm Marios. I'm a software engineer at IBM based in Zurich. And the title of my presentation is Moving Bytes at the Speed of Light. So my presentation consists of two parts. First, I'm going to talk about GPU to GPU exchange. That is a feature that enables GPU to GPU data transfers across Presto C++ workers. And the merging process of GPU to GPU exchange in upstream Velox is still in progress. And the second part of my presentation is going to be about Zephyr. Zephyr is a distributed high-performance I/O system that lets us fetch data faster from object storage, and it provides a distributed caching layer that is based on Velox async data cache. But before diving into the details of GPU to GPU exchange and Zephyr, I wanted to give you a brief summary of the hardware that is available today versus the hardware that is going to be available soon, so that we know what we're talking about. So on this slide on the left, you can see the GB200 NVL72 rack from NVIDIA that consists of 72 Blackwell GPUs achieving up to 5,760 teraflops, having a GPU memory bandwidth of 576 terabytes per second, and the GPUs are connected with an NVLink network having a bandwidth up to 130 terabytes per second. And on the right side, you can see the Vera Rubin NVL72 rack that is announced from NVIDIA, and this consists of 72 Vera Rubin GPUs, achieving up to 9,360 teraflops, twice as the Blackwell architecture, having 3 times the GPU memory bandwidth compared to GB200, up to 1,580 terabytes per second, and having an NVLink network that is 2 times faster than the one in the GB200, achieving up to 260 terabyte per second bandwidth bidirectional. So I wanted with this slide to make it clear that GPUs are starving for data processing. And if we think about the cost-performance ratio, the busier the GPU is, the better the cost performance we get. So how can we keep the GPUs busy? By delivering the data faster. And that's what we're going to do with GPU to GPU exchange at Zephyr. So I'm going to start first with a GPU to GPU exchange, a new feature that we introduced to Velox. Thinking of Prestissimo multi-GPU overview, we have multiple Presto C++ workers, each one pinned to a single GPU. And we have the Presto coordinator that assigns plan fragments to those Presto C++ workers. Each plan fragment consists of multiple pipelines, and this pipeline is a sequential series of operators. Now, if we want to get this massive performance advantage from the GPUs, we must never leave the GPU during a query execution. And inside a single pipeline, this can happen because almost all the operators are supported from CUDF, so we never leave the GPU. But what happens when 2 or more Presto C++ workers want to exchange data between each other? In that case, Presto by default is using the so-called HTTP exchange, and as the name of this mechanism implies, the HTTP protocol is used, which is very, very slow. So what happens when we have a GPU cluster and we use the HTTP exchange? We have 2 major performance implications. First of all, we need to leave the GPU and go to the CPU. So we are bottleneck from PCIe throughput that is 32 gigabytes per second for PCIe 4 and 64 gigabytes per second for PCIe 5. But the second one, which is even more important, is that we use HTTP, so we will never reach even that throughput. And when we have systems like the ones that I presented in my first slide, we have NVLink bandwidth connecting the GPUs, and we want to be limited from the maximum throughput of the NVLink that is up to 300 gigabytes per second for NVLink 3, up to 900 gigabytes per second for NVLink 5, and this is going to be doubled in Vera Rubin architecture, up to 1.8 gigabytes, terabytes per second. So we want a mechanism that understands the hardware and makes use of NVLink if it's supported instead of the HTTP exchange. And this mechanism is called UCX exchange or GPU to GPU exchange. As the name implies, this exchange is using UCX network library. UCX automatically discovers all the available data paths and selects the fastest route based on the system topology, for example, NVLink in that system. So UCX exchange enables efficient GPU to GPU communication without manual tuning. So if we focus on a single VM, that in that case consists of 8 GPUs connected with NVLink, you can see the NVLink switches with a green color. If we use our UCX exchange and we want to transfer data between 2 GPUs that belong to the same VM, UCX exchange is going to pick NVLink in order to transfer data between GPUs on the same node. Now, if we have 2 of those VMs that we want to transfer some data between 2 GPUs that belong to different VMs, then UCX is going to use those orange RDMA-capable network interface cards, and it will perform a GPU direct RDMA for inter-node GPU communication. GPU direct RDMA means that we're never going to go to the host. So the path is like we start from the source GPU, we go to the RDMA-capable NIC on the first VM, then to the other side on the RDMA-capable NIC of the second VM, and then directly to the GPU of the destination VM. So how exactly UCX exchange is designed to fit Velox? On the left side, you can see a CUDF partitioned output operator that creates multiple partitions, and each partition has multiple CUDF packed columns. And on the right side, we have a Velox sync operator. And, if you think about it, the Presto coordinator is telling the right side, the Velox sync operator, that you need to receive data for a specific partition from multiple remote workers. And for that to work, we introduced the UCX exchange operator that upon receiving this message from the Presto coordinator, it creates a UCX exchange source object for each worker that it needs to receive data from. And this UCX exchange source on the right side is going to establish the connection over UCX with the left side where a UCX exchange server object is living. And then we have the data flow from the left side to the right side. The UCX exchange server is going to train the queue where the CUDF packed columns for a specific partition are stored. It will transfer them to the other side over UCX, exactly as I mentioned before, where a UCX exchange source will place them in a UCX exchange queue, and then the UCX exchange operator on top is going to train that queue. It will unpack the data for that partition, and it's going to pass the data upstream to the Velox sync operator. And this is going to happen for all the remote workers that are sending data for that specific partition in parallel. Now, talking about the performance using UCX exchange, in that case, we run TPC-DS SF1000 using 8 NVIDIA 800 GPUs, and this system supports NVLink. And we wanted to compare the performance using UCX versus when we're using the default HTTP exchange that Presto provides. And we see that we're always faster with UCX exchange, but especially for queries that are exchange heavy like query 9 and query 21, we see a massive performance advantage improvement. Especially for query 9, we see that it's 22 times faster compared to HTTP exchange. Now, another experiment, here I used a G7E.12x large VM from AWS that has 2 NVIDIA RTX Pro 6000 Blackwell GPUs. And I ran again TPC-SF1000 with HTTP exchange and with UCX exchange. And we see that we go from 1026 seconds down to 112 seconds when we're using the UCX exchange. And this is one order of magnitude faster, as you can see. Now, if we run the same experiment, but we make the GPUs not be collocated as in the first scenario, so we have 2 of those VMs, but we use 1 GPU on each VM, then we need to go over the network. And we see that for HTTP exchange, query 21 goes out of memory. Why? Because the latency increases of the HTTP protocol, because now we need to leave the VM and we need to go over the network. And this results to data staying more in GPU memory, and that's why query 21 goes out of memory. Now, if we use the UCX exchange, we get the exact same performance as in the first scenario where the GPUs are co-located in the same VM. And this happens because, as I mentioned earlier, UCX is going to pick the GPU direct RDMA for a GPU to GPU transfer over those RDMA capable NICs. So that was everything about UCX exchange. And now I'm going to move to the second part of my presentation, that is about Zephyr. So as I mentioned earlier, Zephyr is a distributed high-performance I/O system that lets us fetch data faster from object storage, and it provides a distributed caching mechanism layer that is based on Velox async data cache. Before analyzing the architecture of Zephyr, I wanted to show you this slide that I borrowed from Greg's NVIDIA GTC presentation. That is a breakdown of Presto GPU operators for TPC-H SF100 on the left side, and TPC-H SF1000 on the right side. And we can see from these pie charts that the table scan operator takes up to 74% of the total execution time for SF100 and up to 61% of the total execution time for SF1000, which means that fetching data and decoding data is a very expensive process, and we need to optimize it further. Now, I'm not going to talk about decoding Parquet data in this presentation. I will focus mostly on fetching data from object storage. So, as you know, a lot of clients have their data stored on object storage that can be Amazon S3 or Azure. And in that case, we need to provide a mechanism that fetches the data fast. So what happens on a Presto C++ worker nowadays without using Zephyr? The worker is going to fetch the data from S3, in that case, using the default AWS SDK S3 reader. It's going to cache the data in the Velox async data cache, and then it will decode the data on the GPU of that worker. So we moved from this version to the Zephyr architecture, where we disabled the Velox async data cache on the Presto C++ worker, and instead we moved it to a separate Zephyr server process, whose purpose is to fetch data from S3, cache them in the Velox async data cache, and then stream the data as fast as possible to the Presto C++ worker's GPU memory. So I wanted to focus on three things. First of all, the Zephyr server can live in a VM where no GPUs are existing. We don't need GPUs on the Zephyr server side. We just need memory. Secondly, we optimized the S3 reader so that we can fetch data faster from S3 even when we're using a single Zephyr server. And third, for copying data from CPU to GPU, we use exactly the UCX exchange mechanism that I described in the first part of my presentation. So we let UCX pick the right path for a CPU to GPU transfer in that case. Of course, the goal is not to have only a single Zephyr server, but to have multiple Zephyr servers and let them fetch data and cache data in parallel. So the architecture looks like that. We have multiple copies of the Zephyr servers. The Presto C++ worker is distributing the requests over gRPC to the fleet of the Zephyr servers, and then we let them read data in parallel, cache data in parallel, and stream back the data to the Presto C++ worker's GPU memory using CPU to GPU RDMA over UCX, using UCX exchange. So the advantages of the Zephyr architecture is that, first of all, we minimize the cold query execution time. Why? Because, first of all, we improved the S3 reader so that we can fetch faster from S3. And also because we increase the bandwidth by reading data in parallel. Secondly, when we have our data already cached in Velox async data cache, we can just stream them back without any extra copy, where just streaming the data from the CPU, from the memory where they're located on the Zephyr server, directly to the Presto C++ client's GPU memory. Third, we can scale out the Zephyr servers on demand. So based on the amount of memory we're using at the scale factor that we're running, we can create as many VMs as we want and run as many Zephyr servers as we want. So the RAM that we have in total is aggregated across those multiple Zephyr servers. And finally, we have a persistent cache across Presto cluster restarts, which means that if we run an experiment in a Presto cluster and we fetch all of our data across a fleet of Zephyr servers and then we restart the Presto cluster, this is not going to invalidate the cache. So second time we run the experiment, all the data are going to be there in the Zephyr servers. Now, talking about Zephyr performance results, the first experiment was to use a single G7e.12x large VM from AWS that has a single GPU, and they run a TPC-DS 100 with and without Zephyr. And if Zephyr is enabled, we're using a single C7GN.16x large, a VM that does not have GPUs, as I mentioned earlier. And we see that for the cold execution time, we go from 45 seconds down to 29 seconds. And that's why I mentioned earlier that even with one Zephyr server, we can be faster than the current Presto C++ worker because we improved the S3 reader. And that's how we can minimize the cold execution time. And for the warm, we see that it's exactly the same because if the data fits in memory, then we can just stream the data to the Presto C++ worker, and that's a proof that the gRPC is not introducing any other overhead. Now, of course, we want to scale with the Zephyr servers. We want multiple of them. So if we go to a higher scale factor like TPC-HS1K, in that case, I use the same VM but 2 GPUs, and I run TPC-HS1K with and without Zephyr. And if Zephyr is enabled, we use now 2 CHGN.48x large VMs. And we see that for the cold case, we go from 245 seconds down to 138 seconds. And that is like almost twice faster. And the warm case is exactly the same because of the reasons that I mentioned earlier. And now another example. What happens if we just want to fetch an 8 GB file using 3 Zephyr servers, each of them using a CHGN.24x large VM? So as you can see, each of those VMs is equipped with a 300 Gbps NIC, and the Presto C++ worker is living in a VM where there is a single 400 Gbps NIC, and we fetch this 8 GB file that can be a Parquet file, right? And in this case, it's a Parquet file. We fetch it multiple times. As you can see, first time we fetch the file, this is cold. So when we start the Zephyr servers, Veloxizing data cache is empty. So first time we achieve 20 gigabytes per second throughput on the Presto C++ worker. And from the second time and on, all the data is already cached in Veloxizing data cache across the Zephyr servers. And having a 400 Gbps NIC on the client means that we can reach up to 50, theoretical 50 gigabytes per second. 45 is the actual maximum throughput that we can get, which means that the Zephyr servers, when they have the data cached, they can fill up the NIC on the client side. And in that case, since we have 3 Zephyr servers, we see that each of them can push up to 35 gigabytes per second since we have a 300 Gbps NIC in each of those VMs. So if the client has 2 GPUs, each one connected to a NIC, then we can just have the exact same results per client. So those 3 Zephyr servers can fill up the 2 NICs on the client side, 2 400 Gbps NICs. So as a wrap up, GPUs keep getting faster and faster, but I/O still remains a bottleneck for data processing applications. And using UCX Exchange, we can unlock the GPU to GPU performance, making use of UCX library that automatically selects the fastest path. That can be NVLink or GPU direct RDMA across VMs regarding the GPU to GPU transfers. And we can use Zephyr in order to fetch data from object storage and cache them using this distributed caching mechanism that is based on Velox async data cache, resulting to end-to-end moving bytes at the speed of light. That was the title of my presentation. So thanks a lot for attending. If you have any questions, feel free to reach me out in the coffee break. Thanks a lot.
Are you ready to go? Or? Yeah, okay. Hey, good morning, everyone. It's been an interesting conference. We're glad to be here today. We are both from Data Pelago. I am John Janakiraman. I lead engineering for Data Pelago.
I'm Satya Billa, and I'm a technical fellow at Data Pelago.
So we're going to switch in the middle. We're going to switch in the middle. Okay, I'll start on the first few slides, and we'll proceed with Lakshmi after that. Okay. Data Pelago, we is a startup based in Mountain View. About 5 years ago, we realized something that is kind of common knowledge to everyone here, that data and AI are kind of driving forces in making technology advance. They're almost dictating everything today. Closely related to that is that there is a surge of innovation in accelerated computing hardware, whether it's in GPUs or FPGAs or TPUs and things like that. So that is what we set out to mine and build a data processing acceleration engine that will work for any processing platform, things like Spark, and be able to process diverse data on any infrastructure. So that was the genesis of the company. What we built is a core technology called Data Pelago Nucleus. And as the diagram shows, that is intended to unify both relational data processing, query processing, traditional query processing, and also model-based processing, where you can use machine learning models to drive processing itself. So that enables you to work on diverse data, whether it's tabular data or JSON type semi-structured data, or PDF files and so forth, on whatever hardware is available. If you have just CPUs, or if you have CPUs and GPUs, the cloud providers also provide other computing elements like FPGAs, and things may evolve in the future. We wanted to enable all of those things for our customers to be able to do the data and AI processing. So that's Data Pelago Nucleus. We'll talk a little bit more about it. Our primary product is Data Pelago Accelerator for Spark. And it is available in the cloud, in GCP, and in AWS. And we have customers who are actively running DPAs for serving their production workloads. Okay. data Pelago nucleus, if you are a computer architect, you need to define systems with very clean language interfaces, clean hardware interfaces, both for composability, which the community here knows very well, for also to be able to be future ready for future engines. Everyone knows there is a rapid evolution in the hardware that is available. I mean, from NVIDIA, from other players. Data is becoming richer. All kinds of data are being processed. And we're talking about Spark, and then Flink, and then Axiom. So the variety of programming models that are being applied is not going to stop. The data is going to become richer, and the computing elements that are available are going to become richer. So we need to build a product to be a sustainable product for the long term. So what we have is an architecture that drives that. So at the top level, we have basically an intermediate representation which provides a unified representation for computing models, whether you express it through Python or SQL or through Spark or Flink or Trino or Presto. We want to be able to absorb all of those things in a uniform way. That's at the top layer. And at the bottom layer, we want to have a hardware abstraction layer that makes it possible to run on hardware as it evolves. We don't want to change the entire stack just because we have a new generation of GPU in itself, right? So that is captured in the PDU accelerator interface. So in between these two things are the layers of data Pelago nucleus. There are basically three key components. I'll talk to them in the next slide. At the application layer, it's the data app, and that generates these IRs. And then at the bottom layer, there's a data VM. VM stands for virtual machine. And that is really the one that is at the bottommost layer. And in between, you have the OS kind of layer, which is the data OS. What I want to point out is that since this is Velox's execution engine, we saw yesterday, Masha talked about Axiom, a planner engine in C++. So we also believe that to be successful, our platform needs to combine the execution layer and the planner layer. So data Pelago nucleus encompasses both of them so that we can actually bridge the application to the hardware in an ideal way. So that's the overall architecture. So the components, as we described, right, they are data VM, starting from the bottom, data OS at the next, and then the data app layer. The data VM is very sophisticated. We have a lot of pride in building like the first industry's first domain-specific data processing virtual machine. So it basically is a virtual machine like you would think of as JVM or a Java virtual machine or an x86 machine or a ESX virtual machine, but it has languages that describe data processing. The data processing could be, find, personal identifiable information in some PDF file, or it could be, do a join, right? You can describe verbs like those things as part of that language, and that is all that we code to from the top layer. And that language is basically serviced by a device called the PDU. And that PDU is the one that everything, all the layers of translation, compilation, and interpretation about that, it codes to that. That basically allows us to insulate every layer above from the device specific itself. And then we realize this PDU on these various hardware elements, whether it's a SIMD CPU or it's a GPU, we realize on all of those things. Today we have data VM implemented on x86 SIMD machines, NVIDIA GPUs, Xilinx FPGAs. We have the entire stack running on all of them. So we can actually accelerate all of these Python and SQL platforms on all of these platforms. But it's built to be able to, when we have TPUs or other new devices, we can actually enable those things as well. The layer below that is the data OS layer, which has two functions. One, it's basically the thing that converts or compiles the intermediate representation that describes the application logic to the language that I described as the instruction set architecture. So that is one core function of it. And there's a lot of intelligence in it, which we'll touch on some of that when we talk about the planner. Just as you can figure out various ways to do joins, you can figure out what are the most optimal ways to execute a particular program using these instructions, just as a compiler does. It may be that there is no GPU, or it may be there are 2 GPUs, or it may be that there's only 2 CPUs. So all of those things are relevant in generating this compiled program. The other core capability of data VM is the resource management itself. How many operators are being currently executed, how much memory is available, right? So all of those things go into resource management decisions that Data OS takes at runtime. The last one is the data app. In the context of Spark and Trino and Flink, data app is a plugin. This is the one that makes our platform easy to interface to existing platforms. This is similar to how Gluten interfaces to Spark. And it can consume these Spark plans or Trino plans and convert them into this intermediate representation that is defined by Data Pelago Nucleus and is used by Data Pelago Nucleus. While in the context of Spark, we don't need to do all of the planning. Spark does its own planning. Data Pelago Nucleus also includes a full-fledged planner that can actually take the Python program or the SQL program and actually generate IR from scratch. So anyway, that's an overall component view of Data Pelago Nucleus. So for today's talk, we want to kind of highlight 2 of the key technical elements. One is the data VM, specifically its realization on GPU. As I mentioned, this is one of our crown jewels. Lakshmi will talk about it. And then following that, I'll come back and talk about some of the planner-related smart acceleration.
Thank you, John. So in the last year's session, we introduced this data VM and also explained why we think this is the better way of offloading the general purpose computation onto the accelerators. So you can see on the left side, it's most CPU-centric program. In a typical CPU, you usually have an ALU, a register file, and a control unit. ALU is the workhorse there. And all the software virtual machines typically mimic what the CPU does. If you look at the JVM instructions, it's mostly add, load, store, add, subtract, shift, and so on. Whereas on the right side, if you look at the data VM program, it's more high level. You can see the parse instruction, select instruction, building a hash table, and so on, right? So we covered these in the last session. So today, I'd like to shed some light on why we believe this is a better way of offloading general purpose computation onto the accelerators. So if you look at even though this slide shows that x86 CPU is not really an accelerator, but if you get into the details, most of the CPUs have, for example, AES instructions. That AES is typically done in less than 10 clocks. So it is in a way accelerator CPU. So if you go to the very bottom and see what a general purpose CPU looks like without any accelerators, right? So this is one such example. A chap called Stephen Dolan, he proved almost 10 years ago that a move instruction as it is defined in the x86 CPU is actually Turing complete. So which a move, as you know, is used to move data across registers to memory, and memory to register, and so on. And another chap called Chris Domes, he actually implemented a C compiler just for that machine, which means if you imagine a CPU with just move instruction, and then you can actually execute all your programs on that, just one instruction. So let's call that move CPU, just for sake of conversation. And let's contrast it with the x86 CPU, right? So on the middle, you will see a simple Fibonacci program written in C. On the left-hand side, you compile it, and then you got the right answer at 9. And then if you look at the object dump, I highlighted the instructions, the top-down. you see a comparison with 0, comparison with 1. Just like in the C program, there is n is equal to n is equal to 1, followed by a call to the Fibonacci recursive call, and then addition. So you can make sense of what is on the left-hand side. On the right-hand side, it's the same move compiler. You compile it down. If you look at the object dump, it's just full of move instructions. But you still get the right answer. Right? So now good luck finding where the comparison is and where the jump is and so on. But nonetheless, it's a very general purpose computer. It has no acceleration, just one instruction, but you can compile any program down to this CPU. So now what's the catch here? If not, I mean, if it can do anything, then why not build a CPU with just move instructions? So the same guy who implemented the C compiler compiled this Doom video game. On the left side, you can see it can do 60 plus frames per second, which is comfortable for playing a video game. On the right-hand side, the same Doom binary compiled using just the move instructions, it actually renders 1 frame every 7 hours. So you can see the difference. Even though the Xed CPU instruction set looks very primitive, it's actually orders of magnitude faster than the most general purpose computer, right? So if you go along the same vector, in the same silicon, you can see silicon implementations that are orders of magnitude faster than a general purpose x86 CPU. For example, if you look at switching ASIC in a top of the rack switch, for example, which typically has 40 servers with 100 gig linkage, and they all go to the top of the rack server, and that can do 40 times 100 is 4 terabit per second switching. So if you put a general purpose CPU inside in that, and then say, okay, go switch 4 terabit, it cannot, right? So there is a very special purpose chips designed in multiple generations to get to that 4 terabit per second. So if you kind of draw a system design 101 chart, where the most general processor on the right-hand side and the less general on the left-hand side, less performant on the bottom and the most performant on the right. CPU, move of course, our move CPU is the worst one. It's very general, but it's not useful. 7 hours per, 1 frame every 7 hours, probably a human can draw that whole frame by hand. So whereas CPUs or GPUs are a lot faster, but they won't give you the higher maximum throughput. And most of the accelerator vendors are on the left top. The switching, it's not really programmable, but it is really fast. So for example, Intel's Q80 accelerator, it does compression encryption. It does really fast, but it doesn't do anything other than those, right? So in this setting, where do we want to be? So we want to be on the top of the right-hand quadrant, right? So we wanted the most general purpose processing element that is high performant. Now, how do we get that? For practical reasons, we implemented it in 2 formats. One is a virtual machine, which we call the data VM, that it's most general, but it also, I mean, it's Turing complete, but it also has instructions at a higher level than a general purpose CPU. Now, there is another component to it, which we call PD, which is essentially a hardware specification that describes how to interface with the different types of hardware accelerators, and also what kind of hardware accelerators make sense and how to implement those, right? So that's what essentially the data VM is. This is the thinking behind our virtual machine. So with that in mind, as John said, so there's a PDU layer at the bottom, and you can take that hardware abstraction and implement it in anywhere. So we started with an FPGA. We took that, we had some learnings, and then we took that same thing on the GPU. So implemented the same interface and specification on the GPU, and then now, so I think we covered this one already. So now as I said, we implemented on the FPGA, and we had some learnings, and also there are it's a little bit different than coding an unconventional way of implementing things in GPU. So we took the PDU specification and implemented on the GPU. And we published some numbers compared to CUDF. So it's almost more than half a year old. So I'm going to skip this for now. So in the interest of time. So now these are some numbers where we ran, as John mentioned, DPS is our product. So we took the Spark, and then this is a general customer setup that most of our customers use, which is a Dataproc Spark implementation with 2 of those high mem nodes with 1 NVIDIA Tesla TPU each, T4 GPU each. And you might know the available memory is only 16 gigs, so two of those total is 32 gigs. So there's a lot of invention in innovative things in how you manage that, when do you evict asynchronous memory allocation and asynchronous things like that. So our data, most of our customers store their data on the cloud storage, Google or S3. And then in this talk, I'll just pick 2 queries, one from each, TPC-DS and TPC-H. And then the actual performance number doesn't matter because it changes on the cluster configuration. So we normalized everything to 100 seconds, and GPU utilization is mostly 100%. So on the left-hand side, what you see is the typical Spark plan, and the Velox column shows how much time, normalized to 100 seconds, how much time the Velox operator is taking. And this exact same operator, the last column shows how much time the same operator is taking on the data VM implemented on a GPU. Now, there are 2 main reasons why you see that gain. One is as I said, our data is on GCS, so we made some improvements there in the scan part, and also these are all Parquet files, so it's a Parquet decode part. And GPUs are really good at faster filtering part, so that's where you gain the filter part of it. And the second one is this TPC-H, one more from the TPC-H test suite. Here, this particular query is more heavy on the projects and aggregates. So you can see the project time is almost 56 seconds to 1 second, and then the filter plus scan part is 46 to 40 seconds. You see around 5x gain here. So that concludes. Thank you.
So that was, I guess, a quick view of how Data Pelago Nucleus works on some example TPC-DS. Our customers obviously are not running TPC-DS. I think everyone knows that. So when they are running some arbitrary workload, a common question that the customer faces is, well, what is this going to do for my workload? How much is it going to accelerate? It's a hard question to answer, as everyone who has experience knows. Acceleration depends on a number of things: what operators are part of the plan, what kind of data is being processed, what are the characteristics of the data, and then the acceleration engine itself, what does it involve? What are the fixed costs associated with the engine? What are the data conversions that are involved, and other kind of attributes? And then, if you know people who use Gluten and Velox know there is this fallback, unsupported operators fallback. So it's basically a mixture of engines that are being deployed. So some of them are executing in one or the other. So it's about what are the overheads associated with those engine fallbacks and things like that. So this simple way to deal with this thing is, you just say if the operator is supported, run it on the accelerated engine. Otherwise, you fall back. That's kind of the default Spark, Gluten, Velox approach. You could try something a little bit more, saying, hey, I want to optimize or minimize the overheads. So I'm going to now say if the stage supports all operators that are supported, then I'm going to execute that stage in the accelerator engine. Otherwise, I'm going to just run that stage in the Spark engine to basically hide the transition costs with the exchange and so forth. Or you can try to be a little bit more intelligent, say I'm going to assign some cost for the operator, and I'm going to include some high cost for the conversions and things like that. Those are all what we have found are quite simplistic. As you can see in the chart there, all the greens are supposed to be running in the accelerated Velox engine. The blue ones run on Spark, and then all the yellow things are all the transitions that go back and forth. So when you do these kinds of things, what we have found, I think people who have experience in the field also know this, is we are then delegating the burden to the user or the customer itself. What is the burden? First, the application itself may degrade because you are moving things back and forth, you can degrade. And if they want to avoid this degradation, they have to go through the burden of actually testing the workload, tuning the workload, configuring the workload. It's something that you can do for 10, 20, 50, 100 workloads, but if a customer has 1,000, 10,000 kind of workload, this becomes impossible task, right? So this is the problem. So what we built for that is something called smart acceleration. The basic idea is we want to optimize the performance of the workload by targeting the acceleration dynamically, not by configuration, upfront configuration, by targeting the acceleration dynamically based on runtime information. When you say targeting acceleration, it is about saying what is going to run on, if you have a mixture of engines, what is going to run on which engine, right, and how. So this dynamic engine includes decisions based on workload independent aspects. Is there a GPU here or not? And what is the speed up that I expect on my engine? Is the operator supported or not? And then there are things that are workload specific as well. What is the sequence of operators? What happens after this supported operator? And what are the characteristics of the data, what data types, how much data, and so forth. And we want to do this without requiring any configuration from the customer itself, from the user itself. So that's what smart acceleration does. Basically, there is a mechanism, and then there's a policy. The policy itself is based on a cost model. The cost model, at a broad level, it factors data related information. As you can imagine, shape of data, types of data, volume of data, and things like that. Statistics related with the data. Complexity of the operator and the data types, whether you have complex types or it's just scalar types. And then some characteristics of the engine. You need to know how your engine, what works, where it performs better, and what are the fixed costs, and so forth. So we have a model structure describing this cost model that we have built through studying our own system with a variety of workloads. And then that's a parameterized cost model, and we retrieve the parameters based on the runtime information itself. So that's the policy part of it. And the mechanism itself, in the context of Spark, it still uses the Spark plan. It captures the logical and the physical plans that are emitted by Spark. It also retrieves the statistics that Spark retrieves when it's available. We basically use those things to infer, because we may do more sophisticated filtering, so the data statistics change as you go up the plan. So we infer those kinds of statistics, and then we generate alternative plans, and then pick the one that is the most optimal using that cost model. So that's basically what we have. Here are some illustrative examples. Obviously, we do this for customer workload, but those workloads are all pages long. So we're trying to kind of illustrate the point here. So here, basically, it's a Spark environment. For this case, we are only using CPU because we want to compare it with off-the-shelf Gluten and Velox. The data set itself is a SF1000 TPC-DS data set living in cloud storage. These are all synthetic query. So in this case, you can see this specific query ran for 25 seconds in vanilla Spark. And Gluten takes a longer time. It runs in 52 seconds. The interesting thing is that for this specific query, all operators are supported by Gluten. There's really no fallback. So if you had a policy saying, if there is no fallback, I will just run the workload, you would be degrading your performance. So your workload will actually perform worse, even though there's no fallback. Now, with the smart acceleration, we are able to find out characteristics of the data and the operators and make runtime decisions to choose the right plan for executing, and with that, we actually perform better than both Spark and Gluten and Velox at 24 seconds, right? So that's one example. The other example, this is the last slide, yeah. The another example is similar, but here you can see that Gluten and Velox actually speeds up the performance, but we can actually perform even better than that. And in this case, there is actually a fallback because of the in-memory table scan. We don't enable the table cache flag. So even though there is fallback, Gluten Velox performs better, but we actually perform even better than that. Anyway, so this gives you an illustration that just using simplistic fallback-based decision to run it in Spark or run it in Gluten and Velox is not going to get you what you want, which is acceleration. And smart acceleration is kind of an interesting way to kind of address this problem and make sure that you don't degrade applications and you actually improve them as much as possible. Anyway, thanks. That's basically what it is. So everyone has talked about composable architecture. Basically, Nucleus is that. It allows you to run diverse programming models, Spark, Plan, Trino, and things like that on CPU, GPU, and other kinds of infrastructure. We talked about data VM, which is basically a platform for hybrid CPU-GPU acceleration, and then how smart acceleration can allow you to accelerate performance, and more importantly, do it in a way that customers can actually now widely deploy this platform for a larger number of workloads without having to do manual tuning on this. Thank you very much. Yeah.
Hello, I'm Yongil, a software engineer from Xina. Xina is a startup company that develops CXL memory controllers. First of all, would like to thank the Velox community for giving us this great opportunity to present. Today, I will introduce memory war and what is CXL and how CXL can be used for data processing and share our benchmark results. And after that, my teammate Sungwoo will share the experience how we integrated our data processing library, Xflare, with Velox, and how Velox can leverage CXL to improve performance. Modern computer systems are increasingly constrained by the memory war. Chiplet-based CPUs have scaled to hundreds of cores, but memory capacity and bandwidth have not scaled at the same rate. As a result, memory capacity and bandwidth per core are actually declining. CPUs spend more time stored on memory, so simply adding more cores no longer delivers proportional performance gains for memory-intensive workloads such as data processing. Meanwhile, DRAM cells scaling is approaching its physical limits, and server platforms are constrained by memory channels and DIMM slots. Scaling local memory is reaching its practical limits. We need a new cost-effective way to scale memory capacity and bandwidth. The cost situation is getting worse as well. CPU cost per gigaflops has kept falling, while DRAM cost per terabyte has stayed high and recently surged due to AI demand. Memory now dominates the total cost of servers, reaching up to 70% of the total server cost. Efficient DRAM use is now more important than ever. CXL is an efficient solution that addresses the memory war. CXL is an industry standard high-speed interconnect for processors and accelerators and memory on top of the PCI Express physical layer. By attaching CXL memory device into PCI slots, a server can expand its memory capacity and bandwidth beyond local DIMM limits. The CPU can access the CXL attached memory like main memory using normal load and store instructions. There is no special APIs and no DMA transfers to access memory, just to read and write memory. The key feature of CXL is hardware managed cache coherence between CPUs and CXL devices. This allows CXL integrated accelerators to share data with the CPU more directly without separate data movement steps. CXL also enables memory pooling across servers, allowing each host to allocate memory on demand from a centralized memory pool or use the pool as shared memory across systems. There are two major threats to performance in query engines like Spark and Velox, disk speed and data skew. These are also the key metrics to watch most closely when tuning Spark performance. Disk speed happens when memory runs out. Joins, aggregations, and source, they all maintain large memory states. Shuffle especially requires a lot of memory because of repartitioning. When memory is exhausted, data is spilled to disk and performance drops dramatically. Data skew leads to imbalanced partitions, so some tasks process far more data than others. The heavy tasks struggle with memory, while other tasks remain underutilized. So servers in clusters are often provisioned for the worst case, which wastes a lot of memory. Now, let's look at how CXL can help mitigate these challenges. First, CXL memory expansion provides additional memory capacity and bandwidth to a single server. With the CXL memory expanders, servers can go beyond the limits of traditional DIMM slots and memory channels. A single server's memory capacity can be expanded to tens of terabytes. This increases cluster memory capacity and bandwidth without adding more nodes. It is very attractive from cost perspective. Clusters can have larger total memory capacity and bandwidth with fewer nodes. More memory can delay or reduce disk speed, and fewer nodes can reduce the amount of shuffle data. Another important benefit of CXL is DRAM recycling. Data centers refresh servers regularly, but many DRAM modules are still usable after servers are retired. Because DRAM has a longer life cycle than servers, CXL memory expanders can reuse the DRAMs as an additional memory tier for new servers. Given the high cost of DRAM, reusing existing DRAMs through CXL can significantly reduce overall TCO. Disk skew creates a stranded memory problem. Some nodes run out of memory and spill to disk, while others have still unused memory. Since memory is attached to each server statically in conventional architectures, this imbalance is difficult to rebalance dynamically. Microsoft said the average of 25% of DRAM is stranded at Azure. CXL memory pooling can be a solution to this problem. Hosts can borrow memory from the shared memory pool on demand and return it after use. It allows those to meet peak memory demand without over-provisioning every server and reduce total cluster memory. A CXL memory pool can also be used as a shared memory across multiple hosts. By pricing shuffle data in the CXL shared memory, it can reduce network-based transfers, so shuffle overhead can be significantly reduced. CXL introduces new tiers in the memory hierarchy. We now have memory expanders and shared memory pools between main memory and storage. CXL memory expanders increase capacity and bandwidth within a server. CXL memory pools extend the memory hierarchy across multiple servers. These new tiers give us much larger capacity, but also have higher latency and lower bandwidth than main memory. Therefore, software needs new optimization strategies that are aware of this new memory hierarchy. More broadly, this calls for a shift toward memory-centric computing. The conventional computing model is CPU-centric computing. Wherever the data resides, it eventually brought to the CPU for processing. Because CXL memory typically has higher latency and lower bandwidth than main memory, when large data sets are stored in CXL memory and CPU process them directly, performance is often bounded by PCI bandwidth. This is where memory-centric computing comes in. Instead of moving data to the CPU, we move computation closer to the data. An accelerator inside the CXL device can filter and process data locally and return only the final results to the CPU. This reduces data movement significantly, so we can improve both performance and power efficiency. The key idea is simple. Move computation closer to the data, not data to the CPU. This is MX1. It is a computational memory we designed for memory-centric computing. It is also the world's first CXL memory device to support the CXL 3.2. MX1 is based on PCIe Gen 6, and it supports 4 channels of DDR5 RDIMMs, providing up to 1 terabyte of memory capacity per device. It integrates the 3,000 RISC-V cores for massively parallel computing to the data stored in the CXL memory. It also has 48 vector processing engines to accelerate vector search. These are our prototype device spec, and an upgraded production version will be released early next year. You can request the device samples at our homepage if you would like to experience memory-centric computing. MX1 is basically CXL memory expanders, so it provides additional memory to the server, and CPU can access MX1's memory as its own memory. MX1 also shares the virtual address space with the host process. When host process allocates CXL memory and maps it to a virtual address, it also copies the page table entry to the device's MMU, so both sides can reference the same pointers in the same address space. This is not the same as GPU unified memory, which relies on phase faults and migration. Because MX1 shares the same memory and page table with host process, there's almost no overhead. This also allows MX1 to remove the data input and output stages before and after offloading. No separate device memory allocations, no explicit data transfers, and no pointer swizzling and unswizzling. This simplifies the offloading process and significantly reduces data movement cost. This is our micro benchmark research on Intel's latest generation Xeon server. We compared one CPU NUMA node with one MX1 using some of the representative query processing operations, such as compression, decompression, and packet decoding, aggregation, and filter operations. We evaluated 3 execution models: CPU processing data in main memory, and CPU processing data in CXL memory, and MX1 memory-centric computing. MX1 achieved up to 4.7 times higher throughput and 18.7 times better energy efficiency than CPU processing data in CXL memory, and up to 2 times higher throughput with 6.2 times better energy efficiency than CPU processing data in local main memory. Since this is only one-to-one comparison, And each socket supports up to 4 CXL devices. We can expect up to 4 times the great performance in a full configuration. Now, I'll hand it over to Sung-woo.
Okay, thank you. Hi. In part 2, I'll be talking about how we are extending Velox for CXL native query execution. Before we go any further, I'm Sung-woo. I'm a software engineer at Xena, and I lead the development of Xflare. So what is Xflare? It's a CXL native data analytics library we're building at Xena. Think of it like a CUDF, but for CXL. So it's for easy adoption of CXL in your favorite data processing platforms. There are a few characteristics. It's written in Rust, first of all, and it's highly asynchronous to overlap the CPU work and memory-centric computing. It uses open formats, arrow for in-memory, and Parquet CSV JSON for files. It takes care of hardware orchestration for you, such as CXL memory allocation and kernel launching. It is a closed project for now, but once our MX1's production-grade version becomes generally available early next year, we will be opening to the public. So we wanted to bring in memory-centric computing to Velox by integrating Xflare. And when we designed the integration layer, what we wanted to do was create an extension instead of modifying the Velox core directly. So, well, thanks to Velox's nice extension framework, driver adapter, we were able to pull that off and extend Velox for memory-centric computation very easily. We call our integration layer collagen. So try to imagine how surprised I was yesterday when Pedro talked about their collagen project, and I thought the name was unique enough, but I guess not. So our collagen layer accepts execution plan and arrow batches, and hands them off to Xflare, which offloads computation to MX1's 3000 RISC-V cores. Driver adapter allows extension to replace a sequence of operators with a custom operator. So at each driver initialization, we scan for a sequence operators that we can offload to Xflare, and then we replace it with our custom operator, which sort of acts as a facade that just relays the request to Xflare core. There was a tiny challenge we faced. We need to pass the operator context from C++ Velox to Rust Xflare. So what we decided to do was create a custom protobuf, much like Substrate. So we encode the operator context in protobuf and then offload it to Xflare driver. We also needed to transport Velox's column across the collagen. Since Velox's column vectors are arrow compatible, we leverage that. So in our custom operator, we export the Velox column vectors into arrow CABI format, and then we export it to Xflare. And we import that into our own column vector format. And then when we are sending back the intermediate result back to Velox, we just go just the reverse process of it. That's me last year. After getting our MX1's prototype device, we were able to showcase our devices at OCP Global Summit and Supercomputing Conference. These are the biggest events for data center and infrastructure players to show their latest and future technologies. We did a live demo of TPC-H queries on Apache Spark. through Gluten and Velox and then Xflare using memory-centric computing. And if you think about it, it's quite remarkable because Velox and their idea of composable architecture opened an opportunity for hardware acceleration companies like us to test our device against very famous data processing frameworks like Spark. So this could have been like years of software project, but we were able to pull that off within a few months. So thank you, Velox. I want to conclude my presentation with a maybe new development idea. So from our extension journey, we came to believe that Velox can really benefit from having a CXL-aware memory allocation. So let me walk through 2 scenarios to illustrate that. In the first scenario, when memory pressure hits the limit, Velox goes through a memory arbitration process, and eventually some operators ends up spilling their intermediate data to the disk. With the CXL-aware allocator, you can delay and reduce the disk spills, which can benefit Velox for 2 reasons. The one, you're not spilling anymore, and then 2, you can also reduce the cost of memory arbitration process. You can also get smart with this and store data in different memory tiers according to your access pattern. So hot data like hash table can stay in the local DRAM, whereas warm data like row containers can stay in the CXL memory so that you can expand the memory and then reduce the CXL latency. The second scenario is allocating the value stream's row vector directly in CXL memory. Value stream operator is an operator that converts Spark's row-oriented data, input data, into Velox's column vector format. With current implementation, value stream allocates the row vector in the host main memory, which is quite inconvenient for us in memory-centric computation because our MX1's cores cannot access the host DRAM directly. So to start the memory-centric computation, we are forced to copy the data in the CXL into the CXL memory. But with the CXL-aware memory allocator, you can allocate the row vector directly in the CXL memory, and you can just start the memory-centric computation right away. So that's the approach we actually take when we offload table scan operator, for example. We allocate CXL memory for Parquet reader to load the pages from the disk, and then we just start decompression and page decoding right away. We can think of some hurdles to building a CXL-aware allocator in the current implementation. The current implementation doesn't allow the custom allocator to be pluggable. So we are gonna have to do like a driver adapter approach in this. And also CXL memory is a separate memory resource from host DRAM. So we are going to need to have a custom memory manager and a memory arbitrator. But we think that it's worth a shot anyway. So we will be communicating with the Velox community about this idea, and hopefully we'll get to make a contribution. So here are the things that you should take away from this presentation. Analytics is hitting a memory wall, and memory-centric computing can change this with higher performance and better energy efficiency. And this is why we believe that Velox can benefit from adopting CXL memory-centric computing. So that's it. And if you have a question about this presentation, memory-centric computing, or CXL in general, please come find us during the lunch break. Thank you.
Okay. Okay, wait, before people head out to lunch, we want to try to do a conference picture. So I'm going to be super annoying and ask everybody to move to the middle. You don't have to sit, just stand. I'm going to try to take a picture from the stage. Thank you. Hello. All right. Welcome back from lunch. We are going to get started. I am pleased to introduce Ankur from Meta, who is going to be talking about Project Flare and the work they're doing with gluten.
Thank you. Hey guys, my name is Ankur. I'm an engineer in the batch compute team here at Meta. Been at Meta and batch compute team for the past 7 years. For the past 1 year, a little less than that, we have been working on Veloxification of Spark workloads. So today I want to take this opportunity to talk about the work we have been doing, the challenges we have faced, and our journey so far. So in terms of agenda, I'm going to introduce our team. I'm going to talk about our motivation for Veloxification. We'll talk about how we got Gluten to Meta. Then I'm going to switch gears and talk about the migration that we are doing. As the mass migration, we want to make this offering transparently available to customers. We'll be talking about challenges. Of course, migration at this scale is many halves, sometimes many years. So we want to talk about how we are thinking about that, how we are working with gluten, some of the improvements we have made. And finally, last not the least, we want to talk about AI acceleration, the new tool, the new shiny toy we all have to work with. So I'm going to talk about how we are looking at that and trying to speed up the migration that's going on. So we are the batch compute team. We provide Spark as an offering to all the teams within Meta. We are a single warehouse. So anyone with analytics need who wants to run Spark, they kind of funnel through us. We get to see large volume of workload. We get to see large variety of workload. So PySpark, data frames, SQL, you name it, we have it. More importantly, we get to see people pushing the envelope of Spark, what Spark can handle. So people who have worked in Spark would know that Spark is kind of like, it's not an infinitely scalable system. Driver is the single point of failure. There are things that start happening as soon as you have a large number of executors, as soon as you have a large number of tasks, as soon as you have a large number of partitions and shuffle partitions, right? So when people come in and they try to push to the extreme to like tens of thousands of executors, we start seeing RPC bottlenecks. Sometimes they work with tens of thousands of partitions and millions of files within those partitions. All this metadata is huge, and it kind of like creates a memory pressure on the driver. And when the best case that happens is the memory pressure causes an on the driver side. But worst case, we start seeing RPC bottlenecks, and we start seeing things which don't make sense, and driver's not giving up, yet it's not really working. So we start seeing executor heartbeat failures and stuff like that. So for these reasons, we have a heavily customized fork. So we have lots of these fixes that we have applied for various different customers. We also have a mini ecosystem. Might not be a surprise to people. We have our own distributed file system, our own metastore. We have file formats, our own table format. We have our own resource manager, which is Yarn-like. So all of these integrations give us a flavor of Spark, which is heavily customized internally. I want to talk about the motivation for Veloxification. So the reason we are doing Veloxification is twofold. One is efficiency. I think this is the obvious one. Of all the experiments we have run, we have seen like a 20-25% average win. We have, of the pipelines we have onboarded so far, the win is varying all the way from 20% to 70%. And when we see something as big as 70%, it's kind of exciting and boosts our confidence in the kind of costs that we can save around here. At our fleet, which is quite big, I don't know if I can talk about numbers, but we kind of believe that we have one of the largest fleet on the planet. These savings are immense. So we are talking about hundreds of millions of dollars here, and that's the kind of money nobody wants to leave on the table. So this is kind of like the obvious reason. But if money does not excite us, there is also enablement. There are some use cases which are looking for runtime and efficiency speed up. They have the sensitive landing time requirement, so the job has to be done. Cases like model freshness. And if we can speed things up for Spark jobs, we are effectively enabling these use cases. So that's like, we have a lot of AI ML workloads recently coming in with these sensitive requirements, so we are trying to help with that. Talking of that, if we think about scalability, we can actually enable those cases using two ways. We can horizontally scale, so we can always throw money at the problem. We can say, hey, we are just going to throw a large number of executors. We don't care about the cost as much. It's okay to have somewhat higher cost, but we really want this job done in n minutes or n hours. But we start seeing bottlenecks in driver that I talked about earlier. Now, these are not completely unsolvable bottlenecks. We are talking about improvements in event bus. We are talking about efficient memory utilization of the metadata structures we have within driver. So these are solvable, and there's a set of people who's working on these horizontal scaling problems. We are specifically focusing on vertical scaling. So vertical scaling, we are trying to help use cases which don't really need 5x, 10x kind of boost. Even if they can have 20, 30, 40% speed up, they're still going to benefit. These are the use cases which are there on the fence, and a little push is going to unlock them. We're also talking about pipelines which are cascaded. So these are pipelines one after the other, and shaving off 20% from one pipeline across many pipelines is just going to give us that big boost that we're looking at. So with that, let me talk about Gluten and what it took for us to have the MVP around Gluten. As I mentioned, we have our own ecosystem. So one of the challenges for us is to get these open source technologies and make sure it's working nicely with all the integration points that we have. Right? We have our own file formats, so we had to build some integration into making Gluten aware of it. We had to do some integration with the distributed file system that we have. So integrating the access tokens, security, and remote spill support in there. One thing that we were waiting on was Spark 3.4. So we are in the middle of this migration from Spark 2.4 to 3.4. We had been using Spark 2.4 until last year. Things started changing. And last year, mid last year is when Gluten really got unlocked for us. So we had 3.4. Now we could take Gluten. Gluten has this hard dependency on 3.x because it's based off plugins which were introduced in 3.x. So last year is when we got started. So July timeframe is when we got started on this. We also have our own shuffle system, so we had to make some integrations with shuffle. We had to make Gluten aware of some of the things that were going on with our own shuffle layer. An example of this is the server-side sorting we do in shuffle. So when the reducer state starts, it already is getting the sorted stream, and there's no point having sort, but we found that Gluten wasn't aware of it, so we had to make Gluten aware of the sorting that's already happening. So this is like one of the few examples that we have had to solve. One thing we did around DevX, and I don't know, I think it's an industry problem, but kind of profound here. We have a large number of configs in Spark. We have like 2,000, 4,000 config knobs in total, and sometimes we pass these jobs around with 25 configs, and we say, hey, how do you run this job? You're like, take these 25 configs, go run the job, and people come back saying, this doesn't run. You're like, hey, did you look at that 17 config? Maybe there's a typo in that. So we wanted to be sure we're not spending time in trying to troubleshoot these issues, which take like maybe sometimes a couple of hours, and that really adds up and kills the productivity. So one thing we did early on was to invest into DevX, make sure that we have strong tooling, make sure that it was flip of a config for us. So we were able to enable this. This really boosted our experimentation velocity, and we were able to do it with ease. Lastly, I'm going to talk about the DSV2 writer, something that we had to implement. So in our 3.4 version, we have a heavy reliance on the override partitions dynamic exec. And we found this implementation was unavailable in Gluten, so we had to go implement it as part of Gluten. So we implemented that. Talking of the DSV2 writer, for people who are acquainted with override partition dynamic exec, or even if you're not, this is kind of like the high level of how it works. It has two parts to it. First off, it's not an operator, it's a command. It's a command which is going to dispatch these tasks. And effectively what we are saying is that give me the child plan RDD, and I'm going to pass you a function, and this function is going to process the rows which are created. In case of override partitions, all we have to do is write the rows. So RDD spits out the rows, and the override partition dynamic exec write to file task is going to write those rows in a file. When all these files have been written, there's some kind of commit that happens in driver, and there are multiple steps that happen in driver. We commit the files to the relevant directory. This is the partition directory which is going to be registered. Then we publish the partition. We compute the stats and publish those as part of the partition. There are things like empty bucket file creation. We also have small file compaction. So a bunch of things that happen, and there's like non-trivial complexity which happens outside of what runs on the executor side, right? So as part of our implementation, we wanted to be sure we are inheriting the logic, and the way we implemented this operator was twofold. We created the operator as part of the native plan, so it would write to files via the native plan through Velox boundary. And on the driver side, we would still have everything inherited. So any changes here, any fixes here, we don't basically have that code sync problem. We are keeping an eye on it. This is something that we want to collaborate back, contribute back to Gluten. So we are keeping an eye on it, and I think there's some development, but this is on our roadmap. Alrighty, so by this time, start of this year, we had this MVP that we had taken to multiple pipelines, and these pipelines, we are not talking about toy pipelines, but just like one stage, relatively complex, expensive, impactful pipelines. So we were able to demonstrate confidence of the MVP that we had. Now the next problem we are working on, starting 3 months back, is how do we take this, how do we deploy this at scale to all our customers? How do we do it in a non-disruptive fashion? How do we do it transparently so customers don't even know there's a migration going on, right? What we are looking at is sort of the high-level view of the migration framework that we have. So I'm going to read this from the bottom right. There's a Spark driver, which is trying to make an admission decision. So this driver wants to make a decision on whether this app should be running native or vanilla. It's going to need some kind of persistent state lookup. So we have a database maintained, which is going to have some kind of migration state. So every pipeline is going to hop these states, depending on the testing we have done before. Driver is going to make this lookup decision of the pipeline, and it's going to see, oh, this pipeline is blessed for migration. I'm going to proceed. There are more fallbacks which are implemented as part of driver. And one reason to implement admission logic in driver is because we have a lot of context. So we have context of flattened configs. We have context of runtime. The driver can go look up the history of the job to see if there have been failures, if the failures have been introduced by migration. It can see if there has been a cost regression. So out of being defensive, we take a lot of rules into account when we are doing enablement. And admission logic is only going to admit when everything looks fine. So working backwards, how did a pipeline get to the migration state? How did we bless the pipeline? There, of course, has to be a rigorous amount of testing that goes in. So as part of our testing, we have this A/B testing framework, which is going to fire off one run with vanilla, that's the control run, and it's going to fire off another run with native. And then we are going to fire more jobs to compute the hashes of these output tables. And we compare the hashes. Everything looks good across a couple of runs. We declare it a win. This is good to proceed. I'm abstracting this a little bit. There are a lot more checks with respect to number of containers, kind of task failures. If everything looks at par between the two runs, we are going to make this happen. Now, there's a problem with capacity. The problem with capacity is at our scale, there's only a limited fraction that we have, right? So how do we make sure that we are not shooting in the dark with respect to testing? And how are we making sure what we test has a high conversion possibility? We don't want to be in the business where we take all these pipelines, just throw and hope something comes out of it and try it over and over again and see that we are not really getting conversion. So we want to try and get to the plans which are within reach. which brings us to the shadow planning rollout that we did. So as part of shadow planning, what we did was across our fleet, we deployed this. We deployed gluten-only planning. On the left is how the run looks like. So in vanilla, we are going to go through analysis, optimization, planning, and finally, we are going to submit to DAX scheduler. There's, of course, the AQ complexity. We're going to do it stage by stage. But if we abstract that out, we are effectively doing the same with a Spark session, which is running with gluten enabled. So this Spark session is a clone session. It's working in the background. We are not blocking the main thread. We are not introducing any latency challenge. And we are collecting all the fallback information as part of the planning itself. So right now, we have our production data sets, which are fully decorated with the fallback information, giving us a sense of prioritization, giving us a sense of score, giving us a sense of confidence that if we take these pipelines which don't have any fallbacks, there's a high likelihood that we would be able to onboard them. So as part of this, this is what we found. The data set that we have decorated, about a fourth of that data set has seen no fallback. So this is a fully nativizable plan. This makes us confident. This makes us very positive of some amount of footprint that we can cover without really running into conversion penalties. And some talks have talked about row to columnar and columnar to row steps that are injected whenever there are fallbacks. Our goal is not to run with hybrid plans. We are going to try and run everything native. So our push is to try and get to fully native plans as much as possible. The 47% share is coming from Java UDFs. So we have seen that Java UDFs come in the way. They are the sole blockers. What I mean to say is that if we can solve those Java UDFs, if we can migrate those as native UDFs, we would be able to fully nativize the plan. So we are not going to have that conversion penalty just because one of the project using scalar UDF is not compatible. So with these two, we would be able to cover 75% of the SQL workload. Lastly, 27% is coming from a flavor of UDFs we have where we are running these script transforms. These are like script and sidecars which are running out of band. This is not something we're tackling right away in the next 2 months, but this is something that we have plans for. We are looking at different approaches. At the end of the day, these transforms, these are like C++ transforms which adhere to some interface, and the task is to kind of like build an adapter so they can adhere to the Velox UDF and kind of like do some adaptation over there. All right, next big challenge. So we are basing our migration on the fact that we are going to have fully native plans, but is that sufficient? The other big challenge is that of memory and tuning. We can, of course, take a pipeline. We can migrate it, and we can try running it with gluten, but it's not necessary that it's going to run reliably. It's not necessary that it's going to provide the efficiency and the wins that we are thinking of. There is some kind of memory tuning that has to happen based on the fact that we are switching the eval from something which is heap hungry to something which is completely off heap. So we have to make that adjustment somewhere. What we are looking at is the existing memory tuning framework. This is how we do the memory tuning around here at Meta. So we have a mix of user configs, history, and a new kit on the block which has been implemented recently. We internally call it memspec. It's a plan estimator. Think of it like a visitor which is going to walk down the plan tree asking every node what the requirements are, and then do it at the stage boundary, finding out the max of all the different memory knobs and that we have to configure. So different kind of, there are like 5 or 6 different kind of memory configs. Heap and off heap are the most interesting ones, but then we have sidecar processes, we have Python UDFs, we have netty memory, and all of that combined gives us the container size. So in the end, when we are asking for containers from the scheduler, our equation kind of takes all of these memory configs into account and asks for a container. So for us, most of the problem gets simplified if we can have the adjustment between heap and off heap. And if we can work with the constraints that our total heap plus off heap is going to be constant, we can say with some confidence that our container size is going to be similar. So that's the amount of memory we are hogging on our clusters. And if we can hog that amount of memory for a lesser amount of time, we are effectively improving the cost. And this kind of aligns with all the experimentation we have done so far. So the work we had to do here was to make our plan estimate logic aware of the native operators. There was some complexity related to AQE, might be too much in the details, but our plan estimator is tuned to look through the AQE plan using AQE helpers. But the way Gluten operates, it operates at the the preparations level, and it comes in as and when stages are getting progressed through AQE. So sometimes you would see the plan where the leaf stages have been nativized, but the subsequent stages haven't really been nativized, and that's because they're just waiting for AQE to kick in. All right, so in terms of top blockers, Java UDF is something I already talked about. This is the top blocker. We already have a migration plan for this. We have a flash talk later today where we talk about how we are using AI to accelerate the migration of these Java UDFs. Our strategy is to nativize all these Java UDFs and make sure we don't have any fallbacks. Script transformation, I talked about the adapter approach that we are taking. And last not the least, I'm going to talk about this scan-only mode, which people who are working in Gluten might have some acquaintance with. This mode in Gluten just nativizes the scan operator. And given that most of the scans are columnar anyway, there is a columnar to row conversion happening no matter what. So there's no regression with respect to conversion happening. For us, this is an attractive option because even if we are not saving cost around here, we are still working towards the goal of stack consolidation with respect to redos. We are a complex stack. Most of the meta is C++. We have moving data infra slowly towards C++. Spark is sort of like the long pole to it. So we have these Java redos, and they come in the way of deprecation. So what we are trying to do is we are trying to have the scan-only mode where we are able to move away from these Java redos and have native redos. So this option is coming in handy. It's going to come in for workloads which we would not be able to fully nativize, but knowing that something exists in a toolbox is kind of good and makes us confident. All right, let me quickly talk about the Gluten improvements that we have made. So first one is around the driver memory. When we started off with experimentations, we found that driver was actually bloated. In some cases, it was taking like 34 gigs as opposed to 12 gigs in vanilla. We found that there was an inefficiency in the Gluten partition. So in terms of split generation, we are going to have these split objects and partition objects, as we call them in Spark lingo. And they have file metadata within. So there were two things going on over here. One is that we were not keeping the heap structures, which could be cross-referenced, having single graph, which is accounting for the memory. We were keeping serialized structures. So they were duplicated across the partitions, and that was spiking driver memory. The other one was around a large number of partitions and a large number of files creating large amount of metadata. So these partitions, if you peek inside, if you look at the file paths, these are relatively long file paths, and they are really redundant. It's only the file name that changes. So we implemented this mini encoding, which is going to pull the prefix, store it once per split, and not at a file level. And given that these splits can have hundreds of files within, we end up saving like 100x right over there. So this kind of helps with those drivers which are overshooting memory. DSV2 writer is something I already talked about. I'll just breeze through it. AQE plan splitting was something unique, which was happening for our DSV2 writers. So we noticed that the AQE plan node was coming in between and creating a fragmentation issue between the plans. So we would see that the native plans, there were two separate native plans getting invoked as opposed to one plan. So given AQE is kind of vestigial at this point, you're running the final stage and there's no other optimization that's going to happen. We implemented logic to kind of like throw away and make one single native plan. IO subsplits is an interesting one. With IO subsplits, we noticed that Spark would produce these splits. In some cases, these files were in gigs. And we would notice that we would have IO prefetch, and then followed by compute, and this was interleaved. So compute would actually wait on I/O, and Velox has this notion of subsplitting and prefetching, in which if you can provide it splits upfront, and if we can just break down that file into subsplits to Velox, it pipelines them and makes sure that the compute thread is not waiting. So we have a separate I/O worker thread, and we have a compute thread, and I/O worker thread keeps the compute thread busy every time. We notice like a 10 to 15% improvement with this. Finally, I want to talk about the AI boost. Got a minute, so I'll quickly breeze over this. In terms of development boost, the migration framework I talked about in the olden days would have taken like 1.5, 2 months. We were able to deliver it in a week or so. There's a table format implementation we had to do. It would also take like 2 to 3 weeks. We were able to deliver it in 2 to 3 days. So it's definitely speeding up the project in terms of features that we are delivering. But also our whole migration loop has been accelerated from this. So at this point, we have multiple skills which are assisting all the human loops that we have. So when humans had to sit on the edges and find out why the jobs are regressing, or why we have hash mismatches across these tables and figure out what is causing data corruption, now we have AI which is kind of helping with that. So we have a bunch of skills. We are trying to get to a point where human is not working with the skills, but we are kind of like inverting this and have like automation and skill, and pushing humans on the side, involving us only when it's really necessary for issues which are going to need issues like hash mismatches. There's an example we saw where broadcast hash journal was producing 0 rows. So something which really needs human intervention is where we want to keep ourselves. Otherwise, we're trying to automate the hell out of this. Cool. That's it from me. Thank you for listening. I'm going to be around. If you have any questions, we would love to talk about this. Thank you.
Hi everyone, I'm Abdullah here with Vishal. We work on AI data infrastructure, and today we will talk about Zephyr on Velox, a query layer we built to power agent memory, graph rag, and hybrid retrieval use cases. As far as we know, this is the first system that repurposes Velox for federated query execution. Here's how the next 15 minutes flow. I will take the query layer and architecture. Vishal will talk about the graph rag and agent memory and their use cases. Three distinct AI workloads you see here, and not one of them has a database that fully answers the query shape they need. Agents and co-pilots need memory that outlines a single session and can be joined with structured context, not just similar text. Knowledge graphs these days routinely run into billions of nodes, and traversal still has to stay cheap at that scale. Graph rag and hybrid retrieval pipelines are drowning in glue code. The query shape should be expressible natively, not stitched together by hand across three systems. And you see like a same missing primitive across all three, and it breaks down into 4 retrieval needs. Here are the retrieval needs, each with the store it lives in today, and that what that store is missing. Vector DBs, for example, are fast at semantic recall, but they cannot walk a relationship. Graph DBs are great at traversal, but their vector support is weak. Analytics engines handle structured reasoning well, but offline in batch, they are not serving latency. Relational DBs handles exec filters and joins over structural fields cleanly, but only as a post filter on results from another store. That wastes the retrieval work you already paid for. So there is no single store that does all 4. So we built one query layer that does. Zephyr says what you want. Axiom figures out how, and Velox makes it fast. So what's Zephyr? Zephyr is the de facto query language for graphs nowadays in the industry, and ISO GQL, the first international graph query standard, is built on it. The model is simple. You draw the pattern, and the engine finds the subgraphs. If you look at the query example, this single query does semantic similarity, finds the shortest path, and ranks by both. So overall, 1 pattern, 3 retrieval modes you see in a single query. And it's everywhere, in cloud graph DBs, embedded ones, and every major AI framework. Wherever graph data lives, Zephyr is the common dialect. So Zephyr already won the language layer for us. The next question we needed to answer was how to execute it at meta scale. And over storage we don't own. So this is the resulted architecture we come up with. And as you see, Zephyr comes in through multi-language clients for reads and writes. Antler grammar parses it into abstract syntax tree. Next comes the extensibility layer that exposes graph algorithms, vector search, temporal queries, and hybrid scans as procedures. So all of them compose into a single plan. Plan translation lowers the logical plan with graph patterns written as joins and hands it to Axiom. Meta's cost-based optimizer for Velox we use for join reordering, predicate pushdown, and cardinality-based planning. The physical plan runs on Velox, and at these we have pluggable connectors, reaching graph stores, knowledge graphs, relational and vector indexes. Spanning every layer, you see like our platform services like schema, lifecycle, caching, and observability. Privacy is also enforced at the plan layer. Policies compile into plan predicates, so they can't be rewritten around. So Velox didn't need to become a graph engine to solve our problems. the graph layer compiles down to Velox. And why Velox? 4 reasons Velox was the right framework for us. Yeah, first, vectorized execution. Velox is columnar and sim-friendly. So graph rows reuse the same analytics operators at runtime. We get a throughput for free. Second, plan infrastructure. Joins, filters, aggregations. Every graph pattern we care about is already a Velox operator. We didn't add new ones. And third, federation through the connector model. Pluggable storage, any backend behind one plan. We don't own the data and we don't want to. And fourth is like the memory and resource management, like pool spilling, back pressure, which are better tested at meta-scale. We didn't want to really rebuild. So yeah, 4 wins from Velox, and not one required a fork. That was the key for us. You see supported backends in different categories. So same query language, same plans, whether we are hitting a billion node, billion user graph in production, or SQLite file on agent's laptop. And second layer, like Prism and Hive handle analytical and bulk graphs. XDB, MySQL give us native vector on SQL on relational DB. And graph and vector co-located in one query, no federation needed. And for embedded, SQLite for 0 infra agents, and for prototypes, PhaseDB for hybrid vector, text, and recency search. Adding a new backend is mostly an interface implementation now for us, no engine fork required. That's the query layer story. I will hand it over to Vishal, who will walk you through how this powers GraphRack and agent memory use cases.
Okay, thank you, Abdullah. Hey, everyone, I'm Vishal. In the first half, Abdullah showed you what Cypher is and how we built on Velox. So next, I'll talk about 2 problem domains that are essential for AI systems, and we'll look at how these are applicable over there. So let's start with GraphRack. I'm sure you've all heard of RAG, right? Retrieval Augmented Generation. It's basically a way to ground LLM responses in real data at query time. Now, the problem with RAG is that it treats docs as just isolated chunks. It knows what is similar, but it doesn't know what is connected. This is where GraphRack comes in, right? So GraphRack can traverse relationships and help you answer questions like, who owns the services that were involved in this incident, right? So it can track the owners that way. So GraphRack solves that by adding a graph structure on top of different data that is semantic, you have semantic understanding about, right? And this is where Cypher comes in, because Cypher that we built on Velox lets you express graph plus vector in one query without additional glue code required. So we see like recurring patterns in GraphRack, right? There are multiple use cases. There are some graph native patterns. There are hybrid patterns, right? In graph native patterns, we can talk about multi-hop retrieval. So you can ask questions like find postmortems about services that depend on platform X, right? There are other graph patterns that can span into service intelligence, explainability, and there are other hybrid patterns that show up like when you require constraint-aware filtering, you require signal re-ranking or personalization. So all of these patterns require a similar query shape to recall semantically, walk relationships, and filter by constraints and then rank them. Okay, so one way to think about these patterns is find, traverse, and expand, right? And this is where Cypher can help you think like this. So when you're doing a find, you're doing a precise multi-signal retrieval. So when you ask questions like which services are mentioned in this auth failure incident, so you're going in with a semantic understanding of what that auth failure means. It could be login, it could be some other semantic term that's used. So this is going into vector search. It's doing a text search plus vector search, but it can also have a recency factor into it to boost the ranking. Next, you can traverse and you can add, you can traverse a relationship and add to that question to say who owns these services, right? So that's a 2-hop traversal on top of your semantic search, which is document, to service entity to the owning team. And you can continue to expand it further to ask broad questions, which involve multi-hop neighborhood discovery. So you can ask it questions like, a Ceph fired, what's the blast radius, right? Okay, so that was GraphRag. Another problem domain that has emerged is agent memory, right? It's the persistent memory that enables agents' intelligence. So the expectation that you have from agent when you're interacting with it is that gives you session continuity. It has access to a knowledge graph that it can access while talking to you, and it has adaptive learning. So as you interact with the agent more, it produces even better interactions, right? So when an agent operates for hours, days, or weeks, it's building that personal experience, and to query that personal experience is where agent memory comes in, and that's where Cypher can be used. So here are these like 4 types of agents that we've all been using, right? There are coding agents that are IDE assistants. They're performing coding tasks. They're enabling code review boards. There are knowledge brains that you can talk to, discuss. When you're brainstorming on certain problems or doing some designing, you can work with these knowledge brains. There are team knowledge bases that are showing up as agents, right, which can have access to team docs, wikis. It can organize chats. It can also, to some extent, manage team's execution, right? And then there are these long-running agent loops. So agents that are used for specific problems like operations, support. It can also make some autonomous decisions independently, right? Like to respond to like customer queries or do some mitigations for incidents and things like that. So again, over here, you'll see the similar pattern emerges where you can recall semantically, walk through relationships, and then get the time and ranking into consideration. Okay, so how Cypher helps, like we saw with GraphRag, right? There is a problem with flat memory. Vector can only retrieve similar experiences, but it doesn't understand what is connected. So there's no causal chain. So if you ask questions like what happened the last time, it doesn't know like what caused the last time, right? So it doesn't know like what is happening and how that's connected to the overall knowledge base. So agent memory also needs these combined signals: vector, text, recency, and edges. This is what Cypher on Velox enables. It unifies all signals into one comprehensive query plan with streamlined execution. And then again, in agent memory, I'd encourage you to think of building your queries like this: find, traverse, and expand. For find, you can ask questions like, user mentioned login problem. What did we discuss, right? So if you look at the query over here, we do a call into DB index vector search, and then you can have some filters specified, yield certain fields, and then you can order by, right? Now you can build on top of it to say, what caused the deployment failure that we debugged? So it can do a search, a semantic search, but it can also do a match and walk through dependencies or relationships. And then expand is, again, where you can ask broader questions, like walk me through the SEV that happened last week, right? So vector finds a starting event, and then you can expand with the edges. Okay, so what's next for us? We're continuing to develop this. We're improving our graph support, adding support for more algorithms. We're doing vector search enhancements, tighter integration, and enabling hybrid retrieval. We're working on query optimization and support for more backends to expand our reach. And we're also considering making our work on Cypher on Velox open source so we can encourage more community contribution. Okay, so to recap, we looked at what Cypher is, how we built it on Velox. We looked at 2 problem domains, agent memory and GraphRag, and then similar patterns across these: find, traverse, expand, and how we can write queries across these. So Abdullah and I will be right here, happy to hear what you guys are building. If you have any questions, happy to answer. And thank you so much for your time.
Okay. Hi, everyone. Good afternoon. My name is Yuan. I'm an engineering manager from IBM. So thanks a lot for the Velox community. It's glad to be here and to meet some old friends. It's really a great event, and I really enjoyed it. So for the agenda today, first, I will introduce the key features and we implemented in the past year for Gluten. And then I will introduce some details for some of the key features we introduced last year. And then I will do a short introduction on the IBM Watsonx Data Spark. And then I will introduce the performance optimizations we have done in the past several months. In general, we get almost 2x performance since last year. And then there's a summary. All right, this is a picture for the Gluten team in IBM. So most of us are based in Ireland, and some of us are in the States, and there are also some new guys from India. And by the way, some of the team members are in this event. So if you have any questions, to reach out to them. And yeah, I'm really proud to be one of the team members here. So in general, we have 7 committers and PMC of Gluten, and we also have 3 Velox committer and maintainers already. And IBM is 100% supporting on open source projects. Yeah, so this is a journey for the Gluten project. So it's been like 5 years, 6 years. So it starts from a very, very small POC in 2019. And then we made some homemade engines based on Arrow and again Niva. And then we realized the performance and the functionality is not so good. And then we found the Velox project. And glad we found Velox project since then. And we start to implement the necessary functions and the gaps with the Velox backend. We introduced the many functions, many operators, and gradually we came to this way. And in March 2026, so Gluten is finally graduated from the Apache incubation project. So it's a top level project right now. Yeah, it's all credits goes to the Gluten and Velox community. So I want to say a big thanks for the community. Here's a picture for the roughly 200 contributors in the Gluten project, expanding from almost 30 companies. Yeah, it's a big thank you to all contributors and also the Velox community. So here's our key goals in 2026. So in 2025, we actually implement several important features, including the performance improvement on Shuffle on BHA, and also the Spark 4.0 support, and data lake, and also GPU support. Those are actually already done in 2025. So in 2026, we are continuing the efforts. In general, we are introducing better support for the semi-structured data, including CSV, JSON, text, and we will continue to do the performance optimizations. And then, which I will introduce in later slides. And then we were expanding the platform support, including so x86 and ARM are already supported. We are adding the GPU support and also expanding the support to IBM Power and IBM System Z. And we are enhancing those nightly releases by enhancing those CI/CD pipelines. And we are adding the tuning recipes. In general, we are introducing some tuning method for including I/O, including memory, and some basic performance tunings. And more than that, we are adding the Spark 0-day support. So we are trying to add the Spark main branch support in our Gluten repo. Basically, we have a nightly job that pulls the main branch code of Spark, and then we were integrating into Gluten. And then we were, of course, another big goal for us is to grow the community. So this is Velox integrations we have done. It is quite very detailed here. So Velox primarily is is designed for the Presto project, and for Spark, there are some gaps we found, including the operators. For example, there's some different implementation on the expand node support. And then we also found some join types mismatching with Presto. We added all of those operators support, and then we found the in the Parquet or org support level, we also found some important gaps. For example, the timestamp support is kind of different in Presto and in Spark. So we implement all of those gaps, and also the function. So in general, Spark has like more than 300 functions, and almost all of those functions has different semantics in Spark and in Presto. It is very, very difficult for us to like close all of those semantic gaps. So it is actually a long tail task, and thanks to the Gluten community, like we just list all of those functions in the community, and then there are many contributors start to pick up all those tasks, and then gradually we contribute to the Velox side. Until now, we roughly completed the 260 functions, which already covers the majority usage in production environment. That's a very, very big achievement for us. And also on the performance and stability side, we are continuing our efforts on that. So it is still due to the different implementations between Spark and Presto. So naturally, we need to do more things than for the Spark design here. So yeah, this is very informative slides. So here's a challenge we run into basically almost in almost every functions, every operators. So we did those, but till now we still have some results mismatching issues. We're calling for help on those issues. For all of those issues, we have already feedback to the community, Velox community, and we are now co-work with the Velox community to close all of those issues. All right, for next, I will introduce several key features we have implemented in the 2025 and 2026. So the first one is, we have a new design on the GPU support. So we do have the full offload GPU support already, which thanks to the Velox community and the NVIDIA friends. But in Gluten, we are trying to do something a little different. So we are trying to introduce a concept called adaptive hybrid execution. For example, we are only offloading those compute-intensive stages into GPU, but for those IO-intensive stages, like loading the table from S3 or GCS, then we just leave CPU on it. So in this way, we can like utilize the GPU more efficiently and reduce the cost from the big picture level. So we have a POC ready now, and the POC results is very promising. It should like roughly 2.5x performance improvements, while we achieved 60% cost reductions. The second one is from the hardware support. So again, thanks to the Velox community, so there's already some platforms is already working. For example, the x86 and ARM are already working, and GPU is in progress. But there are also some other platforms we are working on. For example, the FPGA and Power and the System Z. So IBM is contributing on the Power and System Z support, and I do know some engineers from China. They are working on the local ARM CPU support. So this is a great complement for the community. We could actually attract more developers and more interest on Gluten project. Yeah, the third feature for us is we are adding the 0-day support for Spark release. So initially we only support Spark 3.x release only. And in the beginning of 2026, we are adding Spark 4 for support. Right now, we do support 4.0 and 4.1, but that's still like behind the Spark community. And in this year, the Spark community actually is trying to introduce a very aggressive releasing method. They're doing releasing every quarter. So to work with this, we are adding the Spark main branch support. So we are pulling their code from the main branch and then do the build at nightly. So in this case, if there's a new release from Spark, we could actually align with them and cut the branch in Gluten. Then naturally we will have the corresponding release for the related Spark release. Yeah, the fourth feature is we are adding more backend support. So initially, we are focusing on the Spark SQL mostly, and currently we do see some efforts from the community that tries to expand the support to different engines. For example, the Flink and Kafka engines are already there, although it is still in the very initial stage. But it's good to see Gluten like start to move into different workloads. Yeah, the next one is for the Gluten UDF code gem. So when we try to do POC or enable in custom environments, we found that the key performance limitation for Gluten is actually on the Java UDF. So usually in the user environment, they have some legacy UDFs either from Hive or from Scala, from Java UDF. We introduced the partial project feature, which actually can extract the UDFs, and then you can actually do project those supported expressions with native functions and only do the fallback for that specific UDF. But that can help, but that does not fix the issue entirely. So we are now leveraging ARMs to convert the UDF into C++ code, and then build that into a dynamic library, and then load into Velox. Yeah, I think our friends at Meta also have a session on that. They may have more experience to share there. So, but based on our early results, we are seeing very productive. This is very productive for us now. Yeah, last feature is we are doing the broadcast hash join optimization in Gluten. So initially we are reusing the shuffled hash join code path in Velox, which actually will build the table for each thread, which is a big waste on the CPU as well as the memory. So in the latest release of Gluten, we are adding those optimizations on the broadcast hash join. So instead of building the broadcast hash table for each thread, we will build that table for only once inside the executor, and then the executor will share that build map, hash map, and then reuse it, so that the memory footprint is reduced. Yep. So the next one is native lakehouse support in Gluten. So Gluten has inherited from the Spark design of data lake. So in Spark, they do have a very unified design for different data lakes like Iceberg, Delta, and Hoodie. And Gluten actually can inherit from that, and we do have a chance to unify design for all of those data lakes, because we only need to implement the APIs that Spark provides. So in this picture, we showed that the approach we are using. So we kind of reuse all of those control plane. So the metadata plane is not changed at all. Instead, we are just hooking on the data plane. For example, for the write code path, we are just do a hook, then offload the write to Velox write. Then we can support those data lakes very, very easily. Until now, we have Iceberg and Delta supported already, and now we are working on the Hoodie and Pymon support. In our early results, we do see like up to 4x performance gain on the write-intensive workloads. Okay, so for next, I will introduce a bit on the IBM Spark. So IBM Watson Zeta is part of IBM Cloud. On the left, it describes the technical foundations of the components. It does provide many features already, so including Presto, Spark, Mivos, and data stacks. It also supports all of those open source data formats like Parquet, Org, and yeah, many of them are supported already. So Spark in IBM software portfolio. So IBM actually was one of the first companies that offer Spark as a service. That was back in 2014. And then in 2015, IBM established the Spark Technology Center, which I guess most of you guys should have heard of this before. And now IBM is expanding. We are moving the expanding to the native engine support in Spark, which is a Gluten team. Okay, so here's a performance improvement we are doing mostly this year. So the diagram is basically describing a stack that the upper layer is from the client. We do have SQL clients. We do have data frame clients. And then in the middle, there's first we will need to optimize for the Spark optimizer. And then in the middle, we have Gluten and Velox. And then when it goes to the I/O, we do have the local caching feature. And then we do have the support for Delta Lake and Iceberg. And underneath, it is using the object storage like S3 or GCS ABFS. So to improve the performance of the workload, we actually need to inspect each layer of this stack. And yeah, one of the interesting things, if you, for example, we need to fix the S3 reading performance first. And then after fixing that, you may notice there's a new bottleneck coming up on the different layers. Yeah, and then here's a picture for our performance improvement in the past several months. So back to November 2025. So roughly we benchmarked the TPC-DS 10 terabytes performance with all of those default parameters, and since then we start to optimize those with the methodology I just described. We did many optimizations, like roughly 10, 15 optimizations there. And in the past quarter, we are doing very good progress. As you can see in the picture, so we almost achieved 2.3x performance improvement in the past quarter. This is a very big achievement for us. And actually, we are actively upstreaming those optimizations, but some of the optimizations are not upstreaming yet. So yeah, feel free to approach us for more details. And then here's another picture for the benefits we observed from the custom workload. In this picture, so in the left, it's the default Java Spark performance. And then we introduced several optimizations, including offload the scan only option. And then we did many improvements on the table scan side, including the row group skip and split prefetching. And with all of those optimizations applied, we have seen almost 7x performance. And the customers are really happy about this. And then the last one is for the GPU work we are working on. So instead of offloading all of those operators into GPU, we found that in Spark workload, it is typically introducing very, very big data set. The data set is too big so that it cannot fit into the GPU memory entirely. So we kind of introduce a different mechanism to it. We are trying to introduce a new concept called adaptive hybrid execution. So basically, we leave those IO-intensive stages into CPU, and then we offload those compute-intensive stages onto GPU. And in 2025, we did a quick POC with single node based. That is a collaboration work with NVIDIA team. So we found that, like in the left picture, so for the first stage, we are still using the CPU as the execution. So we found the performance is almost similar with the original CPU-based execution. And then we offload the second stage, which is a very compute-extensive stage. It's a second stage from Q95. And it involves the very heavy hash aggregation, hash join. And then we found if we offload that stage to GPU, and then we can achieve very, very good results there. So with this POC in 25, so we are very confident. We have more confidence on this approach. So in 2026, we are now expanding this to multiple nodes. So in this year, we are adding more features to allow the POC to run on multiple nodes. Basically, it actually reduces the resource profiling feature and AQE, adaptive query execution feature in Spark. So we introduced a second resource profile, which is the GPU-based profile, and then in the AQE framework, we kind of inject our cost-based optimization there. We found if we found it is a very compute-intensive stage, then we will offload that stage into the GPU executor. So the patches are still under review in the Gluten community, but we do see very good results in our POC. So we made some POC with 3-node based environment, basically 2 CPU nodes plus 1 GPU nodes. And then we see roughly 2.4x performance improvement. And of course, with up to 67% cost reduction. Yeah, this is a very, very good achievement for us. Okay, so the last page is on the Gluten velocity, adoption velocity here. So we are actually collecting the production stories in Gluten community. Here's a picture for the adoptions. I actually removed some of the adoptions earlier than 2024. So starting from 2024, you can see the icon may be a little small here. So we have some early adoptions in 2024. In 2025, we have five more landing stories there. In 2026, we have roughly 6, 7 now. So it is still in the beginning of the 2026. So I expect there will be more landings in 2026. So this is a very inspiring story for us. And, I have also listed the Power by page in the Gluten community here. Okay, so just to do a quick summary. So Gluten provides very strong Spark coverage and performance, and the community is growing rapidly In March 2026, we achieved the top-level project status. IBM is improving Gluten with various components and the performance side. We worked closely with the Velox community to add the support for the Spark usage, almost covering every component in Velox. And yeah, Gluten Velox already showed very good performance in real production environments. In 2026, we will continue the efforts and then improving on those areas. Yeah, I think that's all the contents here. So some of the tech leads and team members of Gluten is here. So if you have any questions, feel free to reach out to us, and then we're happy to answer those questions. Thank you.
Just a reminder, if you are leaving and you are not a Meta employee, to please find a Meta employee. They should all be out there to escort you out. Thanks.
All right, folks. I'm Chandrasekhar Singh, and today we will be talking about journey of Presto on Spark on Velox stack at Meta. So in this talk, we will be talking about Presto on Spark, its use cases, where it fits in the wider Meta batch ecosystem, and some of the important features we use, and dive into the motivation on why we have been working on the Velox integration, where we stand in our journey. And finally, I will be ending the note with some of the numbers from production and how it has been changing the landscape of running the batch workload at a scale. So where does it fit? So in a nutshell, Presto on Spark in general steps in where a query simply becomes too big for our typical regular Presto deployment. For example, they start hitting into local memory limit at the worker level, or the distributed cluster-wide limit, or they just need access to thousands of executors in order to finish in a reasonable time. Or basically, this query has simply too many stages, which is a risk when you are running on a regular cluster, because query is going to fail or start impacting other queries running on that cluster. Another class of workload is long-running queries. They are more prone to the failures because your worker nodes can go out of the cluster for maintenance or other events, or they can simply fail. And because there is no fault tolerance in the Presto stack, it basically means you lose on the progress and the compute, as well as it delays the completion time. So this is pretty expensive, specifically for the long-running queries. So in Meta, if we have to look at it, any queries which is basically more than 3 hours in duration, the usual home for those kind of queries is Presto and Spark. We do have smaller running queries as well, but that typically falls into the earlier categories that I talked about. So at a high level, it is a Presto cluster running with Spark runtime. So Presto and Spark is basically where you have the runtime benefits of the Spark, but for parsing optimization planner or for the evaluation specifically, eval layer, you have the Presto code. So it's a custom Spark app which runs on a Spark cluster. So in the Spark driver, you'll see that we have all the Presto bits, and basically once we have the final Presto fragmented plan, we create a DAG of RDDs, and from that we hand it over to Spark's scheduler to take it for the runtime. And from there, Spark scheduler takes care of all the resource allocation, task scheduling, retries, task level or stage level, and so on. And once a task lands on the executor, as part of task execution, same Presto eval is used to run the fragmented plan and return back the results, or write it to the persisted shuffle. So some of the notable features that basically makes this stack reliable and the addition in the Presto is task and stage level retries that basically comes from Spark. In addition to that, we have built smarter retries, and these are part of the Presto code base and part of the custom Spark app that runs on Spark runtime. So for example, when you have the broadcast table becoming too big, and when it is possible, we can enable partition join. That automatically kicks in, or basically run with higher hash partition count so that the amount of data you process at each node becomes smaller. Similarly, containers with increased memory is another thing which basically throws in jumbo container, we call it, which are like massive containers, so that the task can go to completion. In some cases, it's not simply possible to disable the broadcast because you need broadcast to do some of the joins. Next is we built the AQE framework in Presto similar to Spark because, since this is a custom app, Spark AQE doesn't fit in here. The framework is there. We implemented join swapping, which does the runtime join swapping based on the intermediate stages stats. For broadcast, we use file-based broadcast because it allows us to do multi-GB broadcast rather than being limited by a few hundred MB, which is more realistic if you are collecting the data back on driver and trying to broadcast it over to workers. Then HBO is another standard feature which pretty heavily used. And then on top of the stack, we have dynamic routing of queries. This is one of the pretty critical features, as well as from user perspective, it's basically what? When a query grows bigger, how do you know? You don't know. You basically want that when a query grows bigger, it fails, it runs into memory issue, and so on. That query automatically gets routed to Presto and Spark. For a user, it's basically the query has been running and it's going to continue to run, and they will keep getting the result back. But this seamless movement of query, the whole reason Presto and Spark exists, rather than user being prompted to rewrite their production running queries suddenly one night when it is too big to fit in Presto, that's the use case. And dynamic routing of queries actually helps there. Moving on, let's talk about motivation and Velox integration. I mean, on motivation, well, it's Velox. So, I mean, last 2 days we spent talking about why and how Velox has been helping. So, when we are running batch pipelines at our scale, and Ankur also briefly talked about it, the efficiency gains translate into massive infrastructure cost. The reliability pays into some of the critical pipelines where you have the monetization pipelines or AIML pipelines basically completing on time. This is very important. So Velox integration, I mean, we have seen with Prestissimo that there has been more than 2x efficiency, 4 to 6x latency gains, and on the that's the efficiency angle. On the reliability front, we all have faced long GC pauses, worker ohms, and pretty loose memory accounting with Presto Java stack. With Velox memory management and faster execution time, we have seen dramatic reduction in the query failure rate, which the numbers I will be going with in later slides. Coming to maintenance and operations, if you look at it as part of the Presto batch ecosystem, it's pretty involved, hard, cost consuming in terms of infra and people to run 2 stacks, basically maintain a Java eval stack as well as C++, keep the feature sets similar, which is quickly diverging, as well as basically certifying every releases every week and making it to production. And in production, you try to reason through, oh, if there is a query showing different output, is it because the regex behavior is different, and so on. And it breaks the seamless movement of queries between Presto and Spark and Presto, which was the whole premise why Presto and Spark was created. So another thing is this overhead just not stands with the Presto team. It spills over to other team where other teams like storage, IO, Metastore, they have to maintain and support client APIs for Java. So that's the whole motivation front. At a high level, everything remains same. Bigger blocks. One thing that changes that once a plant fragment lands on the Spark executor, on the JVM side, we spin up a sidecar if it's not already started on that executor. And over HTTP, we communicate with that, and we send the plant fragment. The plant fragment is translated into Velox plan, and then all the heavy lifting is done in native worker. So if you look at it, native worker directly talks to Hive storage to read and write the tables, shuffle service, which is our Costco, to read and write shuffle data, and distributed file system, which is used for spilling as well as writing the broadcast files. The communication between JVM and native worker on the executor side, this is over HTTP, and it's all metadata and stats which are mostly flowing, getting transmitted over the wire, so not over the wire, on the same host. So there is no data exchange there, so it keeps it lightweight and more reliable on that front. So some of the notable additions or what it took to make it possible. We rebuilt file-based broadcast for native worker because the worker is now Velox, so we had to rebuild it in the native stack, where basically the native workers directly read and write to the file system for the tables which are required for the broadcast. The shuffle integration was another piece which we had to do. I mean, this simply meant that we adding new operators for these new integration points, as well as making sure that those operators have the plan translation from Presto's physical plan to Velox plan. Given that native workers as well as Velox comes with a bunch of additional configs and so on, we had to build a framework to do the wiring for the config for all the way from our config store to drivers and all the way going to the native workers. One important addition was shorted shuffle and short merge join, which was built for sequence storage use case. That's something we didn't have in Sapphire Java, and this has been unblocking a lot of new use cases on the stack. And the memory management integration for the new operators or wherever have been missing to make the stack more reliable. So going into part 2 production, what it took to take new stack to production. So correctness has been our P0. One thing we basically focused on, and initially, I mean, last August, we decided that we need to have a zero correctness issue for a sustained period of time before we can take this stack to production. I mean, once you have the correctness sorted out, you can always pick and choose which queries to promote to production. I mean, you can always go and say, you know what, I'm seeing 40% of the queries which are showing 3x gain, and those are the ones we are going to promote. And basically, you are like, okay, there is not going to be any correctness issues. So, and then in parallel, we focus on the improvement, missing features, or regression. Given Prestissimo has been already running like more than 90% of production workload at that point of time, our expectation was there should not be major correctness issue, and specifically given that it's the queries have been moving between these two systems. So we took the approach to replay and verify all the production queries continuously every day. The biggest challenge was, okay, how do we make sure at this scale we can replay the query? I mean, it's simply not feasible to have additional infra which is continuously replaying production query. So we started with deduplication of query shape. So basically, let's say if I have a daily pipeline, you pick only one instance of it rather than running all the 24 hourly runs. Or if you have queries where basically the queries are in a form where it's just different buckets, bucket of the table the queries are running into, you just pick up one randomly and run it. Another thing we did is take the random sample of 20% of the queries and have a goal of certifying all the production workload in last 5 days. So, and then on every day, basically tries it, fix the performance issue, reliability, and sort out the correctness signals. So, correctness has been slightly, correctness has been slightly noisy due to non-deterministic queries and due to non-differences. So we had to improve verifier and verifier as well as some of the validation framework. So one of the things that was crucial and specifically came from Prestissimo being the golden copy and becoming the production standard is we verify the query, but when we when the verification completes, for the mismatches, correctness mismatches, we replay the query on Prestissimo whenever possible, like whenever the scale doesn't cause it to crash or fail. And then Prestissimo, in the second run, Prestissimo acted as the control or baseline, and that minimized the noise to really large extent. And at that point, it became pretty feasible to end up with just a handful of queries which you need to manually resolve. I mean, we didn't really see many correctness bugs. There were two, and one of the things which was which kind of threw us off, because these were impacting very small percentage of queries. So one category of queries were meta lake tables. This was the instance where some of the tables which had the mutations, we were seeing different row counts. And ultimately, you start with the premise, oh, there are differences and there are JSON extraction differences and so on, specifically when they are used in the join. And then when you end up with the row count differences, you have to, is it real or is it because there are non-differences in some of the functions as well as UDFs? And since they are used in join, it makes it. I mean, in both the that was the with the metallic tables, and another was on the legacy behavior. We hadn't turned it on. So in both of the cases, the thing was the config wiring was missing, and a config was not specifying enabling these features, and thus caused it. After that, basically, we replayed the queries for almost 3 months, doing all the performance improvement as well as feature addition before taking it to production. So we had the daily release to detect and fix issues early. So if we talk about first couple of months, we had the nightly build, and we went through multiple validations, basically production sample queries, query banks, and so on, before we certify a package for replay, not for pushing out to production, but replay. Because if a bad package releases to replay, we lose 1 day of signal. So that's a pretty good hit on the amount of compute available for other queries. So and then it goes for replay, and yes, we replay 20% of the queries, and we have the result to basically further refine and fix issues. There was another thing. We have continuous other system being released as well. We have Spark being released, we have other wrappers being released, and so on. So how do we make sure that other releases don't have new features or changes which are gonna break Presto on Spark on Velox, because this is still not in production. So we added validation node in all the upstream projects in their release cycle, so that even though this thing is not in production, if it's broken, it quickly shows up there. And then typical phase releases to contain blast radius. So where do we extend now? So we have more than 40% of the queries running on Sapphire Velox. One thing to clarify, Sapphire Velox and Presto on Spark Velox, I've been using interchangeably. Sapphire is the internal name for Presto on Spark. So we have been running more than 40% queries on Sapphire Velox since last November. And we have been seeing 1.6x efficiency, compute efficiency, and 1.2x latency improvement. In terms of reliability, our success rate went from 97% to 99%, and we have moved from Spark 2 to Spark 3 for this workload. As the next step, we have identified and actively working on resource efficiency and shuffle area in order to reach 2x efficiency. We plan to deprecate Java stack in coming months once we have 100% of Presto and Spark queries running with Velox. Some of the learnings. Yeah, initially we didn't have daily stable builds, and continuous query replays also took some time to set up, but the churn it caused within the dev team was significant. So this really pays off if you have continuous feedback cycle for this. Maintaining multiple stacks gets tricky. So when we started, we were trying to Veloxify Presto and Spark. At the same time, we had Spark 2 to Spark 3 upgrade happening. So if you think about it, we had 4 stacks in parallel: Presto and Spark plus Java, Spark 2 running in production. On Spark 3, the next thing we want to do, Velox on Spark 2, because we know we are trying to build Veloxify the production version, and then another version on Spark 3, because we want to make sure that these projects don't delay each other. One thing we learned, that major focus, keeping the focus to 1 to 2 variants and basically treating the other variants as incremental, it helped us a lot. So initially we started with let's do Spark 2 and Spark 3 both, and that didn't pan out as we expected. So we focused on Spark 2, basically saying Spark 3 will continue in parallel, and once it is stable enough, we are going to switch. And that pretty much worked out. To be honest, to give the data point, we went to production with Spark 2 for all the queries, And later in January, we switched to Spark 3. And that caused less chaos than trying to do multiple things at one time. Yeah, a handful of queries failing could mean real correctness, reliability issues. I mean, this is one thing we learned the hard way that, okay, you need to take a look at, and for every correctness issue, you need to rule out, because a handful of queries failing, in our case, it turned out to be real correctness issues. Overall correctness has to be P0. I mean, we can't reason about the changing user changing queries or basically data shape changing. For the simplest join, which is using a field which is projected using a custom UDF, which behaves differently in Velox versus Java, the results could be different depending upon what a column value is. So it has to be P0 unless you can control this, in most cases, which is not possible. And shadow signals represent past characteristics of queries. So you may go to production with 100 queries, 1 or 2 may need to be reverted back, because there are some things which behave differently, specifically when it comes to allocation of resources when contention is there. Okay, we have a deep dive later today scheduled at 4:10. Please join if you are interested and are running Presto on Spark stack. And thank you for all the contributors.
All right, so let's start. I am William Chen from Microsoft, and it would be nice to be here. I got the invitation from Meta team, and actually my team located in China. So it's my pleasure to be here to share with you guys about some experience about in Microsoft and how we adapt Apache Gluten and Velox into Microsoft Fabric project. And also, I also have another role about, I'm also the Apache Gluten PMC chair, so I also would like to, promote Apache Gluten as well. I remember there's another guy, Yuan, just have done Apache Gluten community introduction before. So I believe this session will be a very good example to continue and extend the and very good example to showcase how Apache Gluten to become the major project in the world, and also how it adapted into Microsoft. Okay, so this is the agenda today. So the first things I would like to share is about why the moment is really matter. And also it's a very important moment, just like I share with you guys, and also what Yuan has already shared. Apache Gluten actually has become the TLP project this year. So it's a very important moment for us, because it's not only just about to contribute your code into the community, okay? We also care about when the entire Apache community to evaluate if your project can become the TLP. It also evaluates that how many customers usage case has already adopted your project, and also how many community has already grown up in a very specific time. So this is how it works when we become the TLP project. So in this case, I believe for Microsoft team, we have 3 different roles to join with the community. And also we, as a customer use case, there are a lot of customers for Microsoft team to work together and also to phase in Apache Gluten and Velox into Fabric project. So this is why we have 3 different roles to join with the community. And this is really helpful when we go back to see why Apache Gluten can become the TLP project. And when you go back to check, the history about why we choose Gluten and Velox, lots of story right there, because you can, just to cook it by yourself. And also, there are maybe some other options right there. But eventually, we decided to choose Gluten and Velox for some reason right there, okay? For example, like Apache Gluten is an open source project right there. So we would like to choose an open source project because, it can actually get some kind of a good reputation right there. But also we contribute the code into the community. This is why there are some reasons right there. We would like to get some support also from other companies, because it's really hard to do it by yourself only. I mean, there are a lot of issues right there, and just like I said, when the Apache community evaluates a project, they also evaluate your project's use case. So if you can handle it pretty well, then you can do it by yourself. But you can actually take the advantage from the community to get better support. So what the Apache Gluten would like to do is we would like to create a cornerstone for every single one. And after that, you can actually to create your own killer features, or you can actually take some money, make more money for that, for your own features. But why we would like to contribute to the Apache Gluten and also to initiate the project is because we would like to set up the cornerstone with a very good example for every single one. And then everybody can join with us and also to create the fundamental stuff right there, and then everyone can take the benefits for that. So this is why we select Gluten and Velox. Velox, there are some reasons for Velox as well, since I remember we initiated the first generation project, we call it a Gazelle before, which is the first generation before we create Apache Gluten project. And at that project, we did it by ourselves, just to implement the entire operators with native way to do that. But after that, we decided to transfer to Velox and with some collaboration with Meta team. That is because we unified Velox can get a better performance, but also it can get more people to join with the community. And also we have more sense and more troubles. Actually, we would like to focusing on Apache Gluten. So this is why we decided to create a Gluten as the middleware and to create several different backend to be supported in Apache Gluten. So this is how it works. We initially, why we created the Apache Gluten is because we would like to take the advantage from the Spark. So the Spark's advantage is actually to create, to keep its very flexible framework, and also with the scheduling, and also with how it can relocate, its resources for that. And it has already been proved that it can actually, this kind of framework can handle very huge data. And for Gluten's job is actually a middleware to create a unified middleware and also a unified API to control everything. Not only for the unified API, but also we also focusing on, for example, like in the bottom line, side, there's a chart right there. We also would like to control the fallback strategy in Gluten, because during we transfer from logical plan to physical plan, we can decide what kind of the plan we would like to create in Apache Gluten. So there are lots of cases right there. If when we go back to check at the beginning, we can only support only a few operators. So at that moment, the fallback is a normal case right there. So we need to control more to help the customer to get better performance, and also to avoid C2R, R2C situation, and also to get some performance regression with very bad user experience for that. So at the beginning, this is why we create Apache Gluten, because there are lots of issues at the middleware we need to focus. And also we then just leverage Velox engine as the new backend in Apache Gluten to just only focusing on those native operator, and to get the best performance by using those native operators implementation. And this is another issue that I would like to highlight about at the very beginning when we facing Apache Gluten and Velox into our production-ready environment. There are lots of issues right there, not only for, just like I mentioned, for operator support. Maybe there are lots of operators maybe cannot to be support. So fallback is the issue. Another one issue I would like to highlight is about the OOM issue. So when you go back to check how Gluten can be supported, it's because about for Spark, it's a JVM-based engine. So, but for Velox, it's a C++-based operator. So you do need to have a very good control and also management for the memory. And what we have already done is about to ask every single API to connect to go back to response to Spark's JVM. This is what we already done in current Gluten right now. So you can definitely to have the confidence and also to guarantee that Gluten can actually handle pretty well to avoid those memory issues. Besides that, in Apache Gluten, we actually can provide two different ways to control your memory. First one is about to have a dynamic profile to handle your memory per stage. So you can based on your profile to tune your on-heap and off-heap memory based on your different stage. And after that, you maybe can, relocate the on-heap and off-heap memory to fit what the situation that you would like to use in a single stage. But in Microsoft, we use another way, okay? So in the latest JDK part, we actually can learn the JDK to handle this kind of thing. So in Microsoft, we use another way to only use, allocate the entire memory to on-heap memory, and then the JDK can choose about how many memory it may be used for native part. So in the latest JDK, it can actually support this. So in Microsoft, we proposed this with the community, and also we use this way to control the memory in our production-ready environment. And also, we were facing some OOM issues coming from those Velox operators. So there are lots of issues right there if you go back to check the source code 1 year ago. But fortunately, most of the issue has already been resolved right now. So I, as a Gluten PMC chair, I have enough confidence about right now the situation is the best situation. If you jump to Apache Gluten, you can definitely get a very smooth user experience, and also to get the performance gen directly when you are using the upstream or our latest release for Apache Gluten right now. There are some other issues that we are facing, but I don't need to go through every single part since I only have limited time for that. But what I can share with you is about there are some other issues, for example, like how we can diagnostic the performance, or what's the metrics when we go back to consider to connect with the native operator. It's pretty different when we consider Spark JVM engine, because the entire situation just changed. So what we have done is about to create some kind of tools right there, or to create a new metrics into Gluten, and then Gluten can support this kind of situation better. So you guys can actually right now can just to check the Gluten source code, and also to get those benefits right now. So it's also under a very production-ready environment right now. There are also some other issues that we would like to address, especially when we will announce Fabric Runtime 2.0 in the near future. And we actually not only, just like I said, what we would like to do is not just to contribute to the upstream, but also we would like to create some value as a company. Okay, so in this case, we also have some kind of killer feature, for example, like a Python UDF feature we have already done for our Runtime 2.0. So in this case, you guys can actually get a more smooth user experience when you have the Python UDF to get better support in Fabric. So this is why, and also how I encourage you guys to join with the community, and also you can also make some money right there. So it's a very good, process, and also a positive way that everybody would like to see, right? So this is another proposal that what I would like to ramp up is about how we can, make the entire process, to go novel and also to contribute to the community, okay? So you can decide it about, for those bug fix, you can decide to contribute to the upstream. And for example, like in Microsoft, we actually, usually select a single specific release from Apache Gluten. So if you contribute the code into the upstream, you actually can benefit, from the upstream release, and also to, just to have a smooth way to integrate into your internal version. So you can take the advantage from this kind of working model for that. And also, just like I said, you can still keep those killer features by yourself, and also, to do something different, to do some differentiation if you like to do. So if everybody can do that, then just like I mentioned, you can create the cornerstone and also create a very, very stable version from the upstream, and for everybody can actually take the advantage from this kind of working model for that. So this is the result about the performance. So what we would like to highlight is about for Fabric runtime 1.3. So this is an older version for that. We are preparing something new when we announce the runtime 2.0 later. So what I can share with you is what we have already done in Microsoft team, and also with 4 times speed up when we compare with, by using the TPC-DS and also compare with the vanilla Spark. So this is a very huge, performance change that we can get from Apache Gluten and also from Velox support. And in a real case, we can actually get 6 times speed up for that. So it's also very, very good, number for that when we compare with the previous version. And the most important thing is about the cost saving. So when you go back to check the Azure Cloud, you can actually save more money from our products. And also, you don't have, the most important thing is about we don't have extra cost for the end user to enable these features. There's only one parameters that you need to set up and also to enable this feature in Fabric. There are more. Okay, so just like I mentioned, we are actually focusing on the new product we will announce in the near future. So in runtime 2.0, we have provided many things that we will include in the 2.0 version. For example, like we have latest Spark version support and Delta support. We also have, like I said, Python and Scala UDF support, which is an important part to really, solve those problems from the real customer case. We also have lots of optimizations for memory and CPU performance. And also we have some hash problem optimization right there. So overall, we can actually get a better performance when I proposed to this kind of idea into Microsoft product. So there are more. We also, there are other teams actually focusing on Delta at the Microsoft side. So we actually have lots of, key features will be, supported in the upcoming runtime 2.0. And go back to check, the TLP journey. I believe it's a really hard moment. And also, before, when we go back to see, since we spent around 4 years to achieve this kind of goal, and also then Apache Gluten can become the TLP project. And there are some listeners, just like I said, it's not just about how many operators you have, or functions you can support, but also we handle some kind of issues like ON, like fallback issues, and I think this is the most critical moment and also very tough moment when I was in my previous company, and when I promote Apache Gluten to some other company. They actually asked me about how many performance that we can achieve. And after that, there are lots of real customer use case we need to handle for that. So it's a really tough moment for us, but we have already passed through, and also to get this, to land Gluten to become TLP project this year. We also have a very specific plan for every single release. So every quarter, we will do the release for Apache Gluten. And I also posted the link to you guys. I remember Yuan has already done some to show you guys about some key features that we are provided to Apache Gluten in the near future. We also have the full list can help you have a very great, reference to about every single, specific feature that we will provide for Apache Gluten. So you guys can check the website for that. And from Microsoft part, just like I mentioned, we actually can would like to plan that with better performance and also with more features to be supported in the upcoming Fabric Runtime 2.0 project. So it's running out of time. So the last one is about, I would like to ask everyone to join with the Apache Gluten community, okay? So you have multiple ways to do that, not only for coding, so there are several different ways you can just contribute your articles or to publish the document or to become the use case. Since there's a program, we call it Powered by Gluten program. And I have proposed it in our Gluten website for that. So it's really welcome to join with us in the community and also by using the Apache way to grow up the entire community. Thank you.
All right, we are going to just take a really quick break so we can stay on time. So about 15 minutes. Please join us back at 3:20 because we will be hosting a really great panel moderated by Masha. 3:20. gonna do, let me see, hold on. So he'll put it. Okay, folks, we're going to get started. Really excited for this panel. I've heard a little bit about what they're going to talk about, and I think it's going to be really great to get everyone on this panel's perspective on AI coding and what's happening with all of that. We are going to try to make this really interactive. And so Masha will lead the discussion for a little bit, and then we're going to open it up to questions in the audience. So I have a mic. I will run around for questions. So think of questions. We want to make it interactive as they're chatting, and about 15 minutes into the panel, we'll pause and take some questions, okay? All right, so with that, Masha, go ahead and get started.
Hello, everybody. Just trying. It works, right? I think it does. Hello, everybody. Thank you for coming. Thank you for staying. And we talked a lot about databases, query engines, GPUs, other complex things. And now we're going to talk about what I think is on everybody's mind, no matter whether they're database experts or not, is like AI. How do you use it in every day? What do you love? What do you don't love sometimes? Like, AI just became a thing I think nobody can just ignore. It's no longer an option to say, oh, yeah, I'm fine. I don't need this. That's okay. I'm good. Like, I haven't really myself used AI for my daily job until sometime in January. Like, I dabbed at it, like tried it here, tried it there, wasn't thrilled, wasn't like impressed. You would have to press me hard to really, really use it. And then something happened, like in January, New Year, whatever. I gave it another try and never went back. Like, this was the last day I wrote a line of code by hand. And I can't say I enjoy it every single moment. Do I get frustrated with it? Yes. I need to remind myself it's a machine. I should have feelings towards it. But it's definitely changed how I work. I think it changed how pretty much everybody here work in the companies. And we have all figuring it out still. I feel like some of us maybe are more advanced, some are slightly, maybe a little bit sort of less, but we all are still having questions. I don't think anybody has the script and knows how to do it. So I feel like it's very useful to hear from different people with different roles, different kind of problems to tackle every day. How do you do it? What you like, what you don't like, what you found works really well, where you still like looking for suggestions and willing to take ideas. So we have 4 people. I would let them introduce themselves. Let's start with Hasib.
Hi everyone, my name is Mohammed Hasib. I go by my last name Hasib. I am a senior software engineer in the Velox-cuDF team at NVIDIA.
Thank you for coming, and this is exciting to have you here.
Yeah, I'm excited to be here. Yeah, this is my second VeloxCon, and
Welcome. Eric?
Yeah, I'm Eric. I'm from Meta. I'm very interested in testing guardrails, so I'm gonna spend more time on this topic today.
Yeah, I feel like very relevant. Like everybody wonders how to let AI run wild, but stay within some reasonable bounds. Aditi?
Yeah, hi everyone. I'm Aditi Pandit. I'm from IBM, and I've been associated with Velox for about like 5-ish years now, and
since forever.
And Presto more largely. So I can talk about my experiences using AI in those projects.
Thank you.
Hi everybody, I'm Amit. I'm working at Meta for 10 years.
Welcome. Thank you for coming. And look, can't wait to hear what you have to say. My first question is like, what do you love most about using AI for your daily job? Eric, you want to go?
Yeah, I think I'll start with productivity is definitely multiplied. And if you are an engineer with many good ideas and you don't have time to do everything manually before, you are really empowered. Or if you are a team lead with large projects that span across kind of cross-functional teams. Traditionally, we need a POC from every team to provide domain knowledge or land code in their own repo. And if you're not lucky, if any of the team is short on staff, your project can be delayed, right, or at risk. Now, that's not the case anymore. You can do a relatively deep research on a complex domain, and at least having a working prototype first. Of course, it doesn't have to be perfect, but over time we can refine it with the team domain expert. But I would say there are no more team boundaries. Projects can be moving much faster and stable. Yeah.
Definitely a lot of power now, like in the hands. Aditi, what's your experience?
Yeah, so I would say, like, top of my mind, two things. Like, so I end up reviewing a lot of code, and I think, firstly, like a lot of the coding agents, they, we got into this habit of getting them explain the code that's written, and so that made like reviewing code a lot easier than what it used to be. It takes out a lot of grunt work. Like I especially love like explain this error that you can run on any PR and any like test in the CI. And I think one of the other things I think it also enabled me is that I had a lot of like data infrastructure experience, but say not much in like, changing some UI or something. And I would get really hassle to change anything in UI because there are so many layers and so many frameworks. But now, if I just want to implement something quickly, I can just do it. So I think that's something I like.
Yeah. Hasib, what do you love about
Of
AI?
course, I love that it's a team of interns that you can at your hand, and especially lately with like multi-model input and output, it's become really easy to like learn new things much faster, have it explain things, and for example, for me, I'm a part of the libcudf team. I'm not fully working on Velox, only not working on libcudf. I'm switching between, and then before like AI agents, when you switch your mental context, you do a mental kind of context switch, going from okay, I'm gonna work on this thing of Velox, or maybe like this thing in libcudf. It took time. Like now you can teach your agents on to do how to work to behave when you're working on, let's say, libcudf or working with Velox, or when you're working both of these things. So it become easier to translate your skills into something that you can teach to your agents and have them use it. So it's like less mental burden for you, kind of like offload a lot of your work to the agents, which is really nice.
Yeah, so sounds like kind of working across two large code bases, libcudf and Velox, became a little bit easier.
Yes.
Amit.
Yeah, for me, I think I can do many things in parallel. Like if I have to fix some production issues, some crash or bugs or test failure that we could hard to debug. Previously it could take like 2-3 hours sometimes. Now with AI agents you can do in 5-10 minutes, even less, right? And at the same time you can do some coding work also. So it definitely make one person do many things and utilize the time better. That's I really like a lot.
Yeah. Isn't it amazing? Like, if you have like a simple local repro, you can just tell the agent, hey, I'm seeing an error when run X. Figure it out. And it does.
It does, yes.
In many cases, it does. It's
Yes.
like, for me, that was like, really? That's nice. It takes a lot of tedious debugging, printf work out of our days. But is it all like rosy and nice? Anywhere you feel like AI falls short in your like daily work? Aditi?
Yeah, I mean, actually starting using the coding agent was quite stressful because till you get used to how to like make a dialogue with it, I mean, if you'd asked it to write some code and, so like for an example, I wrote some Velox functions using a coding agent. Like the first time, I thought like this is very straightforward. Like so many Velox functions out there, so like well written. I just need to like explain this and use this API. We made a bunch of mistakes, and debugging them was quite painful. So till you learn to like basically be able to describe things and be able to run through every step of the process with it, it's very difficult because you don't know its thinking process, and then when you get this chunk of code and you have to debug it, it's like quite painful. So yeah, but now I got more used to it and got better with the dialogue.
Yeah, it can produce a lot of code very fast, but then how do you know it's the right kind of code?
Exactly. like if you see Velox aggregates, there's so many APIs. It can mess easily between them. So
yeah, thank you. Hasib, how do you feel about it?
So, I'll say the same thing again. It's like having a team of interns, not engineers. And, by interns, if you're...
Every engineer has at some point been...
Yeah, but, but I think the biggest thing for me is that as tasks get complex, they degrade really fast and really bad. So if you're having a bad day and it becomes like a domino effect. For example, working with Velox-cuDF, we have things that are in upstream Velox. If you make it try to understand what's going on in upstream and what's going on in lab-cuDF, and then use those two things in context and do something for you, it's going to break down. It's not going to understand which one to follow. So if you have multiple information from multiple sources, for example, multiple coding standards, lib-cuDF, a different coding standard, it has a different coding standard. And now things start breaking. And then when things break, for example, it's not going to remember that there are some things that are already, well, just going to start like dumping code, duplicate same things again and again. So even with, I think if you don't know what you're doing, then it doesn't know either. So you need to be very specific on what you want and how you want. Otherwise, spend a lot of time debugging.
Yeah. Eric, do you have something to add?
Yeah, I think AI definitely has limitations, but I think that's okay. I mean, human also has limitations. I have limitations. So I'm also treating, similar to you, treating every agent as a smart engineer, but who are also new to the team or new to the domain. So we're trying to solve that by building a team of domain expert agents and keep enriching them with rules and latest context. And with that, we are building something called a harness engineering framework with strong guardrails to help guarantee we have high signal output out of the agents. I think the guardrail, for example, like high signal end-to-end testing suites or performance benchmark, like those are very critical if we're talking about complex systems like Velox, right? Even agent can generate a unit test. For complex system like Velox, we need really well-crafted testing suites to guardrail the output.
Yeah, testing feels like even more important with agents kind of trying to figure out. Like I'm seeing an AI coding agent can make anything seem like working.
I mean, it can just change your test to make it work, or delete it altogether.
Exactly, I saw them do that. Amit, what's your experience?
I think my experience, the designing part of the software, where the main fun was, that might be diminishing a little bit, right? Because now people start implementing very quickly without thinking too much. So that part, how to tell agents that you have to think these other things that we want to do after 3 months, 4 months, maybe after a year, that vision is hard to put. I mean, in prompt or any other way, and also it's hard to write out. So that is major thing I miss.
Yeah, I wish there was a unit test which tests for design correctness.
Yeah.
Yeah, that's my wish. Anything you guys miss about good old days when we were coding by hand? Amit, you miss anything?
Yeah, I mean, in old days, we had to review less designs, less diffs, right? Less code. Now there is a bunch of things you need to review. The volume of things that getting reviewed by humans is increasing, right? It's not like the burden has reduced from the writing side, but the other side is probably exponentially went up.
Do you feel like your to-do list fills up faster?
Of course, yeah. And I'm bypassing and just not looking at it, right? So that is probably downside.
Yeah, yeah. Hasib, how do you feel like anything you kind of wish didn't disappear?
I think like my ability to focus more and like really spend time on things has gone like much lesser than it was before. So now I think we're kind of like getting addicted to AI working all the time. So if it doesn't work, then it gets like really hectic and really fast. And even though you can do those things manually like you used to a year ago, but you know, it kind of feels like burdensome and like you get overwhelmed quite often, quite frequently and quite easily. So that I miss, you know, like to be able to design properly and do things my way.
Yeah, yeah. Eric?
I would say what I miss is the work-life balance and sleep. I feel like
sleep is overrated.
Overrated. Yes. Who needs that? I think working with AI is like it's like a dopamine loop. Every time AI give you exciting results, you got excited, you got a dopamine hit, and the loop continues. And you try to feed the agents with more work. I know many people are trying to queue up work before they go to bed, right? They give it a rough loop setup for it to keep grinding overnight. And when you come back in the morning, you got some exciting results. But the loop continues, but there's no end of work, right? So that's what I'm working on, to find a new work-life balance and get back to normal.
Yeah, I really love how you kind of capture that kind of dopamine rush that you kind of get. Like you before you used to work for it, like to get like a result, to have it working, and you could get tired in the process, and then maybe you'll say, okay, I can get it tomorrow. Now I feel that too. Aditi?
Yeah, I think nowadays, like Amit said, right, the number of reviews you get is crazy. And it's also like a lot of, if you ask for like, okay, what are you trying to do, what's the design? You get a text that's generated by AI. And so like you find yourself drowning and drowning. So every question you ask is also returned by AI and AI. So you feel like you don't know who's the engineer. And like previously, you would know the engineer and like, you know, so everyone has a style and you would kind of like tune to it. But now it's like, it's just like mounds and mounds of text coming from agents. That's how I feel.
Did you ever feel like, hey, can I talk to your agent?
Yeah, exactly. It's like, you don't know whether it's a human or agent.
Yeah. Oh, we've been talking for quite some time. I think there's a lot of thoughts swirling. Anybody has a question? Or maybe not a question, but maybe you've heard something and you want to add? Like some of the things that are going through your mind, or just contribute to this conversation. I think we have a mic. Thank you, Ali.
Hi, I'm Akil from Data Pelago. So I'm listening to this panel discussion and sort of the broader discussion about AI coding, and all of it seems to be focused on using AI as a productivity tool. I'm thinking this entire framing seems backwards to me. So, you know, I don't think it's I don't think the problem in the software industry is the software industry moves too slow, or that we don't produce enough code. It seems to me that the actual problem is a problem of quality. And maybe what we should be doing is not use AI tools as a productivity tool, but say, okay, don't use it for productivity. Use it as a tool to improve the quality of code instead.
I kind of love it. Thank you. Thank you for saying it. I'll let our panelists comment in a second, but I love it so much. I want to say a couple words. the way I'm trying to frame it for myself and whoever is willing to listen, sorry, all of you today, I want AI to allow us not to build more systems, not more things, but rather better. Like systems that require less automation around, systems that require less maintenance, less configuration, less fully understanding how exactly it's built when you're kind of not supposed to, but you end up knowing more than you ever wished you knew about the system. So I hope I'm hearing what you're trying to say, but that's how I'm trying to say it. Let's build better, not necessarily many more things. Folks, who want to comment? Eric, go ahead.
Yeah, I kind of agree with Masha for the state of art kind of direction. Yeah, not more parallel work. But I also want to answer that we're also using agent workflow to eliminate the boring part of the on-call work. Like we have production on-call, we have a release on-call. And even for testing, right, people used to have do the menu evaluation for this diff. What end-to-end test should I prepare? What clusters should I spin up for? This is all the stuff that we are trying to do right now to, at diff level, at release time, to let the agent workflow harness the entire testing process. So human doesn't have to spend time on those kind of chores, I call it. Yeah, just make our life easier and we can focus on more interesting things. Yeah.
Amit, you want to add?
I think, yeah, I mean, the quality part is really interesting. Maybe, I mean, we try to use AI for implementing the hard features that we could never do. I mean, Masha also told me these things, I'm saying the same thing. But there are a lot of cases for a big systems, even like Velox as corner cases that we never try to implement or never try to harden because of resource, right? So those, I think, we should really do, and instead of going for volume.
Yeah. I also feel like, it really helps with prototyping. Sometimes you think good ideas, but like you're really kind of not 100% sure to kind of commit real resources or even go convince other people. I feel it became a little bit easier to kind of whip up something dirty quick and see, okay, is it holding water? So for me, that's actually value, meaning more productivity by like not building more, but rather knowing what to build and what not to build.
Mm-hmm.
Aditi, you want to add a word or two?
Yeah, so in terms, definitely like quality is a big thing, and I actually feel that, now I'm becoming more and more like lesser code but writing more tests, and like telling the agent like, oh, write a test for this, write a test for that. And yeah, I mean, that's kind of nice because now whatever code you try to submit, you can be quite diligent about writing tests, which in the past, sometimes in the speed of things, you might not have written as many tests, but now you can be like, okay, you can have a whole skill around like categories of tests and like make the agent go to it, and that's kind of quite nice.
Yeah, I also found that like sometimes I want to build a test framework. It's not hard, but kind of tedious, like just a lot of code to write. Now I can do it.
Yeah, like now it's easier to like abstract every layer of like the processing stack you want and like kind of write test framework at each one, which could be a bit clunky in the past, and so you kind of just didn't do it, but nowadays you do, yeah.
Yeah. Hasib, anything you want to add?
Yeah, so I'll say like much like human engineers, AI coding agents are also lazy. So if the quality is not embedded in the prompt, in the plan, in whatever skills or whatever you're using, right, it's gonna produce low quality code output. So I think as humans are like the line of defense against bad quality. It's not like AI's job to produce quality code unless it's been told to and specified how. So I think it's at the end like a human's job or whoever's responsible for it. It's job to make sure that there is quality in the work that it's produced.
I feel like it also kind of forces us to be a bit more disciplined and formal about what we do, how we do it. Kind of like explain it, always in writing exactly the standards, which used to be kind of a little bit fuzzy. Oh, don't you understand? Kind of obvious, right? No. So now I feel like it's a little bit good because it kind of allows you to understand more what's important, what's not, why. Well, this was great, great addition. Thank you. Anyone else has a question? Okay, we have some hands.
It's more about some short comment. Actually, I agree 100% with what you actually said. My experience with agents is that right now coding is become more like prompt engineering. And my experience is that if you start with very generic prompts, usually the models, especially these which are hyperscalers, because they go to internet, they basically can hallucinate a lot. So my experience with agents is that you need to have more like multi-agent systems, which are more focused on basically use the prompts to focus on the local data, local jobs, instead of going to internet and try to find something and hallucinate. That way they are kind of more deterministic. Also, you can play with reasoning, right? So if the task is, or the job is more kind of straightforward, you don't want the model to reason a lot. So you can actually say, okay, don't reason, go straight forward to this, right? And you can actually prompt it right away.
Yeah, curious, like if you ever kind of ask it to use less capable model, like cheaper and but also kind of with less reasoning. I've heard some people do that.
Yes, because if you use, let's say, Grok or OpenAI, with these models, they're trained with everything that is on internet, right? But I found my experience is if we use local data from the company, right, and then use smart prompting, they are less prone to hallucinate. Yes.
Makes sense.
Yeah.
Anybody who wants to add or comment on this?
You can take a shot. Yeah, you mentioned the prompt engineering, right? I feel like that is a challenge earlier. I feel like we are already moving past. Oh, sorry. My bad. Where did I lose you guys? Okay,
you haven't lost us. We're here.
I feel like we moved past the prompt engineering to context engineering. Now we are in the harness engineering already. The agent is way smarter than like 1 year ago. I think that's what we are trying to using the domain expert agents and the guardrail for the harness to generate the expected output. But I'm really excited to hear that for your local data setup for your company, it's even better. So that's good to hear.
Yeah. What I'm heard is that you're essentially saying sometimes like showing it less information is actually helpful. Like allows it to focus, just like a human, right? Sometimes you say, okay, I can't know everything. Stop researching, start doing. I think we had another hand. Yeah.
Yeah, hi, I'm an engineer from Meta. My question is like, can you guys share one of the most interesting feature or task or whatever things you've done recently with AI, and how do you use AI to do it?
Sure. Aditi, you want to start?
Yeah, actually, relevant to the panel, I used the agent to write a bunch of Velox functions. And it was pretty cool because the Velox codebase, thanks to Marsha, it had tons of examples. It had, there's a lot of good documentation of the APIs. Yeah, just like very well written code and like even the very good like skills also written in the Velox code base to be able to do like the function authoring quite good and nice. And I think that maybe like encouraged me to use AI more. But yeah, I wrote a bunch of like Velox functions recently. It was actually quite a good experience. So then I started wondering like if we could just automate this with like an agent, and it also made me feel like, hey, could we have just done Velox faster if we had this agent before, and it would have given us correct code for all the functions and everything, like, yeah.
Yeah, definitely. I feel like, agents benefit a lot from like a well-structured code base with like standard patterns. Velox definitely has a way to go, but like I feel like with more code we're writing, I feel it's useful to make sure it's clean, easy to copy paste is safe. So if it is, then agent does really well. Hasib, anything you want to share with us? Like something that you feel like was pretty cool?
Yeah, of course. So I first started working on Velox around late 2024, I want to say. And the first thing that I worked on was table scan and CUDF connector, data source. Those were the first things that I contributed. And recently, by recently, I mean like 2 weeks ago, I started looking into CUDF Iceberg. I think we talked about in one of those slides in the morning. And it was roughly the same type of work. It's adding a new data source, and then it took me maybe like 2 or 4 hours to achieve all that. Of course, I had to then spend 2 weeks to edit and review and everything, make sure everything is good. But yeah, I think that was a very good achievement. And then I learned a lot of things while working on it, especially like instead of giving it something and say, hey, work on this, discussing with it interactively to come up with plans, split those. It's a huge feature. It's split into multiple phases, multiple plans, and then look at those plans and go over with all those plans and kind of like work through with it systematically. So I got like a really good output code to work with, to start working with, which was pretty nice.
Yeah, that sounds very nice. Amit, you have an example to share?
I think most of my examples on debugging, like say, the first time like at the beginning of the year when I found some test failing for some linking issue, which is linking is very hard to debug manually, right? But when I saw I figured it out like in 5-10 minutes. So those kind of things, and then there are some definitely crashes, corruption, which AI is very good navigating through Velox. Even though there are some crashes, corruption it could not figure out yet. Maybe you need Mang, but it's generally really good.
Yeah, actually, my one experience is that whenever you advance Velox and Presto and if there's a failure, AI is very good at fixing it.
Yes. And isn't it nice? Because those are kind of tedious work. We don't mind automating.
Exactly. Like every time this job would trigger, right? We'd spend like half a day between like 2-3 of us, like asking each other, like, how do you fix this? But now the agent does it, like, so well.
There is also like the CMake changes, right? I mean, you know about CMake changes because we don't run CMake internally, so it's hard for us to set up the open source setup. Previously, we need to set up in our laptop.
Isn't it nice? You can just copy paste an error from CI.
Yes.
And don't even prompt anything. It knows, okay, I need to fix it, and this is how you fix it, and like done.
You don't even have to copy paste. You just let Claude go to the CI signal, right?
Oh, I just paste screenshots.
Can it?
Yeah. You can.
Okay, we need to talk because I've been copy pasting, so maybe I'm missing out on some productivity tips. But Eric, any example you want to share? Something like you found like, oh, this is amazing.
I think it's when you are new to a brand new domain. Like a few weeks ago, I'm working with Piper, with the training team. I have zero knowledge about the training platform. But we are trying to help them to onboard to a end-to-end high signal testing framework. So, and there's no resource from training team because they are super busy. So yeah.
Everybody went to build AI.
Yeah. So yeah, just with agents, it is doing a like 4-hour analysis, and based on the plan, it come up with just like I said, it's a working prototype. It's not perfect, but at least I can move forward. With the prototype, now you can use your spec. We're back to like TDD or BDD now, right? We define what we want. We define the test case. Now it iterate on it itself. That's the magic part. It keep improving itself with your well-defined standard and testing case. Yeah.
Don't you find that AI allows you to kind of onboard to a brand new code base, sort of enough to start asking somewhat intelligent questions for busy people who can help you, and kind of skips, using their time to just kind of ask very noobs questions. So for me, I feel like that's very powerful. Like I can come and speak in the terms that people understand, and I can ask a question that they really need to answer, like I can't get easily myself. Yeah. One thing I find pure amazing is that when you kind of debugging query failures, production queries at Meta, they're verbose. I don't know. People love writing SQL. I think they use tools to build that SQL. So it goes for pages and pages and pages and more, and then it fails. And so the standard technique is first you need to minimize the query to get to something you can reason about, and that's boring. I know how to do it. I don't enjoy it. And so one day I thought okay, it's just way too big. No, this thing can't do it, but I also don't want to do it. I'll give it a try, and then I'll write a blog about AI limitations. So I told it, hey, I have this query failure. 10 minutes later, it was minimized to 5 lines, and it also told me what's wrong. I love it. Yes, I didn't get to write a blog post about how AI is coming up short, but now I don't need to minimize queries anymore. So for me, that's pure miracle, enormous time saver, and I just love it. Do we?
Hello, I'm Oliver. I work for Meta. We all know that AI is powerful, and we can move much more faster with the help of AI. But for a junior engineer, I feel like we're having less chance thinking if we're not skipping, when we are delivering the results. So do you have any advice for the junior engineers, especially for their growth in the long run?
That's a hard one. And I kind of happen to know that particular junior engineer. He's pretty good. So he actually has an answer. I don't know. Do you want to share your tips? How you growing? Because, so folks, anybody wants to take a stab at trying to answer that question?
I think I can go. So when I was a junior engineer back in January, that's when we started using AI. So I asked myself this, what's one thing that I do every day which is tedious but not really complex, right? And maybe I can teach AI to do that. And I listed my exact. So one of the things that I used to do every day was rebuild my containers, set up my work environment, which is pretty simple, but it takes 15-20 minutes. But I don't want to do that every day. I just want everything to be in the shape that I left it the day before. So I taught it how to do that and how to. I was quite skeptical because it included installing a bunch of VS Code extensions, fetching a bunch of stuff. I was like, maybe it can do it. Maybe it can, at least it'll do some steps, right? So I was able to teach it, and I was able to do all those things. When that happened, it kind of clicked in my mind, I can really offload things like how to build. I mean, if you have special CMake, special things, right? You type those commands every day, or you have to remember certain flags. Those things are really easy to teach, and they don't really change over time as much. So things like that you do quite often every day, and those are tedious but not really that technical if you know what you're doing. So I think those things, as a junior engineer, I would start by offloading those things and start really focusing on things that really matter. And maybe whenever you have something, just write it as a skill and teach AI how to do it. You fix bugs every day, the whole steps on how to fix a bug, right? Read this, let's say write a test. Do not make any change in the test to make it pass. You always have to make sure that the code passes the test and not the other way around, right? So those things could just accumulate over time, and you can become from a junior engineer to a senior AI engineer, which is not really a thing anymore.
Amit, you want to add something? If not, I'll go and then I'll come back to you. One way I find that AI is very helpful, you can ask it any question. No worries, noob question, stupid question, whatever. It will not shame you. It will actually explain. And so I find it might be useful, like you build something, it build it for you. And then you can ask, hey, is this the only way to build it? Why? What would be another way? Why did you choose that? How about maybe the other one is better? Like engaging in that kind of discussion, I think might be useful because you may learn more about what it actually did, why it chose it. It may switch, or you may can try to discuss, or hey, can we review from first principles and find the best solution on merits? Let's do that together. And I find it's willing to engage into that, in that discussion. So that might be my easy advice, if it helps. Anybody else wants to share?
Yeah. So yeah, actually, I pretty much as first principle added to my top level code rules to really make a change for either research or crafting a diff. It really tried to solve the root cause of the problem. But I want to answer your question. To be honest, I feel like junior engineers is even more empowered compared to senior developers. Traditionally, senior developers has either more knowledge or tribal knowledge or legacy knowledge, but that's not the case anymore. You can easily get access to all of them through the agent. I have seen many junior engineers. They are already operating at senior level, like amazing engineers. So I would say it's the prime time for junior or for everybody who are genuinely interested and motivated.
That's a very good way to look at this. Just if I may, like very quickly, one other thing I find is like, try to explain to somebody else what you're doing. It's remarkable how much better you can start understanding what you've done or what you haven't thought about when you try to explain it to somebody, either in writing or in person, in a discussion. That can kind of deepen the understanding and help get beyond just, oh, looks like it works. Somebody stamped it. I'm doing well. One more diff, next diff. So we have...
I think we have time for just one more question right here. Yep.
Yeah, hi, I'm Oleg. And I have a question. From the business standpoint, code base is always liability, and sometimes it's a black hole for my budget and for my money. We need to maintain our code base, healthy code base. And I have a question. So maybe we already can forget about actual implementation in our code base and use some kind of like set of tests, unit tests, integration tests, some sort of like E2E tests to forget about actual implementation and said, okay, we don't care about code base anymore. It can be sloppy. It can be like terrible until it comply with all our rules, all our tests and working in production. We do not need to check code anymore. No manual reviews, nothing. If like all our gates are working, we will never touch source code again. So we will use agents to write code, to write new tests, to brainstorm a lot of use cases to cover every possible edge case, and it will be our like gates for the production. All tests, okay, that's fine. What do you think? Can we already move to this approach, or maybe in the future? Yeah.
I wish that was the first question, so we had more time. Who wants to start? Eric?
I have to answer this. I have really similar thoughts. If you look at a popular database, SQLite, their code is open sourced. It's free. But actually, their testing suite and benchmark is closed sourced and behind a paid license. So that's how they charge their customers to evaluate whether SQLite work in their production environment or not. Another example is our own Scale AI. They're becoming one of the, not becoming, they're one of the central authorities or judges for large language model benchmarking, because they have those closed source benchmarks that are immune to the AI contamination problem, right? Which is a big problem. And that is what we call the gold standard for enterprises, for Fortune 500 companies when they evaluate large language model for their own company adoption. So yeah, I feel like these benchmarks, these test suites are becoming the standard for kind of to provide quality of agentic output. There's another example. Like I'll stop here. I talk too much. But yeah, this is what I really like. But back to this one, I think it's going to be a black box situation versus maintainability problem. Like for our production usage, if we use a black box approach for Presto or for Velox, it's going to be a nightmare. We cannot start with a new black box to fix this new test to pass, but the iteration will take forever and not going to be a sustainable thing. Yeah.
Anybody else has thoughts on this topic?
So that brings an interesting point because this happened in like the Presto project once that somebody like generated the entire code with an agent, right? And they weren't aware to the point that they said that they would need an agent to answer questions because they didn't want to like answer questions themselves about that code because they had entirely used an agent. And so it almost led to this kind of situation where we had to be like, okay, like, let's just write tests and kind of come up with what we think is the intent, should be the intent, and then that's how we had to test that code. So yeah, some of those kind of scenarios do happen. I mean, definitely.
Yeah. Thank you, everybody. Thank you for coming, making this an interesting conversation. I really love how many questions we got, comments, thoughts, and thank you to our panelists who agreed to come and share their perspectives. I feel like we had a really nice variety and differences in thoughts. So I hope everybody found something interesting, something new. So thank you.
Okay. Hi, everyone. I'm Srinidhi. I'm a software engineer at Meta. I'm going to be talking about the Veloxification of Sapphire. So you folks have probably heard quite a few talks by now about compute engines and Presto and Spark. So I will try to talk about things that are unique and try not to bore you at the very end of the 2-day journey. And I understand the attention is limited at this point. Okay. So also to make things interesting, I tried to maybe switch up the slides to tell a better story compared to what I had before. So we have the customer problem. I'll talk about why we are doing what we're doing, what's the vision, some of the architectural details, some things that we built in the engine that we think will generalize to other engines. What are the challenges, results, and the future? So yeah, I pulled up this slide. Before anything, I just want to throw this at you guys. This is, as Masha called it rightly yesterday, awkward engine. Why do we have it? Masha probably has better words. I had far worse words when I first encountered this. OK, so let's take a look. What is the customer problem? In general, I think you're all familiar with this landscape in analytics where on the left side, customers try to run queries that they want fast responses on. And in the far right, you have workloads that need scalability, fault tolerance, Spark-like things. The stack I just showed you falls at the very far right. Think of it as ripping apart the Spark SQL part of Spark and adding Presto SQL on RDDs. That's basically what this stack is. OK, why does it exist? I got to learn some realities as well. Firstly, are we solving a non-existent short-lived problem? This is a very awkward engine. Like, how has this survived the test of time? A few things, right? Presto is extremely popular at Meta. I almost attribute the existence of this engine merely to this one fact. Why this matters is Presto has first-class integration at all data analytics touchpoints. So users start their data journey at some Presto entry point. And eventually, they want to productionize their workload, right? Customers don't like to move engines. Once they write something for their business, they want it to just work. They don't want to translate whatever they used in their research. They just want it to run every day or every hour. But eventually, data grows. Queries start failing. Presto is massively parallel processing architecture. It has M-cross and streaming shuffle, which limits the cluster sizes. Query zoom because you can't partition the data well enough or can't get the partition small enough on the machines that we have. Don't have fault tolerance beyond a few hours. If a worker goes away, the whole query fails. Sure, you've heard of this story. And everyone loves one-click reliability. So currently, this engine is bundled as a single line of code change in your existing like Presto or Prestissimo pipeline. Yeah, because of all these reasons, this exists. And even just last year, it kind of grew by 2x. But things are changing fast in the world of AI and agentic coding. So some of these realities might be different now. But regardless, I think what is the motivation and vision, and what are we trying to do here? So the vision is pretty clear, right? We want to run Excel-sized Presto SQL queries efficiently and reliably. Like, there is no solution today that other than what we have built here, at least as far as I know. But also, I understand that for the reasons that I mentioned before, this might be like a uniquely Meta problem. And that's why Meta has this engine that we have built. It is open source. It is in PrestoDB. So the other goal is to fully deprecate Presto Java worker at Meta. I think this is just in line with the Prestissimo journey that we have had. We don't want to run the Java worker anymore because of all the great reasons that Amit mentioned. But how do we Veloxify this without it being like throwaway work, right? I think the thing we narrowly tried to focus on while trying to deliver on the first two goals was to figure out how we can get a few things right and use them as building blocks for the future. At least at the time we started the journey, there was no decided future as such. We had the paper that Pedro and others also authored for the composable data engine, but this journey started like somewhere around that time where there was an idea that there's going to be composability, and at some point we'll have something which we can build on. So with that in mind, we try to build things that we can transfer to the new composable data world. It's being called XL now, so that's that. So now we'll talk about what are the few things we focused on and tried to get right that we actually will plan to kind of move to XL. First of all, some general principles we had in mind while building is reuse the full Java control plane offered by existing Sapphire, Java, and Spark. I think I kind of showed you the architecture before. We did not want to rewrite any control plane logic. We just wanted to replace the data plane. This means we don't have to do any additional work for fault tolerance and scalability. There are some unfortunate trade-offs, like we'll have JVM on the worker still, but we kind of swallowed that. All or nothing execution, query runs either fully in C++ or not. This is in contrast to some of the other approaches you see in the industry, like Photon or Gluten, which are GNI based. We made this decision just to keep complexity low. Prestissimo team already built a great worker. We just wanted to reuse the worker as is, reuse its control plane, HTTP APIs, etc. No data exchange between JVM and C++ process, only control messages. Again, keep complexity low. Don't take the performance hit for data serialization and deserialization between the two processes. This means we cannot use Spark's data distribution mechanisms for like broadcasts and things like that, but we were like okay with that. We'll just use persistent storage for all data transfer. So with these principles, we kind of set out to Veloxify this stack. This is what it looked like. So just going back quickly, I shuffled the slide, so I'll have to show you this now. So this was the original stack. As you can see, it's Presto planner, fragmented plan, converts to Spark RDD, and just hands it off to Spark scheduler. And we have code in the RDDs, like compute function, to just spin up the worker, which does all of the actual data plane work. This red box on the right basically changed to, sorry for that, this, right, which is now the red box is a very thin control plane JVM, and we kind of spin up the Prestissimo worker, use the familiar HTTP APIs of the Prestissimo worker to spin up tasks, except also integrate with like the shuffle service for materialized exchange. This was the overall architecture, but going to what we tried to focus on and get right and is durable, right, which is no pun intended, materialized exchange. Why do we need it? This is the building block for fault tolerance. If you do not materialize your outputs, you cannot retry the set of tasks that fail that need those outputs. This is a classically known problem. Where is the complexity? The complexity for exchange is in the quadratic explosion of like data chunks. When you have like M, like workers doing the scan and partitioning the data n ways, you get like M cross n chunks. And for large queries, this gets out of hand. And it creates, even if you think of writing all of those small chunks to files, it creates this random disk IO pattern that is really bad for throughput, and your query just comes to a halt. And you will be like basically hammering the IO layer, service IO layer. This is a known problem again. There are a lot of shuffle services outside. Meta uses Costco. Costco is the shuffle service. It converts random IO to sequential IO. You might have also heard of Magnet and a few other things. Costco, there is a YouTube link. You can watch that for more details. What is complex in this setup is the writers and the IO path that is extremely performance sensitive. We do row by row processing, so you mess up, add an overhead, it immediately shows up in like 1.5x or 2x of the cost of the job. This is also the part that is not hardened anywhere today with Velox, so we tried to focus on it so that we get to do it right. What does Velox already have for Exchange? Velox was first deployed in Presto, so it leans towards like streaming Exchange semantics. On the right path, you have like partition output and output buffers. But this output buffer kind of just waits around holding data for like an HTTP call to come in and take it. But in materialized exchange, we actually want to push it out to the server that will do nice large IOs. So we had to fix that, or rather find a solution alternative to that. Read path is pretty good. The Exchange client, Exchange queue, and Exchange source, which is configurable, like are kind of good enough abstractions to plug new exchange systems into. My personal quirk has been to make like exchange client configurable itself versus like making exchange sources where the whole kind of shuffle system sits behind this exchange source, just pretending that it's streaming shuffle. But that's for another time. Yeah, so to solve this space, we basically added new exchange operators for integrating materialized shuffle. These operators get added during local plan conversion in the Presto workers today. So these are basically the three things we added. So on the bottom, you have the mapper stage. You have exchange write operators, which basically push into exchange output buffer, which pushes out to your external shuffle service. And that's the small random IO part. The shuffle service kind of aggregates from everyone and converts that into sequential large IO, and you have like large, nicely sized files that then can be read by like the reducer stage. And there again, like I just mentioned, the whole partition data for that kind of reducer task is sitting behind like a one exchange source, and its job is to just return like serialized pages. And then the rest of the stack just pretends we are doing streaming exchange. But all that works, so we kind of reuse that for now. In our experience, the harder part of getting this done was the write path versus the read path. The read path is fairly simple. You just read files and just try to do it nicely in a way that Velox understands, and you can convert back to serialized pages. But the write path was like the trickiest to get right. So yeah, a lot of colors, and so I'll try to walk through this and try to explain what we really have here that makes materialized exchange work and how it solves the random IO problem and how it integrates. So you get row vectors on your drivers in a Velox task. And then what you really need to do is partition all those row vectors into the right partitions. The simpler way to do this is to just have a buffer per partition. This is actually exactly what we do in streaming exchange as well. You have an output buffer, and you have destinations, as it's called today. And you enqueue like pages into that destination. And then for destination 0, someone comes and makes an HTTP call. In our case, we just hold it there. But here's where it gets tricky, right? Streaming exchange is generally about two orders of magnitude smaller number of partition counts than materialized exchange. With materialized exchange, the partition count goes way higher. So the number of buffers can be really high, which means that we need to be careful on how big those buffers are, or you risk kind of running out of memory and ooming, or just making the job really expensive. This is kind of the first tricky part of materialized exchange. So here, yeah, you have like, and the other thing is also that even before getting data into these partition buffers, you don't want to be adding one row at a time because you're getting row batches in Velox. So what you want to do is have another small buffer that's fixed cost, which is O of number of drivers. So one buffer per driver where you write the partition data, and then that's kind of the first level of batching. And then that small batch, let's say for partition 0, goes into the, as shown, can't point it out, as shown there. So you kind of queue row groups into the partition buffers. This works really well. It helps us. The main thing that it does well is that the operator memory pool in Velox, before doing it this architecture, we had an initial architecture where our Costco kind of writer was completely opaque. It would manage its own memory, et cetera, and that was very limited budget, which means that the buffers per partition would be really small, which means you create a lot of small IOs. But now the good thing about this is that we integrate into the Velox memory pool, which means that if there is memory, we actually get to create larger per partition buffers, thereby being more efficient. So the write path costs are directly proportional to the number of packages you send and so on. So the bigger packages you create over the network, the lesser the cost is and the higher the throughput. So this kind of tight memory integration lets the exchange writer kind of burst. And the interesting thing that we noticed in our workloads is that this is really useful because a lot of workloads are going to be doing just table scans, partition, and then the next stage is going to be join after the write. So the first, and your jobs are really sized to hold memory for that second stage, which is going to have a hash table or some kind of in-memory data structure. But on the write scan stage, you have a lot of free memory that the exchange writer can now use and create like really good sized packets. One of the things that I think we also, not I think, but one of the things that we kind of did right is from the beginning, like based on our principles we laid out, we actually worked with the Costco team at Meta to write native clients that they currently Costco is mainly integrated with Spark. They had a Java-based writer, and so in Spark the model is you have a task, you create like rows, and you send out rows out of the task into the writer. So, but then that model doesn't work because we don't want to send data out of our CPU process. So we worked with them to actually write native readers and writer clients that directly integrate into the Velox, the CPP process, and Velox is aware of it. So that strategy has also worked out well. The other thing is also like, not sure you can see it, but on the right side of the biggest green box is kind of the mechanism we also are adding to integrate into arbitration. So when these partition buffers think that there is memory and they end up consuming it, but maybe there is not, we want the signal to kind of shorten the buffer sizes so that we are in the reasonable limits. So the reclaim trigger kind of lets us do that. It also lets us flush buffers when there is memory pressure. So this is showing very good results. And this is kind of the most performance-sensitive path in the stack right now. Well, other than what the Presto team already hardened, basically this was the main thing that needed hardening from a performance point of view. The next is exchange read. I think the exchange read part is fairly straightforward, and there isn't like a lot to kind of dive in. We hide behind like this exchange source and like create a Costco shuffle source, and like Costco actually supports like 2 kinds of shuffle. In one of them, it can actually sort the data for you if you're doing a sort merge join. This is an interesting thing about Costco. So we just have one native reader that has a package queue, but it's backed by different kinds of sortedness. And the Velox framework just sees data coming out. There isn't a distinction. It just sees serialized pages. The file readers are also integrated with the memory pool. Currently, we don't. The hope was that we can actually control the concurrency of the file readers based on how much memory is available. So we are set up well to do it, but we haven't added that yet. That's one of the future works. Currently, they just report the memory and participate in arbitration. So yeah, like I said, I think our goal was to, while solving for the organizational goals, also focus on things we could harden, build, and reuse for the future. So right now, these are in Presto OSS. We are going to move them to Velox. We are already in discussions to do that, and so that they can be used in Axel. Pluggable exchange client, I think this part is kind of still under discussion. I personally feel like a fully pluggable exchange client that any other shuffle service like Costco or some file-based service or any other OSS service can just implement in Velox will be like a clean way to kind of integrate into Velox versus like hiding the whole reader behind an exchange source, but this is still under discussion. So so that's a rename. So the exchange writer is now like we're figuring out if we can call it materialized partition output, just to stay in Velox semantics of partitioned output and output buffer. And it's currently like configurable. It's file, Costco, or any other OSS shuffle engine. The other thing that we are experimenting with and have some early numbers are around adaptive row versus column encoding, where the writer itself looks at the size of the row group, and figures out if we need to encode it in columnar or row-wise exchange. The interesting thing we found here is that the compact row format, which is in Velox, which is a row-based serialization format, actually wins in compressed size compared to when you GSTD compress columnar data. Well, we still are trying to find a very good explanation for it, but the current explanation is that the repeatable byte pattern of compact row compresses much better with GSTD than the columnar format. But we used, to be fair, we used flat vectors, which means that we didn't use run length encoding or any of the encodings. So if we use a good encoding on the columnar data, the data itself is smaller, so most likely the columnar would win, but this is a future work. One of the other things we implemented, moving on from exchange, is broadcast join. So again, this is in the theme of not transferring data between the JV and C++. So Spark in general has broadcast variables where the driver will kind of broadcast the data, and you can use it as a hash table in your worker, but we write out files and we just pass around file metadata, and then we broadcast the file metadata that each worker would use to rebuild the hash table, read those files, and then do the probe. But this turned out to be expensive because every task would read a lot of small files, and they would just thunderherd the I/O layer and slow it down and throttled. So we implemented hash table caching in Velox. What it does is we build the hash table only once per worker. It just avoids rereading small files and reconstructing the hash table. And you also save CPU time. There is a Velox doc on it. Again, this is just in the theme of, while trying to Veloxify the stack, what are the reusable things we can build here? So this is one other thing that we contributed. Sort merge join, I think we already touched upon this one. Instead of a hash join, we use a merge join to kind of keep the memory pressure low when partitioning is not good enough. Data grows faster than shuffle systems can evolve, so even with our current shuffle system that's quite scalable, a lot of the jobs just have a lot of data that you can't partition well enough to do a hash join, so you need a sort merge join. So we added support for that. One interesting thing we found is that instead of if we use shuffle service to sort the data before reading, it's actually cheaper compared to having an order by in Velox. And when we investigated, the finding was that this is mostly because the order by does a lot of SERDE CPU cost on the spilling row vectors. The Costco reader is just going to sort the keys. We serialize the key before, and not even touch the whole row to sort it. And once you have the global sort done, you just deserialize the compact row into row vectors. Yeah, so, oh, OK. Sorry, I'm just trying to find, oh, it's 25 minutes, OK. Yeah, I think this part I'll just try to skim. I think we have heard quite a few talks kind of go through this. We just had to do a lot of shadow testing, performance testing to get the numbers we want. We did a lot of regression kind of tackling. And then we used these signals to also certify initial workloads, move them for productionization and rollout. Shekhar had a great talk, so you can refer to that. I'm running out of time. So there are a few challenges that are there with meeting our performance goals. These are common to Spark and Sapphire. We run in a containerized environment. We are I/O driven. There's a lot of variance. So to get high confidence numbers, we just have to do a lot of performance testing. So I will also have to skip this, short on time. So the summary of this slide is we noticed that in general, on the larger workload engines like Sapphire and Spark, we are more memory bound versus Presto that does a lot of filtering and analytical queries is CPU bound. Yeah, I think how did we deliver on our promise or the vision we initially set out on making the extra large SQL queries efficient? We overall see 2x CPU reduction. And this is in line with Presto for total cost reduction. We see like a very wide range between 1.5 and 10x on scan-heavy. Scan-heavy queries just do better. The last one on building reusable blocks for fault-tolerant execution. With materialized shuffle, we kind of built hash table caching. We built the native reader writer clients, which if you heard the talk on PySpark Velox, and of course you heard just now on Gluten, were all reused in those projects. We are transferring the Presto OSS operators into Velox for shuffle. And we did early prototyping with the above components on Axel to just build a fault-tolerant scheduler and see like a local end-to-end query run with materialized exchange with completely native Axel scheduler. Yeah, the current journey is like cost and performance. We're halfway through, but we also built out a lot of the building blocks like we set out to do. Yeah, that's it. Thank you. This was obviously done with the coordination of a lot of team members, just speaking on behalf of all of them. So yeah, thanks.
So in the world of big data compute, when it talks about Velox plus Spark, it's often painted, pictures painted that the future of big data compute is hybrid. So orchestration, JVM for orchestration and the native for execution. But we saw that native can also be fully, the execution can be fully native also, like direction we saw from C++ Presto. So in last 2 days, we actually saw a lot of progress on the Velox front. And also today, we saw a lot of progress on the Gluten front too, both Velox and Gluten. For example, we saw that people are using Velox on DPP. There is iteration support on Velox. We also learned about the probabilistic data structure on Velox. We saw people are leveraging Velox for vector search. And even now we have geospatial capabilities, geospatial capabilities also in Velox. Right. So, and similarly, there's a lot of progress also in gluten side. Right. Now, what is the value of all this? The real value, it comes only when there is more adoption. So there is an adoption story. Okay. Good afternoon, everyone. I'm Kaushik from Oracle, and I'm going to share our adoption story of Velox into Oracle's AI and data platform. As you see, I didn't put any agenda, right? Typically, the first slide is the agenda, which will explain the control flow for the slides. But I didn't put an agenda because I'm here to share with you a journey story. And a journey doesn't need an agenda. Journey may have a destination. Okay. So let's see what is Oracle's AI data platform and how does Velox fits into it, or what asked us to choose Velox into it. Okay, so Oracle's AI data platform is a unified system that brings together data, analytics, and AI into one governed environment, so you can build, run, and scale AI applications directly on enterprise data. Okay, that's a one heck of a statement, right? So let's see what it does. Okay, to break it down for all of you. Okay, so it unifies all enterprise data, which basically means structured data, unstructured data, batch data, real-time data, data from multiple sources. Okay, and then it helps to build data pipelines, which is basically end-to-end ETL pipelines plus data engineering system. You can ingest data, you can prepare data, you can transform data. Okay, it provides catalog plus governance, which means you have data catalog, you have rollback access control, you have data data lineage, all built into systems. It also enables AI plus machine learning, which means it supports ML deployments and agentic AI supports. You can build agents, you can build agent applications, and it provides analytics and BI, which means you can have data explorations, you can have dashboard, you can reporting. It also provides unified development environment, which means you get a workbench, which data scientists can use to train their model, which data engineers can use to build their pipelines, which data analysts can also use to run their notebooks, basically giving a single pane of experience, single pane of glass experience. It provides storage and database layer. So storage is basically supported by Oracle Cloud Infrastructure, OCI's, and OCI's object storage. And we also provide Oracle Automated Database for curated data. Okay. And then we have support for end-to-end lifecycle support. Basically, you ingest, you prepare, you train, you deploy, and use everything end-to-end in a single system. Okay, so the primary thing is that we eliminate the need to glue together multiple systems. Okay, so let's step it down to the thing that makes more sense to our talk today. Okay, so there are multiple user entry point in the Oracle AI data platform. User can use a notebook, can use SQL queries, there's API endpoints, and then we provide unified workspace to work by the users. But the processing is done by the Spark. So that's the main thing. The distributed processing is supported by Spark engine, and then the OCI object storage provides the fundamental foundational data lake layer. Okay, so then the two important aspects that's useful for this talk is that we and the AIDP uses Spark-based processing for data processing, and then OCI object storage for data lake. Okay, so these are the two things that's important to ask. Okay, so now since it uses Spark-based distributed processing, then of course we wanted to have Spark acceleration. We wanted to improve the query performance for our AI data platform. Okay, but we start thinking from the perspective of an user. Okay, so basically the rationale is that we don't want to we want user to give faster query performance, and we also wanted to save users compute cost. But at the same time, we don't want any customer visibility, any customer visible complexity. So if there is a changes, we should change from our side. As far as customers are concerned, their Spark APIs should remain unchanged, their SQL queries should remain unchanged, their notebooks should remain unchanged, their workflow jobs should remain unchanged. Okay, all the changes to enable the native executions or to allocate the off-heap memory should be handled by us from the backend. Okay, so now Gluten plus Velox somehow serve this purpose very well. Especially Velox helps with the fast executions, and then Gluten can take care of the seamless fallback for the operator that Velox doesn't support. So that's a kind of fit the bill very well for our use cases, where we can do all these changes from backend, and our customer automatically start getting the performance benefit for their SQL jobs, or for the data frame job, or for their workflow jobs. Okay. So keeping this in mind, we started our journey to integrate Velox and Gluten into our Spark pipeline. Okay, Spark processing engine. So that's the journey starts. Okay, so I'll share some of the challenges and what we went through and the result we saw. We just started actually. So the first challenge actually didn't come from Velox. The first challenge came from Gluten. So in Oracle, we use Oracle Linux for our development, and so we needed to bring support for Oracle Linux into the Gluten code base, to set up the thing and free ourselves. Plus, we need to do few wiring and configuration, and then also few of the authentication stuff, so to unblock us. Okay, so with that in place, we are ready for Velox and Gluten integrated into our Spark system, and we wanted to then run a TPC-DS query and to see the result. Okay, so let's look at the number together after our fast integration with Velox and Gluten. Okay. Okay, so I don't know how do I put it. I can say surprise, 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 or I can say shock, shock, shock. If you look at the numbers, you will see that a few queries definitely we saw good improvement, but there are a lot of queries there is not much improvement. I mean, plain vanilla Spark had actually better performance than Spark with Velox and Gluten. Okay, so that's kind of initial shock to us when we started. We didn't have by the time we still didn't have the full scope of the work figured out. We were still doing the POC, and so it turns out that just integrating Spark, just integrating Velox plus Gluten is not sufficient to give you full impact. Okay, as you can see the query here. We also need support for native scan, native scan for OC object storage. Okay, and that was not present in the Velox when we started this work. Okay, so in the absence of native scan, what happens? The Spark it goes to the JVM scan, and with the JVM scan with Velox and Gluten, you don't see you see kind of mixed kind of result, right? So it's clear that we need some storage I/O support. Just not that Velox and Gluten is not sufficient. Okay, but it's a valid question for a beginner who are new to this space and who are trying to integrate. Right, first time. It's a very fair question, right? If you wanted to compare with a plain vanilla Linux. Plain vanilla Spark with a Spark with Velox and Gluten, we know that the Velox bring memory efficiency in terms of columnar format reading, and also Velox bring the compute efficiency in terms of SIMD, taking advantage of SIMD. So, and then native scan was JVM native reader even in the plain vanilla Spark, and it is also JVM native reader in the Velox plus Gluten. So then why with a compute memory efficiency we're not seeing gain for all the queries? I mean, we should see gain from all the queries. May not be for as much impactful as with native scan, but we should see gain definitely, right? So it turns out that when you bring Velox plus Gluten into the ecosystem, the complete dynamics change a bit. Okay, so now you actually, though you get some gain from in terms of compute memory from Velox, you also pay some extra taxes. Okay, so one is that when the reading is having by JVM, you copy the data from OC object storage to JVM structures, and then you copy that to Velox native columnar format. So there is two copies happening unnecessarily, which means basically we are having some redundant data movement there. So that is one tax. Plus, you're also doing a conversion. So I call it format conversion tax. Basically, converting from you're reading as a row format and then converting to column format, and that is again unnecessarily coming because we don't have any native reader there, native objects OCI reader there. Okay, and these things will happen every execution boundary. So, for example, in JVM, native JPN, when there's a fallback, every time you'll end up paying this extra compute and memory tax. So, for some queries, it turns out that the amount of the loss you'll have because of this extra tax will actually outweigh the gain that Velox bring. Okay, that outweigh the compute gain that Velox bring. Okay, so with that analysis, it's very clear that we actually that Velox plus Gluten with Spark is not sufficient for AIDP. We actually, though Velox brings compute memory efficiency, you also need the storage I/O support. So basically, need the support for writing an OCI connector in Velox, right? Now, so that becomes our next challenge in the journey. That now you write a new connector for your object storage. Okay, we don't have that in the code base ready, and so that's both good news and bad news. Okay. So the good news is that to write a native OCI connector, we have to implement the custom Velox file system interface, and this interface is very well abstracted in Velox. So implementation has become relatively easy. And also there are other storage systems like S3 and the Azure and then GCS. They have already implemented their connector. So you have some precedent also here. But we have bigger challenges waiting for us. Unlike in S3 or GCS or Azure, we don't have any C++ OCI SDK for OCI. Okay, we have Java SDK, we have Go SDK, we have Python SDK, but no C++ SDK. And you need that thing in place, like in the entire network plumbing and authentication in place that you can use to implement your OCI connector. Okay, so then the scope of the work become now bigger, right? From writing one connector, you have to now write an entire SDK for your storage, and then use that to build your connector. So the scope of the work has now increased. Okay, so then the question becomes: is it worth it? I mean, is it? Are we going to really get that much gain to take such a bigger scope now, right? To produce a new SDK also. So we say that if we can do some POC without taking that deeper work, bigger work, and can produce that, okay, it's indeed the right path, then it will be helpful. So fortunately, we had some help there. Okay, we have the OCI actually has some S3 compatible endpoint support. So, and OCI provides some S3 compliant endpoint support, which one can use using an S3 connector. And also, fortunately, the Velox has S3 file system already built on AWS C++ SDK. So it's available in the Velox code base. So we said that, okay, if we have already S3 connector, and we have a way to connect access OCI object storage using an S3 connector, because we provide that endpoints. So why not use that path and do a POC, right? And see that, okay, the things are working before we take a bigger work. Okay, at least for POC it's good enough. It's not good enough for the production use case, because in production we'll need a lot of OCI specific authentication support, OCI specific network plumbing. So those will need bigger work. So instead of going such a big work, let's do a small POC with this and see that it's working. Now this time results was actually encouraging. Okay, I didn't show the result here, just for you. Let's save it for with the native connector. And so, so with that encouragement, we actually went ahead and implemented our C++ SDK, miniature version of C++ SDK, and with all OCI specific implementations. And then we use that to implement our Velox file system interface. And then we also brought the wiring in the Gluten, so that now end-to-end things are in place. Okay, so with all this in place, now we can celebrate the result. Okay, so let's quickly celebrate the result. And we run TPC-DS query this time, and you can see that with a scale factor of 100,000, we have almost all the queries have better result except for 3 queries. And you can see that top 10 queries really have good results. Some of them have 7x to 8x improvement. And same result we saw with 1,000 scale factor TPC-DS queries. If we take a top 10 improved queries, you see again the very good impact. Some of the queries 7 to 8x improvement here too. And I can also see similar thing with the 10 scale factor. You see almost all the queries has now better improvement when everything is end-to-end. Okay, I mean from Spark to Gluten to Velox to native connector. Okay, and you can see that some top 10 queries also have very good improvements. Okay. So with that, we have things in place, and we integrated entire thing with our Oracle Editor platform, and we have actually make it available to our customer to use. So what is our contribution to Velox community then with this work? Okay, we just started. So I mean, our primary contribution is adoption. Adoption is the primary contribution. I'll just say, more people adopt, it encourages more other people to adopt, and it also brings more use cases and bring a compounding effect. So I'd say that's a first, very small, impact. Plus, there's a little tangible impact also, tangible contribution also. If you look at the Velox code base, you will see that Velox has, as I said, there's a storage adapter for GCS and Azure and S3, but there is nothing for OCI. Okay, it's missing from the code base. And if I quickly show you a snapshot of MUM8, you can see OCI there. So that's the tangible contribution to start with. Okay, we need to just refactor out the SDK part, then we can push the changes to this thing. Okay, so yeah, so I didn't add any concluding slide because we didn't conclude. It's just the beginning. It's journey will continue, and we'll have more stories to share with you. Thanks everyone for present hearing.
Hello. Hi everyone. My name is Krishna, and I have been working with Pratik, another engineer on our team. And we work on Velox, but we have been working over the last 1 or 2 months to increase the efficiency of open source contributions to Velox. And if you've been working over the past any number of months, then you might have noticed some changes over the last couple of months that have hopefully made things a bit better. And we will continue to work on this to make things better as we move towards GitHub first. So I think a few months ago, if you were like trying to contribute to Velox, if you made any change, you would see CI signals take a long time. Like it would take 2 hours plus. Like 128 minutes was our longest. On an average, it was always end at more than 2 hours. And then you would have test run for 45 minutes. And if you had failures, you had to like go through a sea of logs. And it's all considered very normal, and but it wasn't the best dev experience. And before moving to GitHub first, we wanted to make that better because with GitHub first, we wanted more meta engineers, especially to have lesser friction when using Git and OSS workflows compared to internal. Right. So we concentrated on like making things faster, reducing the PR turnaround, getting signals faster to you, making them more greener, in the sense that you see less red, more green, and less flaky signals, less, when something's red, there's something wrong, you have to look into it, right? And then making it more smarter. So if something is wrong, it tells you, hey, this is what's wrong, go fix it, right? So I'll be just covering stuff like that now. So to start off with, like, if any of you have contributed, like, these are like the biggest jobs that we used to run on the CI, and Ubuntu debug was the one that would take like 2 hours plus. We reduced that to 53, and in fact, it's better than 53 right now. It's around 40 odd. Fedora debug also, it went from more than an hour to like 35 and less. Adapters, which is the big job that I think most OSS folks are interested in, which runs the whole gamut of S3 and hopefully OCI, as the last gentleman was talking about in the future. All of that is reduced to like 30 minutes. And our test used to run 45 plus minutes, and I'll talk about what I mean by test groups, that went from like 20 minutes to 13, 14 minutes. So we did a significant work to like reduce the time, make sure to get signals faster. So how did we go about doing that? So first thing we did was we measured per file timings on the EC2 runners for our actual file. So we used to run all the tests sequentially. Like you'd submit a job, we'll build everything sequentially, then C-test would go and run every test sequentially. And that is like really slow. Even if you try to parallelize it, it doesn't scale well or something. So what we did was we measured per file and we bin packed them into groups so that we could parallelize and run these tests across workers and like get a speed up. With the bin packing, we were smart about bin packing, so we didn't have any skews on certain end, and so with that kind of bin packing, we were able to get the test runs from like 45 minutes, which is take to is now less than under 20 minutes, like 15 to 70, something around that. So that created a huge speed up. We also run fuzzers. We were doing like a full build to run all our fuzzers. We had like 14 fuzzers right now, and we would do like the whole Velox build, which would come. In case you don't know, we have 550 targets when you build Velox. And so these 550 targets, like you don't need 500 of those targets when you build fuzzers. So we just build those fuzzers, ship the fuzzers out to like their own workers, and we run those instances. All these fuzzers link against libvelox, which is a shared library that we create. We also tuned the workers. We went to bigger workers, but we also tuned it. So apart from just using bin packing. And we also did some source for code rebalancing, like certain tests, for example, the index lookup join test by itself would take up 15 minutes plus, like almost 1,000 seconds to run it. We split that up and then refactored that so that we could parallelize that better. So with all this, we were able to like get, improvements in speed up. It came at some cost. So like I said, we had to group test binaries. In case if you don't know, like 500, like the actual Velox output is that most people are interested is just libvelox.shared object in OSS. That's just one. Every other target is either a benchmark or a test case or a fuzzer binary. It doesn't, the model that Meta internally follows where we use Buck, it's, we encourage use creating targets and false targets and all that. That works internally in Meta because of the infra and the scale we have to handle these kind of things. And because we don't have shared linking inside our infra, we use static. But on OSS, that's like not good at all. It like slows things out considerably. Each time you create a target binary, you end up writing almost half a gig executable, right? So over 500 targets, that's like 20, 30 gigabytes just binary executables where, the static code is like just replicated n number of times. So to deal with all that, we group the test binaries. You collapse the binaries into it. So doing that, you lose some level of, you can't target certain egg texts, so you have to which is fine. I think when you're submitting CI, like you mostly ensure like you run all the tests. So I think that was like a trade-off. If you don't want it, you can set the group test to off, and then you can target some specific test that you want to run. And like I said, we had targeted fuzzer builds. Also, we did a lot of improvements. Your CI runs on these Docker images where, we didn't have that much discipline going ahead. Like you would, like people would download dependencies and stuff like that. And we actively tested that out because we wanted to ensure that that part of code was well tested. But that creates a lot of flaky builds. And going to GitHub, we want to make stuff green. So that means reduce flakiness and increase reliability. So now we have containers that have everything baked in. And so that has made things much more reliable at the but there's a cost in pays. You have to the build step of the image is more. So if you are changing dependencies, that's a cost you pay upfront. But that's just one time. And then also system depends. So like I said, we just switched to system from bundle dependencies. Bundle means you pull in stuff from the internet to build stuff, and we don't do that as much on CI anymore. So all of these changes, got us 60% reduction in build times and test times, which is significant. And then some work that Pratik is also doing is going to bring that up much, much more. So our goal is to get it to building on your local dev machine or as close to that as possible so that you get really quick signals. And the second part is making stuff greener, right? So when I say green, what I mean is no more, less red. So unless you're pushing out code that is wrong or, we don't want to do that. We don't want people to get bad signals or have flaky signals, right? If our signals are flaky 30% of the time, you get into the habit of ignoring the red signals, and we don't want folks to do that. A red means, yes, something is absolutely broken. You need to go check it out. So we added flaky test retries with JUnit XMLs that capture the flaky test part. And then we have the first run that's very aggressive. And on failures, we rerun the failure to figure out the flakiness, and it's really flaky. Flaky tests will show up as yellow warnings and not red failures, and then we follow up with the authors to try and get those fixed. We also have structured failure reporting. So G-test assertions will land as a PR command and a GitHub error. You don't have to go through all your your thousands of lines of log to figure out what failed. It's very frustrating to go through those whole set of log, find out which particular test failed in Velox exec text, because that's pretty long. We did a lot of work to kill the fuzzer crash failure false alarms because we increased the parallelism of CI. A lot of that work was done by Pratik in figuring out why those fuzzers failed. So much thanks to that. And in that, we've deterred, a lot of the hard-coded timeouts we had caused these issues. Like we resolved table evolution fuzzers 10-second timeout, reduced that problem, raised the Presto request timeout for our window join aggregation fuzzers. So all these changes help reduce 40% of our fuzzer failures. Fuzzer failures were used to account for a large percentage of the flakiness and the red signals we get, and we have brought that down considerably. It's still not below to the level where we'd like. We wanted to get have fuzzer flakiness below 5%. It's around 10% right now, so we're still working on improving that. So, but this reliability has made sure that if you see a red signal, it's very likely something you caused. So, you have to look at, it's a better signal for you to go look into and fix stuff. So once you get the signal, so some of the some other stuff. So it's just not fixing fuzzer bugs or fuzzer infra bugs. We also found real correctness issues. One of the issues that Pratik found was that there was a file descriptor bug that we found, which had about a 0.75% flakiness rating, and that was because root cause was that there was a member initial isolation order bug, which closed stdin during a test. And then glog would grab that same stdin file descriptor 0, and then it would write it out, and that would cause this corruption in the fuzzer that would come out and it would fail. And it was not something, and we struggled to replicate it until we used, spent a day or two with Claude and finally figure out that bug. So that was pretty cool. He discovered several bugs that he fixed, make timestamp off by 1, where we had wrong timestamp, where timestamp values could be 24 hours and 60 minutes, which is wrong. Some optimizations where datetime format was being recompiled per row, which made things slow, and so that also improved stuff. So in process of making stuff greener, we actually fixed quite a few correctness bugs also, and also made the signal better. Also, and the next section I want to talk about is making things smarter. So with AI, Claude, and stuff like that, we rolled out the ability for folks to actually call upon Claude for code reviews and comments and questions inside our CI. We restricted it to meta engineers, but we are going to allow all committers to Velox to have this capability. So if you're a committer to Velox, you could invoke Claude, and then ask questions or ask it to do code reviews and stuff like that. So this is, I think this is pretty useful, and it gives us feedback sooner. We are trying to also incorporate this, with the proliferation of Claude and these AI tools and the PRs that AI-assisted PRs we're getting. I think we have to set roadblocks to ensure that, the code reviews we get have some minimum level of bar rather than, having the burden of PR reviews fall upon just the maintainers. So that's the next step that we'll be working on. So apart from that, we also did some really cool work on the nature of your build. So build impact analysis lets you to know how targeted your change is. If you're making if change to type.h or something fundamental, you can see that your change is going to affect almost every binary that we create, 500 or something, and how fundamental that change is and how careful you have to be when making that change. And we do that using CMX file API gives us the file to target mapping and allows us to figure out all the changes that you make in your PR, how it affects and which are the source targets that is going to come. And based on that, we can, we just added the build impact analysis, but we're going to use this to drive builds in the future so that we just build the targeted, the targets that are affected by our code change and make sure they build and the tests succeed. so that you get much quicker feedback rather than running the whole CI, building every target, running all further. So we expect that to like reduce the turnaround time very significantly. And the other cool thing we also added is the CI failure analyzer, which allows us to, which you should have seen if you have been running, submitting code. If you see any CI fail in your job, like this workflow runs and it tells you what failed, why it failed, whether it was due to your changes or whether it's a pre-existing issue, and also gives you suggestions on how to fix it, which I think is pretty useful, and it's auto triggered. So that, I think that has been well received by the community. So all of these changes, the net effect is that if we expect PR feedback in like, you get PR feedback on your PR in half the time in respect to signals. Red status means something is wrong with the PR. You have to fix it. Like, it's not something you can ignore. Failure, cause, fix, and suggestions will land as a PR community. We'll try to help you with your PR and let you know why it broke and how you can go fix it. And we'll also add, some sort of automated PR reviews to make sure it meets a minimum bar of our PRs. For maintainers, you have to do, you have to do less drudgery in looking up logs and explaining to folks why it failed or whether the failure was legitimate. So you can, more hands-off for the maintainers, and they have to like actually look at, do more real work rather than log archaeology. They get an estimate on the impact of the particular change. It's hard to quantify impact, but at least you get an idea of like how dangerous some change can be. And then again, faster feedback for the maintainers too. So next, we're going to add more failure analysis coverage and more Velox-specific review skills, and also add faster builds and faster build, so that you get on your PRs, you get much quicker feedback on what happens next. So all this has been leading, like I said, to because we want to do GitHub first. With GitHub first, right now, for those who know, like the source of truth is inside Meta's FB code. Like we import stuff and then lands in Meta, and then it's exported externally and merged there. With GitHub first, this order will reverse, and GitHub becomes the source of truth. Once we get there, we plan to get there soon, but we're still working on stuff. But for OSS folks, for external contributors, your workflow would still remain the same. Essentially, before you merge, though, before you get the power, what would happen if you went to GitHub first is you get the button saying, yeah, click, you can merge in GitHub. But before that happens, there will be another workflow that runs that validates it and pulls in your code again, and we run some sort of backwards compatibility check and further analysis to make sure it's good. And then if that fails, you would get some sort of signal saying, hey, why it failed. Whether it's like a backwards compatibility failure or test or build or something like that. We can't, some of that will be sort of like restricted, like we might not be able to give you stack traces and stuff like that, but we'll give you the general nature, and we'll have somebody work with you to fix that. And the reason why we do that, since it's C++ and our APIs are still not that well defined, we're hoping this is like the first step we can use to like make it GitHub first, and then slowly work on locking things down so that we can completely make it GitHub first and eventually get rid of this step. But apart from that, it should all be the same, and merge timing should be similar. And if, like I said, it's coming relatively soon. And if you have questions, you should feel to reach out to me, Pedro, Rohit. And yeah, so that's all the work we have been doing on the CI build side. I hope it's been useful to contributors, and we welcome suggestions, and we want to increase the velocity of contributors and the contributions coming into Velox. So again, thank you for all your help and efforts.
Hi, everyone. Thanks for stay here for the last talk we have. My name is MJ. I'm from Meta. I work on the batch compute team. Today, we're going to talk about our journey about how do we migrate Java UDF to Velox use AI at scale. So we're going to start with our the problem space, what's the problem we are solving, and then what's the tooling we are building for it, and then our end-to-end solution, and then share our current status and what's our next step. So we'll start with our problem space. So as our previous talk mentioned, at Meta, we are migrating our Spark workload from JVM to Velox runtime through Gluten. So ideally, you can see on the left side, everything just running on Velox native runtime, and until it hits the Java UDF, which Velox cannot run. What Gluten does in this situation is fall back the unsupported Java UDFs back to the JVM on the right side, and then get the result back to the native until the UDF finish. It turns out this is one of the biggest blocker for us to fully utilize the performance win from the Velox runtimes in many ways. For example, the data conversion between native and the Java runtime is very expensive. And also with the fallback, we lost lots of the optimizations on the native side. And also, this also complicates the memory management on both JVM and the native side. In addition to that, what complicates the situation more is that at Meta, we have more than thousands of the Java UDFs and more than 60, around the 700 of this UDF. We don't have any of the Velox equivalents. We only have the Java coders. So this is a huge number of the unsupported Java UDF we have. So how can we tackle these problems? So initially, we just try to manually rewrite this UDF. We read the Java code and then manually rewrite in C++. It takes weeks, even longer, to migrate even one UDFs. And also lots of time, we misses lots of the edge cases because there's no documents and no unit tests for that. And also, since the volume is huge, 700 UDFs, so it cannot scale. So what we do next, as the AI is getting more powerful, so it's very naturally to ask, so can we just use AI? So can we just ask AI, read the Java code and rewrite everything into C++? So I believe many of you guys already tried this method, but however, it still doesn't work very well because AI is very good at reading source code very fast and generates boilerplate C++ code instantly. But lots of time, AI is not very good at catching many edge cases, and also AI cannot verify its own work objectively. So here is some a real example we hit when we migrate some of the Java UDF. And for example, for one of the UDF which expecting two key value arrays. So the test cases here is provide two arrays with different size. So from the Java UDF, what I expect is we just ignore the additional values. So we just provide the two key value pairs. But when AI writes the Velox UDFs, it expect the key value has to be the same size, and then it's through the exceptions. So say the arrays doesn't match. So this is AI misses edge cases. So another example is the same UDF, and then there is a null in the middle of the key arrays. So the Java UDFs just expect to through exceptions because it doesn't allow null in the key, the map key arrays, but the AI just assume, just skip the null and just keep the rest of the key values. So those edge cases, the AI is not really good at it. So it's come from all this experience, our key insight is AI is very powerful, but it needs a self-verification harness to verify and validate its own work. So in our case, how can we provide the AI a tool to verify its own work? So the idea is very simple. Since the Java UDF can always produce the the expected results for any given inputs. So why can we just ask AI to always compare its results with the result from the Java UDFs? So with these basic ideas, it comes to our the tool we specifically built for AI agent for this purpose. So we call this tool the fast testing framework. So to make this tool AI native and AI friendly, we make a few design decisions. First, we need to provide AI agents ground truth by using the result from the Java UDFs. And also, the tool needs to be very lightweight. So everything needs to be run locally within single process. So the AI agent can very easy to run it with one command and on the same host and get back the result instantly. And also the tool need to be fast. So our tool right now can validate thousands of random inputs data in seconds. So the AI can just get fast feedback and iterate on the results. The last one is whenever there's a result mismatch, we need to provide context-rich information so AI can know exactly the issue is and go back to reread the source code and fix the bug. So this is a high-level picture of the workflow of our tools. So we have the AI generates C++ UDF and the original Java UDFs in place on the right-hand side. And the AI agent will just use one command. We use bug test, which is our build, the build tools, like the CMake, to trigger the tools in the middle to validate the results. And the tool will provide a signal of either pass or fail on the right side. So if it fails, a more detailed reports will just print it out. And the AI can just read out from the tool, and then AI can iterate and loop on it until the signal get passed. So if we look into the fast testing framework, it's on the high level on the top, we leverage the Velox vector fuzzer to produce randomized inputs with different data types, nulls, and the different encodings. And on the left side, we run the new AI generates C++ UDF directly with the random input data. And on the right side, we run the Java UDF with the same input through JNI. So there is no external cluster, external Spark job. So everything just through JNI within this same process. And on the bottom, we have the comparators, which will collect the data, the result from both Velox side and the Java side to compare everything. The values, the exception behaviors, the nulls, all kinds of the results, and provide the validation signals. Next, I will hand over to my colleague Sandeep to introduce how do we leverage this tool to build our end-to-end solutions based on the AIs.
Thanks, MJ. Before I jump into the solution, so the first testing framework for sure is key to ensuring the correctness of the migrator UDFs, and it also provides that high confidence. But on its own, it's just another tool, and it needs someone to drive it. And to scale the UDF migration, we needed a system that can wrap the code generation and run it through the first testing framework, and that ends up being a single automated loop. And the solution that we have is this AI pipeline. It kind of starts with this touch point where the user prompts it to migrate a UDF, and it responds by kicking off this discovery and classification phase before writing any piece of code. It looks at the prod query plans. It looks at the Java UDF references to figure out the type of UDF. It could be a scalar or an aggregate function or a Spark expression. Once that is done, it also determines the migration path. So in some cases, it helps to avoid duplication. For instance, it might find that an equivalent UDF exists on the Presto side, And in that case, it ends up using a simple registration path instead of a full-blown migration. Once the discovery phase is done, it enters the generation phase. And this is where a lot of the AI heavy lifting happens and bulk of the migration work happens. So we know that AI is so good at reading the code, understanding the semantics, and then outputting new code. In this case, provided that you have the Java reference, the Hive UDF, and once you combine that with the linters and the code style guides, it's able to generate pretty good code. It also generates as part of the generation, it also does generates the first test and hands it over to stage 3. That's where the first testing framework kicks in and runs thousands of iterations of first test. If it finds issues, it sends them back to the generate phase where the patching is done. And that process repeats until the comparator says that everything is good. Stage 2 and 3 is currently implemented using a Ralph loop, and it perfectly fits the current model of TDD cycle that you just saw. Once everything looks good with the first stage, it moves to the shadow test. So that's where, this is probably like the longest running stage we have. It picks the candidates from production and it runs them on the new and the old code path. And it also has the hash validation built in, so it ensures code correctness for the migrator UDF. Yeah, once everything looks there, it moves on to the verify and submit phase. So this is key. Like, we have this case where the shadow runs fine, and maybe once you look in, you see that there is a fallback to JVM. So the verification looks into the shadow runs, digs into the tester runs and the executed plan, and makes sure there was no JVM fallback. So it basically looks at the executed plan and looks for the presence of Velox columnar to row operator and the relative ordering of the UDF execution. Yep, so at this point, everything looks good. It creates this, it autofills the diff plan, test plan, and creates the diff for review. So looking at how we got here, this was all before AI, right? We started out manual, all the phases of discovery, code generation, and the verification all were done by hand, and obviously it didn't scale well. And then once we had AI in picture, that's when things started moving fast. We were able to delegate a lot of the volume work to AI in the form of AI prompts and instructions, and that kind of helped speed up the migration. But it also came up with the challenges of, you have to repeat the AI instructions, and sometimes you miss certain stages, and you end up having inconsistent diffs. And the learnings from this state led to the current state where we have now codified a lot of this AI instructions and prompts into skills, commands, and we also wrap them into an orchestrator, which can then pick up the task and run with it. Still have the touch points. The engineer has to kick off the migration, then there is a checkpoint confirmation, and obviously someone has to review the diff. Coming to the results, we see a tremendous increase in speed of UDF migration, going from a few weeks per UDF to under a day on the UDF right now. And at the same time, the correctness verified through the first testing framework and the shadow test. In terms of challenges, non-deterministic UDFs and formatting variations. I think this was covered in previous sessions as well. Like, you have floating point number representation, differences between Java and C++, which kind of limits this framework. And we also have Table type functions which are not currently supported by Gluten remains a limitation as well. What's next? Yeah, so we want to try to fully automate the UDF migration process. So this more looks like almost no touch points. And this means you have an auxiliary pipeline that kind of looks into the production usage, finds the unmigrated UDFs, and then kicks off the AI pipeline, which we have in place right now. And at that point, the only involvement comes in the form of diff reviews. Yeah, so that's the goal we have. Yep, that's it. Thank you.
I'm going to keep this short and sweet. I know it's been a long 2 days. So thank you, everybody, for sticking through all the way to the end of day 2. I know there were so many sessions this year. Everything's recorded. Everything's on live stream now, accessible. But this is really great. We do these things to get the community together. And of course, it's great to get all the content, but more importantly, to make connections with each other. So thank you. Make sure you're following Velox on LinkedIn, join the Slack channel, contribute to the project, and keep an eye out for VeloxCon Europe, VeloxCon China, and then hopefully next year's VeloxCon. Thank you all.